Welcome to the Deep Dive. If you've ever looked at a project timeline and wondered if it was based on, I don't know, science or just pure wishful thinking, you are absolutely in the right place. We are moving so far beyond the simple world of, checking boxes on a calendar or staring blankly at some static Gantt chart.
Right.
Today, we are diving deep into project execution, into risk governance, and into forecasting by getting into the global standard for how complex work actually gets mapped out.
That's exactly right. If you're preparing for a critical capital project review, or if you need to build a plan that can, actually withstand scrutiny.
Which is always the goal.
Always. Or if you just want to understand why your team's timeline seems to hold up better than someone else's, this is the master blueprint you need. We are unlocking the Project Management Institute's practice standard for scheduling.
And this isn't just about listing dates, is it?
Oh, not at all. This standard, it elevates scheduling from what can be a clerical task, just writing down dates, to a really robust dynamic system for proactively managing complexity and uncertainty in any environment.
The relevance for you, the listener, is just huge here. This standard provides the universal vocabulary, the methodology used by certified project management practitioners everywhere. I mean, from massive construction sites in Dubai to software firms in Silicon Valley.
It's the common language.
It is. You are getting a definitive shortcut to technical proficiency in project governance. We've got the full framework in front of us, and our mission today is, I'd say, pretty ambitious.
I think so.
We want to unpack the core foundational principles and the key vocabulary that govern the very structure of these scheduling models.
And to set the context for this deep dive, it's really crucial to understand the scope of what we're looking at. The standard's historical roots are, they're firmly planted in the predictability and structure of what's called the critical path method, or CPM.
Right, CPM.
Yeah.
That's the backbone of traditional project management.
It absolutely is, but, and this is key in its modern form, it formally and rigorously incorporates adaptive approaches. Things like agile methodologies, Kanban.
So it's not just for building bridges anymore.
Not at all. It ensures the framework stays relevant whether you're building that bridge or, coding an AI application. And it's really important to note this document is meant to complement, not replace, the broader PMBOK guide. It specifically expands on section science, project schedule management, and gives us that granular detail we need for true schedule mastery.
I really appreciate that clarification on the scope. It sounds like a standard that demands rigor, but it doesn't necessarily dictate one single methodology.
Exactly.
But if this document is so comprehensive, who is the primary audience? I mean, are they assuming a certain level of knowledge already?
They absolutely are. It targets project management practitioners, the dedicated project schedulers, the planners.
People who are already in the trenches.
People already in the trenches who already have a basic grasp of project management fundamentals. And there's a really critical assumption built into its very foundation.
Oh. What's that?
The standard operates on the premise that a conforming work breakdown structure, a WBS, is already in place.
So the what of the project?
The what is already defined and agreed upon. The schedule then takes that defined scope and figures out the when and the how that work will get done using precise sequencing and resource allocation. If your WBS is shaky,
then your schedule is built on sand.
It's structurally unsound from day one. Garbage in, garbage out.
Okay, that makes perfect sense. So let's map out this territory so you, the listener, have a mental picture of the document itself. Before we get into all the details, give us the overview. What are the 5 main sections of the practice standard for scheduling?
Giving that structure is essential, yeah. The standard is organized into 5 primary areas, and they're really designed to move you from theory to application and then to assessment. So first, you have the introduction, which is what we're using today to lay the groundwork and define the strategic value. Second, there are the schedule model principles and concepts. This section outlines the foundational rules that apply no matter what setting you're in: predictive, adaptive, or some kind of hybrid.
That's where the life cycle continuum lives, right?
Yeah.
The sort of map of all the different project types.
That's exactly where it is. Third, we find the schedule model good practices overview. This covers the best ways to handle the entire life cycle of a schedule. The planning, the development, maintenance, communication.
The day-to-day work.
The day-to-day. And this section focuses pretty heavily on practices for CPM-based models, just given their structural complexity.
Okay, that's 3.
Fourth is scheduling components. This is a detailed, really granular catalog of the specific elements required inside a CPM tool. Things like activity codes, constraints, flow calculations, the real nitty-gritty.
The technical stuff.
Very technical. And finally, Section 5 is the Conformance Index. And this is, I would argue, the most valuable tool for the listener. It provides a concrete, measurable method to assess how well a project schedule actually adheres to the standards guidelines.
So it moves assessment away from just a gut feeling.
Away from subjective opinion, this looks okay, I guess, to objective, hard fact, it's an audit.
That's powerful. And just to touch on the advanced context, you mentioned the appendices. They seem to go beyond just the daily maintenance of a schedule. What kind of specialized topics do they cover?
They are crucial for context, yeah, and for highly specialized use cases. They cover the changes introduced in the latest edition, which is important for any experienced practitioners. They list the contributors, which establishes credibility. And they offer some advanced conformance assessment tools that are more diagnostic than the main overview in Section 5.
There was one more, right?
Yeah.
Something a bit more dramatic.
Yes. Perhaps the most fascinating part, especially if you're technically curious, is the inclusion of a section on forensic schedule analysis.
Forensic analysis. That sounds like Schedule CSI.
It is, functionally. That's a great way to put it.
Yeah.
This is where you look backward, often in a really contentious environment like a lawsuit or a big contractual dispute.
Oh, wow.
To determine the exact sequence of events that led to a delay, who was contractually responsible, and what the financial damages actually are.
So this standard isn't just about building good schedules for the future.
It emphasizes that this standard isn't just for building reliable schedules, it's for defending and analyzing them long after the work is done. It means every single schedule model instance we're about to talk about is, well, it's essentially legal evidence just waiting to be used.
That really raises the stakes.
It does.
Okay, so let's unpack this. Before we can even get to the complex flow diagrams or the math, we need that universal language, which is precisely what the standard is designed to deliver. So what are the fundamental building blocks of a project schedule? Let's start with a clean, precise definition of project scheduling itself.
Absolutely. The lack of clear terminology is, I think, the first reason so many projects fail to communicate effectively. The standard starts by defining project scheduling as the application of skills, tools, techniques, and experience to develop effective schedule models.
Okay.
That integrate all the project components, activities, resources, relationships to optimize execution and meet the approved schedule baseline.
The key word there seems to be optimize.
It is. Notice that emphasis. Optimize execution. It's about achieving the best possible outcome under a given set of constraints, not just, writing down a list of dates. It's optimization, not mere documentation.
So with that definition in mind, what are the core components, you call them the atoms of the project, that have to be in every single conforming schedule model?
These 4 atoms are completely non-negotiable building blocks. First, you have the activity. This is defined as a distinct, scheduled portion of work that has a duration greater than 0.
It takes time.
It takes time. It consumes time, whether that's an hour or 6 months, and it consumes resources.
Simple enough. What's the second?
Second is the milestone. This is a significant project event, but the critical distinction is that it's defined by having 0 duration.
0 duration.
0. It is a point in time. It's a snapshot of an achievement. Project start, phase completion, regulatory approval, delivery acceptance. The second you assign a duration to it, even a tiny one, it stops being a milestone and becomes an activity.
And that would mess up the whole calculation.
It fundamentally alters the schedule's logic calculation. It throws everything off.
I love that clean, sharp distinction. So activities consume time and resources. Milestones are just these moments of affirmation. But where do you see practitioners often misuse this distinction? If I were building a house, poor foundation is an activity.
Right.
And foundation cured and inspected is the 0 duration milestone.
That distinction is paramount. It's especially important when you're calculating float and running resource leveling algorithms, which rely on really precise timings. The most common misuse happens when teams try to define a phase gate-like, say, document review complete, as an activity with the duration of 1 day.
I've seen that.
Everyone's seen that. But it's bad practice. Why? Because if it has a duration, the tool assumes resources are required for that day, and it builds float relative to that non-existent piece of work. Milestones should just mark the moment an activity chain is completed or a decision is finalized. If you misuse it, your critical path calculation, which depends entirely on finding the longest sequence of tasks, it becomes inaccurate.
Got it. What's the third atom?
Third is the resource. The standard defines this very broadly. It includes skilled human resources people, but also specialized equipment like cranes or servers. It includes necessary materials, concrete, steel, and of course, budgets or funds that are required to complete the scheduled activities.
So if I don't have the budget to hire that specialized concrete inspector, that's a resource problem that should be reflected in the schedule. It's not just a separate funding issue.
Exactly. The schedule model has to integrate this. If the resource profile in your model shows a shortage or a conflict, say you've scheduled 2 activities at the same time that both require the same single crane, the model helps you detect that impossible scenario early before it becomes a crisis on site.
And the fourth and final component.
The fourth is the logical relationship, or what we usually call a dependency. These are the necessary links that dictate the order or sequence of the work. For CPM, this is often broken down into 4 types. Finish to start.
The most common one.
The most common, by far. B starts only after A finishes, but there's also start to start, finish to finish, and the much, much rarer start to finish. These dependencies form the complex web, the network that the scheduling tool uses to calculate the duration of the entire project.
Okay, so those are the building blocks. Now let's move on to the tools. We so often conflate the software with the plan itself, but the PMI standard meticulously separates them. This feels key for technical proficiency. Could you clarify that scheduling ecosystem for us? The tool, the model, the instance, and the presentation.
Yes, this is where we shift from the static components to the dynamic process itself. The scheduling tool is simply the software or the platform. It's the engine.
Microsoft Project, Primavera P6, something like that.
Exactly. Those are the tools. They provide the component names, the definitions, the formats, and most critically, the algorithms that run all the calculations. Think of it as the calculator and the canvas, but it's inert until we feed it data.
Okay, so the tool is inert. What is the schedule model then?
The schedule model is what you build inside that tool. The standard defines it as a dynamic representation of the entire project plan. It incorporates all of the durations, the dependencies, resource constraints, calendars, everything, to produce the actual schedules and artifacts.
It's a living thing.
It's a living entity. It's developed and then continually maintained by the project team with input from stakeholders. It really is the complex, interconnected brain of the project, and it's designed to be manipulated and updated constantly.
So if the model is this dynamic, constantly changing brain, what in the world is a schedule model instance?
Think of the instance as a highly detailed, dated photograph, or maybe a specific archived version of that dynamic model processed by the tool at a single moment in time.
A snapshot.
A snapshot, exactly. It captures specific data points, maybe the updated status as of Tuesday at 5 p.m., or the approved frozen schedule baseline at the start of the project. These instances are absolutely essential for tracking performance, for running variance analysis, and crucially for that forensic analysis we talked about. They provide an immutable historical record.
You need that snapshot to compare where you plan to be versus where you actually are.
Without it, you're just guessing.
That distinction between the model dynamic, future-looking, and the instant static, a historical record, that is incredibly powerful. And finally, how do we communicate all this complexity to people who aren't schedulers?
That brings us to the final piece. The schedule presentation. This is the visual output that's generated from a specific schedule model instance, and it's tailored for communication and decision-making for a particular audience.
So it's not one size fits all.
Not at all. The standard emphasizes diversity in presentation. We are talking about bar charts, the classic Gantt chart everyone knows, but also network diagrams which show all the relationships visually. There are detailed resource profiles showing who is working on what and when, activity lists, and crucially for adaptive projects, things like Kanban boards.
So the key is picking the right tool for the job.
The key is selecting the presentation that best suits the audience and the life cycle they're operating in. You don't show a construction foreman a Kanban board, and you definitely don't show a software developer a 5,000-line critical path method chart.
Okay, so why go through all this meticulous, painstaking effort? If you, our listener, are trying to justify the cost and time of creating a conforming schedule model, what are the big strategic benefits that this standard guarantees? This is where it gets really interesting for me.
The strategic value goes so far beyond just calculating an end date. The primary benefit, I'd say, is simplifying complexity. Scheduling organizes this massive, complex amount of work into manageable phases and activity groupings, which makes it humanly consumable.
Is breaking it down.
Breaking it down. But its deepest value, I think, lies in quantification. It is the core mechanism that enables the optimization of that constant balancing act in project management. The scope, cost, and schedule trade-offs.
Ah, the iron triangle of constraints. Faster, cheaper, better. Pick two. How does the schedule model actually make those inevitable compromises quantifiable?
It provides the data. It's as simple as that. For instance, if the scope has to expand, the schedule model immediately calculates the impact on time, which then calculates the impact on cost, usually due to extended labor or resources.
Right.
Or, if management comes down and demands a shorter schedule, the model forces you to identify which specific activities need to be crashed, that is, shortened with additional resources, or fast-tracked, which means overlapping phases that were supposed to be sequential.
You can't just say, go faster.
You can't credibly argue for faster delivery without understanding the specific resource and cost implication, and the schedule model is what provides that quantitative data. Without it, you are literally just guessing about the investment required.
That dynamic relationship is so key. It moves scheduling out of the back office and puts it right in the executive suite, allowing for truly data-driven negotiations and decisions.
Exactly. It supports project success by ensuring there's a rational balance among cost, resources, scope, and time, all wrapped up within a credible project management plan. And crucially, the standard emphasizes the schedule's dynamic nature. It is not a static artifact.
It's a living document.
It has to allow for iterative refinement to address changes in scope or shifts in resource availability or, external factors. It is designed to be a living document that evolves with the project's actual progress. This means your project manager needs to be constantly rerunning that CPM calculation as tasks are completed.
That constant rerunning is really what separates a good scheduling team from a great one. But beyond just optimization and updating, how does this schedule help with something like communication?
Oh, it's an indispensable tool for collaboration and for performance management, precisely because it is quantitative and it's structured. A well-structured schedule presentation, using the right visual output for the right audience, helps every single stakeholder understand the critical details, the who, the how, the where, and the when of the project work.
So everyone is on the same page.
If the entire team, from the project sponsor all the way down to the frontline worker, is looking at a consistent, high-quality model, communication is dramatically streamlined because the source of truth is singular. There's no debate about the plan.
Can you give an example of how that clarity helps manage expectations?
Sure. Let's say activity A is on the critical path, and activity B has 40 days of what we call total float. That's buffer time. That clear delineation, which is provided by the schedule, tells the entire team exactly where to focus their immediate energy and where they have some breathing room. It directs the collective effort.
Let's get into the specific applications then. Where does the schedule model generate the essential data we need to run the project proactively, not reactively?
It touches nearly every single aspect of project control and forecasting. First, the model provides the data for time phasing of activities. This is absolutely critical for cash flow analysis and for budget forecasts. You can't release funds efficiently if you don't know exactly when the associated work is scheduled to start and finish.
Okay, so that's finance. What about people and equipment?
It drives detailed resource planning and mobilization. For a large construction project, you need to know not just that you need a crane, but when precisely it needs to arrive on site and how long it's needed for. The schedule model allows you to optimize that entire logistics plan, ensuring the right people and the right equipment are available exactly when needed.
So you avoid expensive idle time or crucial delays.
Exactly. You avoid that crane sitting there for 3 weeks, costing you money, or not showing up when you need it, which costs you even more in delays. Third, it is essential for the coordination of project events and dependencies across completely separate teams. If the IT team is deploying new servers, the facilities team needs to know the exact window for environmental readiness power, cooling, all of it. The schedule model is what connects those silos.
It's the master integrator.
It is, and perhaps most proactively, it enables the early detection of risks, issues, or opportunities. By highlighting activities that have very tight floats or identifying potential resource bottlenecks that might arise from a sequence change, the model warns you before an inevitable delay actually happens. It is the project's early warning system.
And for those moments when things, inevitably go sideways or when we're exploring alternatives, those what-if moments, how does the model support that kind of analysis?
It provides the data structure you need to support those crucial analytical tasks. Running what-if scenarios is indispensable for good management. For example, you can model. What happens if our key supplier is delayed by 3 weeks?
You can see the ripple effect.
You see the entire ripple effect across the whole project. Or, conversely, you can model an opportunity. If we invest an extra $50,000 to hire 3 more senior engineers, how much float do we gain on the critical path, and is that return actually worth the investment? The model can provide quantitative, data-backed answers to these strategic questions.
And what about looking backwards?
It supports detailed variance analysis. That's comparing your actual performance against that baseline instance we talked about to understand any deviations and why they happened. And finally, it provides the backbone for reliable cost planning and forecasting.
Because cost is linked to time.
Cost is directly linked to duration and resources. If the schedule slips, the cost forecast automatically adjusts, giving management a real-time view of the potential budget overrun. Without a credible schedule model, your cost forecast is just a static budget document. It's not a dynamic management tool.
Okay, now we know the vocabulary and why a conforming schedule matters so much. Let's shift our focus to implementation. The standard isn't just a glossary. It actively guides us on how to actually build and then assess a good schedule model. So, could you review that core process flow outlined in the source material? The journey from input to output.
Yes. The development process is laid out very clearly as a 4-step flow, and it starts with some strategic choices. First, there is selection. The project team has to choose the appropriate scheduling approach. Is it going to be CPM, Agile, or a hybrid? And select the specific scheduling tool.
That seems like a fundamental decision to make right at the start.
It's the fundamental decision. You can't build a quality predictive schedule in a flow-based Agile tool, and you can't really do the reverse either.
So why is selection the very first step? And what practical factors drive that choice between, say, a CPM tool and something like a Kanban board?
It's the first step because it locks in your foundational planning constraints. The factors that drive this choice are enormous. The regulatory environment is a big one. In aerospace or pharmaceuticals, regulation often mandates a highly detailed CPM schedule. The degree of scope certainty, the expected rate of change, team experience, even the contract type.
Contract type?
Oh, absolutely. If you have a fixed price contract with strict penalties for being late, you are far more likely to select a rigorous CPM approach which handles variance analysis and potential claims much better than a pure flow-based agile system.
Okay, so selection is step one. What's next?
Second is input. This is where you incorporate all the specific data points that define the project's reality. This data comes from foundational documents like that WBS we mentioned. It's defining activities, assigning resources, determining durations, setting calendars, including holidays or shift work, and establishing all the milestones and dependencies.
And if the input data is garbage?
But the output model will be garbage. It's that simple.
Yeah.
The quality of your model is completely dependent on the quality of your inputs.
And step three?
Third is creation. All that conforming data is now processed by the tool to generate the dynamic schedule model. This is the point where all the relationships and durations are calculated by the software's algorithm and the critical path is established for the first time.
And finally, the fourth step.
Fourth is output. This is the processing phase where that dynamic model generates the schedule model instances, those snapshots, which in turn lead to the various schedule presentations designed for the users, whether that's a network diagram for the engineers or a high-level bar chart for the executive sponsor. It's a clean flow from strategic choice all the way to a communicated result.
This sounds incredibly comprehensive, but as a listener, I need to know, what is the core objective and scope of this standard and where does it draw its boundaries?
The objective is very clear: to provide standards and guidelines for effective schedule management and, critically, to define a core set of required components that are necessary to build a model that's mature enough to be properly assessed. The standard aims to make schedules valuable, practical tools for execution.
And the scope? What's out of bounds?
Regarding scope, the standard applies strictly to individual projects. It acknowledges that organizational portfolios or massive programs exist, but it focuses on the project level. The argument is that if individual projects are scheduled in a way that conforms to the standard, then the larger program or portfolio structure will naturally benefit from that consistency and quality.
You mentioned assessing maturity. That brings us back to the conformance index. So I build a schedule model. How do I actually know it's a good one and not just, a colorful picture that I made with an expensive piece of software?
The standard provides the conformance index in Section 5 specifically for that purpose. This is the quality check. It's a method to evaluate, often using automated tools, how well a schedule model incorporates all the required components and adheres to the good practices outlined elsewhere in the document.
So it moves the evaluation of schedule quality from a subjective judgment
Exactly, from does this look right to you to objective auditable criteria. For the listener who wants to look instantly smart in their next project meeting, asking if the presented schedule has been checked against the conformance index criteria is a direct way to gauge its maturity.
What are some specific criteria that a conformance index would typically assess? Give us some actionable examples that real schedulers worry about.
A good conformance check looks for things that destroy the mathematical integrity of the model. For instance, the index checks for missing logic or open ends, where an activity doesn't have a predecessor or a successor.
So it's just floating out there unattached.
It's not truly integrated into the network, which means the model can't calculate its states properly. It checks for excessive constraints, using hard dates like must start on, instead of letting the logic network calculate the dates naturally. It checks for negative float, which indicates an impossible schedule scenario that's already late. It also checks for the inappropriate use of lags, which are these forced waiting periods between tasks that often just hide poor planning. A high conformance score proves that the schedule logic is robust and reliable.
That helps explain why some of those schedule review meetings can get so heated. Now, you emphasized a really critical point regarding scalability earlier. What is that fundamental, non-negotiable rule about these core components?
This is absolutely fundamental to creating consistency across any organization. The standard explicitly states that all schedule models, regardless of the project's size or complexity, must include the core components we defined earlier: the activities, milestones, resources, and dependencies.
So the scalability rule is this. Project size and complexity only affect the scale and repetition of the components, not their actual necessity.
Exactly. A small, simple, internal IT upgrade might only have 30 activities, but it still requires defined durations, allocated resources, and logical relationships to be a conforming model. A massive international shipbuilding project might have 20,000 activities, but the fundamental types of required components remain exactly the same. The necessity of the building blocks is non-negotiable.
And that uniform approach is what allows an organization to have a consistent strategy.
It ensures that schedule models across an entire organization maintain strategic consistency, which is vital for aggregated reporting and resource optimization across the whole portfolio.
I have to wonder, though, does this scalability rule sometimes tempt small project teams to cut corners? How do you ensure compliance without making a simple task feel over-engineered?
That's a very valid concern, and it's why the standard focuses on principles rather than strict documentation mandates for every single component. The temptation to cut corners, especially by skipping resource assignment or not defining all the dependencies, is very high in small teams.
I can imagine.
However, the standard argues that even a simple project benefits massively from defined logic. If you don't define the logic, you can't calculate float. If you can't calculate float, you don't know the critical path. And if you don't know the critical path, you're just guessing what's important. The standard essentially says, use the components required to produce an accurate model, even if you keep the presentation very simple. The quality is in the model's calculation engine, not the chart's appearance.
That's a powerful point. Hey, now we hit what I think is the most interesting conceptual jump in the standard. The biggest insight here is recognizing that scheduling is not one-size-fits-all. The standard formally recognizes that the type of project dictates the scheduling approach you need. What's fascinating here is the framework for that approach selection.
This is Section 2, the Principles and Concepts, and it's all strategic groundwork. The schedule management plan absolutely must identify the appropriate scheduling approach and tool before any actual activity definition begins. These principles establish the groundwork that connects the general value of scheduling we discussed in Section 1 with the good practices in Section 3 and the detailed components in Section 4.
And the visual guide for all of this is the life cycle continuum. What are the two axes that define this dynamic map for project governance?
It's a spectrum, you see, not a choice between two polar opposites. The core concept is that no single life cycle suits all projects. The position of a project on this continuum is defined by two axes, which determine the appropriate strategy.
What are they?
The first is the frequency of delivery, which goes from low to high on the vertical axis. How often are you delivering usable results to the customer? The second is the degree of change, low to high on the horizontal axis. How likely are the requirements and the scope to shift during execution?
So if you have low change and low delivery frequency, you're in one corner, a highly predictable project. And if you have high change and high delivery frequency, you're in the opposite, much more volatile corner.
Correct. The spectrum flows from the structured predictive approach in that low corner, across to the more specialized iterative, which is high change, low delivery, and incremental low change, high delivery approaches. And it finally culminates in the adaptive approach, which is high change and high delivery.
And the choice of where your project sits on this continuum dictates everything.
It fundamentally dictates your entire scheduling strategy, your tool selection, and even the type of performance metrics you're going to use.
Let's start with the anchor then, the cornerstone that the standard is most historically associated with, the predictive approach.
This is the traditional waterfall model. It's used for projects where the requirements are known, proven, and stable. Examples would be civil engineering, large-scale hardware manufacturing, or certain regulatory compliance projects. Because the project scope is highly defined and unlikely to change, this allows for major planning up front to reduce uncertainty.
So the goal of the schedule is to set a solid baseline and then just stick to it.
Exactly. Stick to it with minimal deviation.
What does a structure look like for a predictive flow, and why does CPM fit so perfectly with it?
The flow is sequential and very predictable. It segments the work into defined phases where one phase must largely conclude before the next one can begin. A typical example illustrated in the standard is analyze design, build, test, deliver.
A clean sequential process.
It is, and CPM fits perfectly because it relies on the certainty provided by these established logical relationships and durations. Strong logical relationships are the bedrock of CPM's certainty, which is why it works so well in this low-change predictive corner. If those relationships start to break down because the scope changes, the CPM model loses its integrity very, very quickly.
Okay, that makes sense for the predictable world. Now let's dive into the non-CPM worlds, which are so critical for high uncertainty environments like software or novel product development. If a project has, say, a medium to high degree of change but still wants to deliver value faster or needs feedback loops, where does it land on the continuum?
Now we move into the more specialized approaches, starting with the iterative lifecycle. The iterative approach is designed specifically to allow for feedback on partially completed or unfinished work in order to improve or modify it. It's all about refinement and learning.
So you don't build the entire thing and then test it at the end. You build a small piece, you get feedback on the design, and then you adjust your plan for the next piece. This sounds like an engineer improving an engine design based on test results.
That's a perfect analogy. The flow diagram for this shows cycles that explicitly include these refinement loops. For example, analyze A, develop a proof of concept, then you refine AA, then you design, build a test, and you refine again, and finally you deliver.
So it's for projects where you don't know the final answer at the beginning.
It is perfectly suitable for projects where the ultimate solution or the end product design is not fully known at the start. It requires these repeated cycles of development and review to get it right. It answers the question, did we build the right thing?
Next on the map is the incremental life cycle. How does this differ fundamentally from iterative? I think these two are often conflated.
That is a crucial distinction to make. While iterative focuses on refining the solution or the underlying architecture, incremental focuses on delivery. The goal here is to deliver finished, usable deliverables incrementally, providing early value to the customer.
Can you ground that distinction in a real-world example, maybe using software development?
Certainly. If you are iteratively improving a new software product, you might spend 3 months constantly refining the underlying data engine to make it faster and more scalable. The customer sees no external difference yet. That's iterative.
Okay.
If you are developing incrementally, you release version 1 with core login and profile features. Then a month later, you release version 2 with messaging and payment features. Then version 3 with analytics. The customer gets something finished and usable piece by piece. The structure breaks the overall work into these smaller, deliverable segments, and each segment contains the full project element sequence. Analyze, design, build, test, deliver, but only for that one segment of the scope.
Got it. And when you combine the best of both worlds, the refinement of iterative and the early delivery of incremental, you land on the adaptive life cycle, which is what most people today would recognize as agile.
That's right. The adaptive life cycle combines both of those characteristics. It is the ideal approach for high uncertainty projects where requirements are expected to change frequently and rapid feedback has to be incorporated throughout the process. It's designed to maximize responsiveness to change.
What are the key strategic benefits that the standard attributes to this adaptive approach?
It enables early and constant feedback loops with the client, which maximizes customer visibility, and it ensures the frequent delivery of high-value work packages. It shifts the scheduling focus from defining the entire sequence up front to managing the capacity of the team in short, defined time boxes.
And the standard goes on to detail the two primary forms of this adaptive flow.
It does. It defines how the work is managed in practice.
So let's distinguish those two flows, which correlate to some common methodologies. Start with iteration-based agile.
In iteration-based agile, which is typically represented by frameworks like Scrum, the defining characteristic is that each time box is the same size. They are fixed, regular intervals, a 2-week sprint, for example. The focus is strictly on the cadence and the consistency of that time commitment.
So the time box is sacred.
The time box itself is inviolable. The goal is that each time box results in working, tested features. If a planned feature doesn't fit in the time box, it's pulled out and put back in the backlog. This predictability of time and cost makes it suitable for environments that still need some external predictability, even if the scope inside that box is variable.
And what of the second form, flow-based agile?
This typically aligns with methods like Kanban. Here, the time it takes to complete a feature is not the same for each feature. The work is pulled continuously through the system rather than being batched into fixed time boxes.
So the focus shifts.
The emphasis shifts entirely to maintaining a continuous flow of work and managing the amount of work in process, or WIP, using hard limits. The structure still involves analysis, design, build, and test, but the overall time commitment for the cycle is variable, based on the size and complexity of the item that's pulled into the flow. The goal is rapid throughput and the minimization of bottlenecks.
It's really fascinating to see the standard, which historically championed CPM for things like construction and manufacturing, now formally mapping out Kanban and Scrum methodologies right under its own umbrella.
It speaks to the standard's commitment to being universal. They're defining the rules for scheduling models regardless of the specific tools or methodology being used. The model simply has to reflect the reality of the work being performed, whether that's calculating resource float on a 10-year project or managing WIP limits on a 2-day flow task.
Finally, we often hear the term hybrid life cycles. When is a project complex enough to require this kind of blended approach, and how does the standard define it?
Hybrid simply means intelligently combining elements of predictive, iterative, incremental, or adaptive approaches and tailoring them to specific project phases or goals. It recognizes that many real-world projects, especially large, technologically integrated ones, are just too complex to fit neatly into one single box. The choice to go hybrid is driven by heterogeneity in the project scope itself.
Can you provide some structural examples of how these combinations might manifest in the real world?
Certainly. The standard illustrates two main ways these are combined. One is sequential. A project might use an adaptive approach for the initial requirements definition phase, where uncertainty is high, to get client feedback and clarify the scope.
So you're agile at the start.
Exactly. Then, once the requirements are locked down and the design is solidified, they switch to a predictive approach for the long-duration construction or manufacturing or system implementation phase, where efficiency and adherence to the critical path are paramount. The transition point is a zero-duration milestone, requirements baseline approved.
And the second way to do a hybrid?
The second way is simultaneous. You might have different components of the same project being managed using different methods at the exact same time. Imagine launching a new banking system. The software development component, high change, high delivery frequency, is managed adaptively using Scrum.
Right.
Simultaneously, the regulatory compliance filing, the hardware procurement, and the data center installation, all low change, strict sequencing, are managed predictively using traditional CPM. A successful hybrid structure maximizes efficiency by applying the best scheduling approach to each specific challenge within the overall project.
That covers the crucial foundational concepts and that strategic lifecycle continuum map. We've established the language, the value proposition, the quality checks, and the strategic choices. Before we wrap up, let's synthesize the core learning points for the listener.
If you are walking away with 4 core insights from this deep dive, I think they should be these. First, the PMI practice standard provides a universal and non-ambiguous language. Knowing the precise definitions of activities, milestones, remember, zero duration resources, and logical relationships is absolutely essential for global communication and for avoiding project ambiguity. You simply cannot effectively optimize or forecast without this precise vocabulary.
Second, the value of scheduling extends so far beyond just tracking dates. It's a dynamic living tool for active project control. It's used to quantify the scope, cost, and schedule trade-offs for resource optimization, proactive risk detection, cost forecasting, and running those detailed what-if scenarios. If your schedule isn't being used as a dynamic management tool, it's just wall art.
Third, schedule quality is measurable and verifiable. The standard gives practitioners the conformance index to evaluate a model's maturity against objective criteria, like missing logic or excessive constraints. And remember that critical scalability rule. The core components required for a quality model are non-negotiable, regardless of how small or simple the project is. Consistency is the key to organizational maturity.
And finally, that strategic decision you make right up front regarding your project lifecycle, choosing predictive, iterative, incremental, or adaptive, is paramount. You have to align the structure you choose with the environment, especially concerning the degree of change and the frequency of necessary delivery. Selecting the wrong map light, trying to run a high-uncertainty software build on a rigid CPM approach, for instance, is a guarantee of schedule failure, no matter how well you apply the individual tools. So what does this all mean? If you started this deep dive thinking scheduling was just about, inputting tasks into a piece of software, you now have the advanced vocabulary and the conceptual map to identify and evaluate the maturity and the strategy of any project schedule model that's presented to you. You're now equipped to ask not just when something is due, but why the critical path looks the way it does, whether the resource allocation is optimized, and crucially, whether the model actually conforms to global best practices.
That technical proficiency elevates you instantly in any project discussion.
It truly does. Our source material notes that schedule models must align with a conforming work breakdown structure, or WBS. If the WBS defines what the project is based on known requirements and the schedule defines when and how, then what happens to a project's predictability, even a traditionally predictive one managed by CPM, if that foundational WBS shifts unexpectedly mid-execution? How much adaptability or buffer should even a seemingly rigid CPM-based model build in, just in case those known requirements turn out to be less known than everyone assumed? That inherent tension between the WBS's initial rigidity and the schedule's required dynamism is something for you to mull or explore on your own. Welcome back to the Deep Dive. Today we are diving into a topic that I think, for a lot of people, just conjures up these images of, dry spreadsheets and endless status meetings.
Oh, absolutely. Project scheduling.
Project scheduling. But if you really strip away all that paperwork, the schedule it's the dynamic blueprint. It's like the nervous system for any successful project.
That's a great way to put it. Most people see the schedule as this static thing, a necessary evil that only exists to report progress up the chain.
Right. Just for the stakeholders.
Exactly. And they miss its real function. A robust schedule model is the engine. It's what drives execution, what drives prediction, and most importantly, proactive risk control.
So if your schedule model isn't solid,
then the rest of your project management processes are basically built on sand. It's that fundamental.
And I think reliability is the first casualty when that schedule isn't built with, real rigor.
It is.
So our mission for this deep dive is, I'd say, pretty ambitious. We are going to try and give you a shortcut to mastering the principles, the concepts, and all the good practices you need to create schedule models that are genuinely dependable.
And we're really emphasizing flexibility here because modern projects, they just don't all look the same. We have to be able to move seamlessly from that very established predictive world of, say, the critical path method,
CPM,
all the way into the adaptive high change environments of Agile.
And the source material for all of this, for this deep dive, it's drawn directly from the foundational standards for scheduling. We're talking about the good practices that are associated with the PMI scheduling professional designation, the PMI-SP.
That's right. This content is basically the blueprint for creating schedules that can stand up to an audit. We're going to cover everything from the foundational models to detailed Agile metrics, and maybe most crucially, the rigorous governance guidelines you need to keep that data clean and useful for forecasting.
Okay, let's unpack this. Starting with the two main philosophical approaches to scheduling. And I think most importantly, the key factor that determines which one you should actually be using.
To start, you really have to recognize that project management exists on a spectrum of project life cycles.
It's not a one-size-fits-all world.
Not at all. We talk about predictive, iterative, incremental, adaptive, and even hybrid approaches. And the choice you make, it's heavily, heavily dictated by one core variable.
And that is?
Project uncertainty.
Project uncertainty. So, okay, if you're building something like a refinery, the requirements are stable, the solution is well known, you'd lean heavily predictive.
The uncertainty is low, exactly.
But if you're launching, a new AI-driven service where you're still discovering what the customer even wants, The uncertainty is through the roof.
And that's where you have to go adaptive. You have to fit the schedule to the problem. It's the most important first decision.
Makes sense.
So let's start with that bedrock of traditional project management. The predictive foundation. That's the critical path method, CPM.
The gold standard for massive, stable projects. I'm thinking construction, big infrastructure.
Tightly controlled manufacturing, yes. It's the standard because it demands a fixed scope right up front.
And the core focus of CPM, a thing everyone's heard of, is defining the critical path.
Right. That longest sequence of activities that dictates the absolute earliest completion date of the entire project.
So if any activity on that specific path slips by just one day.
The entire project completion date slips by 1 day. Period.
No wiggle room.
And the mechanism it uses to figure this out is the precedence diagramming method, or PDM.
That's how you sequence everything logically, right? Your finish to start dependencies, your start to start.
All of it. It's how you rigorously calculate the early starts, the late finishes, and maybe the most strategically critical piece of information that comes out of a CPM schedule.
Yeah.
Float or slack.
Float is that flexibility, right?
Right.
The buffer zone.
What?
It is. It's the amount of time a non-critical activity can be delayed without pushing out the project end date.
So it's where you have some breathing room.
Yes, but strategically, float is pure gold. It's what you trade with. It's what you use to manage risk. A project manager's skill often comes down to how well they can utilize and protect the float on those non-critical paths.
Because if you waste the float,
The path becomes critical. And now your management focus just got wider and your risk just went up.
so what happens when the calculations spit out a number that's negative float? That sounds bad.
That is a major, major alarm bell. Negative float means that even if you execute every single remaining activity perfectly, with 0 delays from this point forward, you are still forecast to finish late.
So the project is already unachievable as planned.
Officially unachievable. It demands a hard adjustment right now. You either have to shorten durations by adding resources, you have to relax the scope, or you have to go negotiate a later deadline. It's the ultimate reality check that the schedule provides.
And you mentioned earlier that modern tools have taken CPM way beyond just those initial calculations. We're not talking about dates anymore.
Oh, not at all. Modern CPM involves really advanced features like resource leveling.
What's that exactly?
It's where you strategically shift tasks that have float to smooth out the demand for shared resources. Think about it. If you have 2 activities that both need the same high-demand crane on the very same day,
You have a problem.
you have a big problem. A resource leveling algorithm will automatically move the task that has float to a later date when that crane is actually available. It's what turns a theoretical schedule into an achievable one.
But even with all that power, even with resource leveling, CPM still has its limits, especially around that resource contention you mentioned.
It does.
And that's what leads us to the next step, this refinement called critical chain, isn't it?
That is the big aha moment. Critical chain scheduling, which is based on the theory of constraints, is really an enhancement of CPM.
Okay, how so?
Well, CPM is an absolute master at managing the sequence dependency of activities. But it often fails to properly account for the single biggest cause of project delays in the real world.
Which is?
Resource constraints. That one critical engineer, that single piece of expensive test equipment. The bottleneck.
So ever the one senior security architect, and her approval is required for 3 different integration tasks that could otherwise happen in parallel.
Her availability becomes the defining constraint. It completely overrides the logical task sequence itself. The whole schedule now revolves around the availability of that one person.
That makes perfect sense.
And this is where the methodology forces a really profound cultural shift.
Okay.
Instead of everyone padding their individual task durations, which is a universal, often hidden practice where engineers inflate their time estimates just in case.
Everyone does it.
Everyone does it. Critical chain demands that you estimate your tasks aggressively, typically at the 50% probability level.
So if I think a task might take 10 days, but there's a good chance, a 50-50 shot, it'll only take 8. I have to estimate 8 days.
You estimate 8.
Okay, but where does my safety margin go? I feel exposed.
The safety margin is pooled. It's taken from all the individual tasks, and it's managed explicitly and, most importantly, visibly using buffers.
Buffers, okay.
You have a project buffer, which is a big chunk of time placed at the very end of the critical chain. That protects the project's finish date.
And you have feeding buffers.
Exactly. Feeding buffers are placed where the non-critical paths merge into the critical chain, and their job is to protect that critical path from any delays happening on those other streams of work.
Wow, that is a significant shift. If critical chain is so effective at managing resources and, discouraging that hidden padding, why isn't it the standard everywhere? What are the biggest cultural hurdles?
The cultural hurdle is immense. First, project managers have to completely shift their focus. They stop policing individual activity due dates and instead start proactively managing the rate of consumption of those buffers.
So you're just watching how fast you're eating into your safety net.
You are. And second, teams. They hate estimating at that 50% probability level. They feel completely exposed, like you said. It requires total trust and transparency.
And most organizations just revert to padding.
They revert to padding because it feels safer, even though that safety is an illusion. The padding usually gets wasted early on because of Parkinson's law work expands to fill the time available. Critical chain forces all of that proactive risk management out into the open for everyone to see.
Okay, so on one side we have this highly structured, sequence-driven world of CPM and critical chain. Now let's pivot hard to the other end of that spectrum.
The adaptive response. Agile scheduling.
Right.
We have to pivot because when requirements are in that high uncertainty state, constantly evolving again, think software development, R&D, market testing, the overhead of constantly updating a detailed 500-line critical path model every 3 days, it just becomes organizational waste.
You're planning things that you know are going to change before you even get to them.
Precisely. And that's where methods like Scrum or Kanban just excel. Their key characteristics are, frequent delivers of working product every few weeks and distributed planning.
So the team itself defines the detailed execution plan, but only for a very short cycle.
Right. Rather than relying on some top-down fixed master plan that was delivered months ago and is probably already wrong.
So the schedule here is less about a single fixed end date and more about a predictable rhythm, a rate of value delivery.
Exactly. It's all about rapid feedback loops. So instead of calculating float or monitoring buffers, they rely almost entirely on visual tools, on backlogs, and on a few specific charts to communicate progress.
The burn down and the burn up charts.
That's right. They use those to forecast based on observable actual performance.
So to just summarize this whole foundational part for the listener, if your project's requirements are stable and change is expensive, you have to use a predictive method like CPM.
You must.
But if change is cheap and highly likely, the overhead of CPM is waste, and you should be choosing an adaptive method.
And that choice sets the stage for literally everything else that follows.
Here's where it gets really interesting for me. If these adaptive teams are operating without a fixed critical path, without a rigid float calculation, how do they rigorously track progress? How do they manage stakeholder expectations and maintain accountability?
They do it with those visual metrics you mentioned, focused on deliverables and effort reduction. These charts are the heartbeat of an agile team.
And they communicate everything.
Everything. Progress, forecasts. They do it clearly to the team and to the stakeholders, and it minimizes the need for heavy documentation while maximizing transparency.
So let's start with the first one, the iteration burn-down chart. You call this the remaining view.
Yes. This chart is the foundation for tracking an agile sprint or iteration, which typically lasts, 2 to 4 weeks.
Right.
And it tracks the remaining effort, usually measured in ideal hours or task estimates, against the days of the iteration. The commitment is very simple. Drive the work down to 0 by the deadline.
And the visual analysis is incredibly revealing.
It is. Imagine a chart. The horizontal axis is the iteration days. The vertical is the remaining effort. First, you plot a planned effort line.
The ideal path.
The ideal path. If you committed to, say, 400 hours of work over a 9-day iteration, that planned line is just a straight downward slope from 400 on day 0, aiming right for 0 on day 9. That line is your commitment baseline.
Okay, now let's talk about the real world. That actual line, the remaining effort line, it can deviate wildly from that plan.
It often does.
So let's take a scenario. What if that actual line stays consistently above the planned line?
That immediately signals trouble. The team is falling behind their schedule target. If that actual line stays high, it means the rate of work completion is just slower than everyone expected.
So maybe by day 5, the plan says you should have 200 hours left.
But your actual line is still way up at 300 hours. That large gap tells you 2 things. First, the team probably isn't going to meet its iteration commitment.
Yeah, the second.
The initial estimates were likely too optimistic. The work is harder than they thought, or they've run into unexpected blockers.
The volatility of that actual line is also a key indicator, isn't it? What if the line stays flat for a few days and then just drops like a rock on the last day?
That high volatility suggests a critical flaw in the process. It usually means the team isn't breaking their work down into small enough pieces.
Or they're delaying integration.
Or they're delaying integration and testing until the very last moment. Work isn't truly done in small increments. It's being completed in these big, stressful batches right before the deadline.
Whereas a healthy burn-down chart.
A healthy chart should show small, consistent drops every single day. It reflects daily progress and incremental delivery.
But the chart can show good news, too. What if we see the remaining effort line drop below the planned effort line, especially early on?
That's a great sign. It means the team is likely ahead of schedule. Maybe the tasks were easier than they anticipated, or the team's capacity was higher than they thought.
So if you see a huge drop between, say, day 3 and day 5,
It means a significant chunk of work was completed and accepted really rapidly, and that provides this immediate high-fidelity feedback that allows the product owner to potentially pull more work into the sprint, or, more commonly, just start reprioritizing the backlog for the next iteration. It's powerful information.
Okay, now let's shift focus to the other big one, the burn-up chart. You call this the completed view
Yes, and this one tends to be a favorite among stakeholders.
because the line always goes up.
The line is always moving in the right direction. It focuses on value delivered. The burn-up chart shows completed work, and that's usually measured in story points done, rather than looking at remaining effort.
So the emphasis is entirely on what is finished and accepted.
It links progress directly to delivered value.
And there's a key governance rule here, which really aligns with that agile focus on a working product.
A very strict rule.
Story points only count when the feature or the story is 100% complete. It has to meet the definition of done.
That is non-negotiable. No partial credit for being 90% done. Done is a binary state. It is or it isn't.
So if we visualize this chart, we'd see a solid line tracking those story points done, moving upward against maybe a projected completion line.
Right. And if you see that solid line flatten out for 2 or 3 days, say around the middle of the iteration, it doesn't necessarily mean the team is idle.
What does it mean?
It often means the work is actively stalled. They're waiting on something. Critical external testing, a security review, integration with another system. The burn-up chart is brilliant at flagging where your value delivery bottlenecks are.
And these iteration level charts, they both tie into what is maybe the most strategic metric in all of Agile: velocity.
Velocity is absolutely crucial, not just for tracking, but for capacity planning and, frankly, for defending the team against scope creep.
So how is it defined?
It's simply the sum of story points that are completed and accepted within one iteration.
And by tracking this over time,
By tracking the average rate over multiple iterations, say the last 3 to 5, the team establishes a predictable, statistically sound rate of work delivery.
so velocity isn't just a number, it's the core defense against the business demanding, an unreasonable amount of scope in the next sprint.
It's a reality check, a data-driven one. If our team's average velocity is 30 points per sprint, we simply cannot commit to 50 points next sprint and expect to deliver reliably. It's not an opinion, it's a forecast based on historical fact.
And that average velocity is then applied directly to capacity planning for the future.
Yes, it allows the team to accurately estimate how much work they can realistically take on, which prevents that cycle of overcommitment and burnout that kills so many teams and destroys the reliability of their forecasts.
So velocity in these charts, they all feed directly into the longer-term high-level view. That's release planning. How is that structured, given how little detail you have so far out?
Release planning covers a much broader time horizon. We're talking 3 to 6 months across multiple iterations. The focus here is on high-level features and strategic epics, not granular day-to-day tasks.
And it's hierarchical, right, to ensure alignment.
Very hierarchical. You start at the top with the product vision. That's the ultimate goal, the strategic objective for the entire product.
And that vision then filters down.
It filters down into the product roadmap, which maps out those features over a longer timeline. The roadmap then drives the release plans, which establishes the specific iterations or sprints needed to deliver a chunk of functionality.
And only then do you get to the iteration plans, which schedule the actual feature development in detail.
That's the hierarchy. And the estimation breakdown reflects this perfectly, which is fascinating.
How so?
At the high level, features are delivered via user stories, and those stories are estimated in an abstract relative unit called story points.
Using techniques like planning poker.
Right, but when the team gets ready for the actual execution in an iteration plan, they break those stories down into concrete tasks. And those tasks are estimated in concrete hours.
So you shift from abstract story points, which measure size and complexity, to concrete hours, which measure effort.
That shift is essential for the day-to-day execution and resource allocation. One informs strategy, the other informs execution.
And finally, those releases themselves. They aren't all scheduled the same way, are they? They could be driven by different business priorities.
That's right. A release can be feature-driven, which means we release only when features X, Y, and Z are completely ready. It can be time-driven. We release every quarter, no matter what, to hit a market window.
And the third type?
Cost-driven. We release when the development budget runs out or hits a specific financial milestone. This flexibility means the scheduling rhythm is defined by the business objective, not just the development team's pace.
If we connect all this to the bigger picture, the best scheduling model in the world, whether it's the precision of critical chain or the fast feedback of agile.
It's utterly useless if the underlying data is unreliable, inconsistent, or unprotected.
So the governance around this schedule is what makes it a trusted source of truth.
It's the framework. It's everything.
This is the operational side of scheduling, the rules of the road that protect the integrity of your forecast. And that commitment has to start with the schedule management plan.
It does. The schedule management plan is the guiding document for the whole process. Think of it as the contract between the project manager, the team, and the organization.
Its purpose is to integrate all the scheduling efforts into the overall project management plan.
And it explicitly defines the how. The processes, the tools, the templates, the approach for creating, updating, and sharing the schedule model. It ensures consistency.
And it has to be integrated with everything else. It must align with the work breakdown structure, the WBS, to make sure every activity maps back to defined scope.
Guaranteed. And it must specify how you're going to measure performance. That means aligning the schedule with cost controls, using metrics like earned value management, EVM, and critically, earned schedule.
Let's pause on earned schedule, ES, for a second. It's a vital, but I think often overlooked, refinement on EVM.
It is. Traditional earned value calculates your schedule variance, your SV, as a dollar value. The problem is, once a project is past its planned due date, the Schedule Performance Index, the SPI, mathematically hits a ceiling of 1.0.
So it stops telling you how late you actually are.
The metric is effectively lying to you. It gives you this false sense of stability because you've technically earned all the value you could have earned by that point in time.
Even though you're still late.
Precisely. Earned schedule corrects this fatal flaw by using a time-based metric. Instead of asking, how much value have we earned, it asks, how much time should we have spent to earn this value? It replaces that dollar-based variance with a time-based variance. And this allows the performance metrics to accurately reflect delays even after the planned completion date, which gives you a far superior, more accurate forecast of the actual project completion time.
So integrating earned schedule is really a mark of a mature scheduling practice.
It really is.
Okay, so we have the management plan defining the process. But before we even build the model, we have to protect the raw data. That's the scheduled data management plan. This is basically your insurance policy.
It's all about business continuity and data integrity. And you must have your project scope, your WBS, and your resource definitions established before you can create this plan. If you don't, you have to stop and define them.
And this plan addresses how the raw data, the actual schedule file itself, is going to be maintained, accessed, and recovered.
That's right. And there are several areas that demand real rigor.
What are the key ones?
First, user access. You have to define roles and responsibilities. Who can make changes? Who can only report progress? Who has read-only access? Strict access control prevents accidental corruption of the file.
Makes sense. What's next?
Backup frequency. Is it daily? Is it weekly? This has to be based on the volatility and the criticality of the scheduled data. If you're reporting daily, you have to back up daily.
And retrieval capability is key, right?
Yeah.
Especially if you get into forensic analysis or a claims dispute.
Absolutely vital. Your data retrieval procedures must be established, and this is the key part, verified. You have to test that you can actually retrieve a previous schedule instance.
So you can reconstruct the timeline.
Exactly. You can prove when a change was implemented or defend against a claim. If you can't verify the retrieval, your backup is worthless. And then you have data retention policies, which are often driven by legal or audit requirements for how long you have to store that data after the project is closed.
And for global projects, those infrastructure risks are constant.
Oh, for sure. The plan needs rigorous risk management to address those infrastructure risks. Conflicts from global access across different time zones, which can corrupt files, backup replication failures, or even just planned maintenance that takes the system offline during a critical reporting period.
The goal is just simple availability.
Availability, accessibility, and recoverability, 200/47.
Okay, let's drill down into the structure of the schedule management plan itself. The source material lays out this detailed checklist of 12 core components.
This is the real governance structure. This is what transforms a simple list of tasks into a reliable forecasting model.
All right, number 1, scheduling approach.
This is where you define the approved methodology, CPM, critical chain, agile based on the project's needs and your organizational standards. The key is consistency.
Number 2, scheduling tool. This seems obvious.
It seems obvious, but selecting the right software is critical. It has to be compatible with your chosen approach and how you want to integrate data. Some tools are just better at integrating cost and resource data than others.
Okay. Number 3, schedule model creation plan.
This defines the development methodology. Who is building the initial schedule? How long will it take? And most importantly, how are you going to manage stakeholder participation?
So are the teams who do the work actually defining the task durations, or is it being imposed from the top down?
And the former is always better for buy-in and accuracy.
Number 4, schedule model ID.
Every schedule model needs a unique identifier. Simple as that. For tracking, for cataloging, it's vital for historical analysis across a whole portfolio of projects.
And number 5 gets even more granular. Schedule model instance.
This is a finer point of governance, but it's important. It's not just the model, but each snapshot, every saved, archived version of the schedule that needs a unique ID for auditing. When you publish a revised baseline, that instance has to be uniquely cataloged.
Got it. Number 6 is calendars and work periods.
This is the heartbeat of the project. You set the project's default calendar, your working days, your hours. But crucially, you also have to define resource-specific calendars.
Like an engineer who works 4 10-hour days.
Or a consultant who's only available on Tuesdays and Thursdays. But there's a big trade-off here. Using multiple calendars adds significant complexity and risk to the automated float calculations in the software.
So it could actually compromise the reliability of your critical path analysis.
It can. The advice is keep it simple if you can, but be accurate if you must.
Okay, number 7, update cycle and granularity. This one sounds bureaucratic, but I have a feeling it's a huge deal.
Oh, it's massive. This is where you balance that need for control against the reporting burden on the team. You have to set the frequency for status updates. Is it hourly for a system outage, weekly for an IT sprint, or monthly for long-term construction?
And that frequency is based on the project's volatility, its risk, its duration.
And this ties directly to granularity. The detail of your activities has to be optimized. Too much detail, the schedule is costly and unwieldy. Too little, and you lose control.
And there's a standard good practice here, a rule of thumb.
A very clear one. An activity's duration should typically be less than twice the update cycle.
So that rule is designed specifically to prevent something. The dreaded 99% complete syndrome.
That's it. We've all seen it.
Tell us more about that. It's the bane of every project manager's existence.
It happens when an activity is estimated to take, say, 6 weeks, but you only get a status update every week. For the first 5 weeks, the report comes back. 20%, 40, 60, 80, and then 99% complete. But the activity is still not finished.
And the scheduler has no real information about what went wrong.
None. The delay is only recognized when the task should have been 100% finished. It's too late. But if you limit that duration to 2 update cycles, for instance, a maximum of 2 weeks if you're updating weekly, the status has to be reported as either complete or late much, much sooner. It allows for immediate mitigation.
That's a great rule. Okay, number 8, coding structure.
This is all about making the data useful for analysis. You develop codes for things like phases, locations, responsible departments, and the link back to the WBS.
And the activity identifiers themselves have to be unique and separate from those codes.
Yes, for maximum reporting flexibility.
Number 9 is resource planning. This is what makes the schedule achievable.
Exactly. A resource-loaded schedule identifies your people, your equipment, your material needs, and it verifies their availability against calendars and required skill sets. This is what lets you generate usage curves, perform resource leveling, and accurately mitigate external impacts, like a weather delay.
Number 10, key performance indicators, or KPIs.
You have to define what success looks like up front. Use operational KPIs like activity starts and finishes, backlog metrics in Agile, or duration growth in predictive models. And these must include those crucial EVM and earned schedule indicators we talked about.
All right, two more. Number 11, master schedule model.
This is for organizational complexity. For massive projects, you need to structure the schedule as a master project with sub-projects linked together.
So by phase or by contractor.
By phase, contractor, delivery team, whatever makes sense. And you only link them at key delivery or acceptance points. This prevents the schedule from becoming one massive, unwieldy file that takes 10 minutes to load.
And finally, number 12, change control.
You have to plan for the inevitable. You use the configuration management plan to track changes, to mark affected activities, and to ensure that your baseline is protected. Changes have to be traceable and approved against that established baseline.
Okay, so moving from that management framework to the actual execution vision, creating the baseline schedule itself.
Yeah.
The schedule model can't just be a compliance document.
No, it has to be a dynamic tool that captures the team's actual execution vision.
And it has to be realistic and achievable.
It has to function both backward and forward. Looking backward, it has to support forensic scheduling analysis if litigation or claims come up.
So you can reconstruct the timeline.
And looking forward, it provides crucial lessons learned data for future projects. Ultimately, it defines the what the work, the who, what, and when, the resources and timing, and the sequence.
And to ensure that realism, the schedule has to be perfectly aligned with both scope and resources. Let's talk about that WBS connection first.
This is where scope creep is either prevented or enabled. Every single deliverable or work package from your work breakdown structure must be traceable to a single unique activity in the schedule.
So nothing gets missed and nothing extra gets added.
No scope gaps and no scope creep. This traceability is also your best friend in a claims defense because it proves every dollar spent was tied to a defined deliverable.
And resource verification is just as important. A schedule without confirmed resources is just a wish list.
It's a fantasy. The resource-loaded schedule must verify that your labor, equipment, and material are actually available when you need them. This means using structured resource IDs and attributes like organization, skill level, location, so you can do accurate resource leveling and reporting.
Without that verification, it's just a theoretical sequence, not an achievable plan.
Exactly.
Okay, let's get to the granular steps of actually creating that baseline. We start with the benchmarks. Milestones.
Milestones are your zero-duration, resource-free markers of progress. They are the non-negotiable benchmarks.
The start and finish of a project phase, a key sign-off, regulatory approval.
All of those. Every single project needs a start milestone and a finish milestone, at a minimum. And they have to include any milestones defined by the customer, the team, or other key stakeholders. They're usually the very first things you put into the schedule structure.
And then we get to the core of it, defining the project's activities. The standard has some very specific rules for what makes a well-defined activity. This is where accountability lives or dies.
These rules are essential. They're essential for timely progress reporting and for data integrity. First, activities should be defined by the team responsible for executing them, but critically, every single activity must have a single owner.
One person accountable for performance and progress reporting.
One person. Accountability cannot be split between two departments. If the task is approved design, one specific person must own that task and its completion date. No ambiguity.
That is a huge shift from the way a lot of places work, with that sort of collective, generalized responsibility.
It is. One name, one task.
Okay, second rule. The description has to be precise.
It should start with a verb, include a specific object, and use adjectives for clarity.
Give us a strong example. The contrast between a bad one and a good one.
Okay, a bad description. Design system. It's completely vague. That could take a day or it could take a year.
Right.
A good description. Finalize user interface wireframes for mobile payment gateway. It starts with a verb, finalize. It includes a specific object, wireframes for mobile payment gateway, and it limits the scope. The good example is unambiguous. It enables clear reporting and real accountability.
Okay, third rule, continuity. Work should proceed without interruption outside of non-working periods from the calendar. Why is this one so important?
Because if an activity is defined to take 10 days, and on day 3 it has to stop for 5 days because you're waiting on external data, the activity must be split at that natural break.
The schedule has to reflect reality.
The schedule must reflect the reality that install foundation piers stopped on Tuesday and will restart next Monday. If you don't split the activity, you lose all your forensic accuracy and your progress reporting gets skewed. The schedule must be a truthful model of execution.
And finally, duration. This brings us right back to that governance rule we talked about.
Yes, duration should typically be less than twice the update cycle. If you report weekly, the activity shouldn't be longer than 2 weeks.
And you said this is the single best defense against the 99% complete syndrome.
It creates a high-frequency feedback loop. If a task lasts, say, 14 days, and you update weekly, at that first status meeting, the team has to report either on track, which is roughly 50% complete, or trouble, which is less than 50% complete. There's just nowhere to hide delays.
And that ensures the project manager can mitigate problems before they start to impact the critical path.
Before they cascade. Exactly.
The only potential exception to this rule is something called a summary activity.
Right. These represent broad, continuous efforts, like boring a tunnel, or maybe a long lead procurement that you're only tracking by its final delivery date, not by granular progress every 3 days.
So the software might just auto-summarize these, showing only the start and finish dates and the total elapsed duration.
Yes, they're treated as a broad bucket of effort. You're tracking a vendor's work only by its agreed-upon start and delivery milestones. And that distinction between a detailed task, which needs that single owner and that short duration, and the summary activity, which is tracked only by its boundary points, that really clarifies why that strict WBS linkage is so crucial. It determines the level of granularity and rigor you need for any given piece of work.
This has been an incredibly rigorous journey through the world of modern project scheduling. I mean, we've covered the entire spectrum, from the sequence focus of CPM and critical chain relying on buffers and resource leveling,
all the way to the flexibility and the constant feedback loops of adaptive and agile scheduling, where we're measuring velocity and tracking work visually with burn down and burn up charts.
And we dedicated a lot of time to the essential role of governance. Because whether your project is predictive or adaptive, that schedule management plan and the data management plan are they're the non-negotiable foundations.
They ensure data integrity, they define accountability, and they protect the data through backups and strict access controls, which allows your forecasts to rely on facts, not just hope.
What's really fascinating here is that whether you're using a complex critical path calculation or a simple burn-down chart analysis, the underlying good practices, they really remain constant.
They do.
Achieving reliability means clear communication. It means defining clear accountability with a single owner for every activity. And it means protecting the integrity of your data through rigorous backup and retrieval procedures.
And this raises, I think, an important question for you, the listener, to consider. If your current project schedule has activities that don't meet these core rules, maybe they're lacking a single owner, or they have durations so long they extend past 2 or 3 reporting cycles, violating that key duration rule.
What ripple effect might that lack of clarity and control have on your project's reliability forecast?
Is your schedule a model of reality, or is it just a list of wishes?
Something for you to mull over or explore on your own. Thank you for joining us for this deep dive into mastering modern project scheduling.
Until next time. Welcome back to the deep dive. This is the space where we take really complex, often dense technical documentation.
The kind of stuff that governs these huge multi-billion-dollar projects.
Exactly.
Yeah.
And we try to synthesize it all into clear, strategic knowledge. This time, we are really getting into the world of project scheduling.
Yeah, and it's a topic where when most people hear project scheduling, they just instantly picture a simple Gantt chart.
A checklist, maybe.
A checklist, a few milestones.
Mm-hmm.
But the sources we've pulled today, and these are straight from advanced project management standards, they reveal that modern scheduling is just so much more than a simple timeline.
Oh, absolutely.
It's a specialized discipline.
Mm-hmm.
It involves these highly sophisticated methodologies, complex mathematical modeling, and I think most importantly, the strategic management of uncertainty.
It really is the strategic core of project execution. I mean, especially when you think about the volatility of resources, requirements that are always evolving, and just inherent project risks.
For sure.
Our listener is really looking for a comprehensive, clear, and, a quick grasp of this stuff. And our sources, they give us the whole blueprint. We're moving way beyond basic timelines here.
That's right.
We're getting into adaptive planning and high-tech model creation.
That's the mission today. We're going to synthesize the foundational concepts that govern how organizations manage time and resources at scale. We're covering the whole spectrum.
The entire thing.
From those environments where the plan is almost, fixed and predictable, all the way to these high uncertainty environments where you're just constantly adapting.
And we also need to get into the digital backbone.
Oh, yeah. The tools, the models, the things that make this kind of precision planning even possible in the first place.
Okay, let's unpack this. So let's start at the highest level, the biggest split. Because the nature of the work itself really dictates the whole planning approach. The way you'd schedule, say, building a bridge is just fundamentally different from how you'd schedule a brand new AI software product.
And that's the foundational split. That's the first decision, really. It's between predictive and adaptive approaches. And this choice is driven almost entirely by the inherent uncertainty of the project.
So it's the first critical strategic decision a manager has to make.
It is.
Okay, so on one side, the low uncertainty side, we've got predictive environments. The sources call this definable work. Can you break that down? What makes work definable?
Definable work is, it's characterized by having a scope that is generally known and really well understood right up front. The risks are manageable, you can quantify them.
Okay.
And the outcomes are largely foreseeable. You base it on past experience or established engineering practices.
So like classic project management.
Exactly. Think building construction where the blueprints are fixed, or, the consistent high-volume manufacturing of something standard like a new car model.
Right.
The destination is clear, the path is mostly paved, so the whole strategic emphasis is on comprehensive, thorough, upfront planning.
You spend the money early.
You invest heavily at the beginning to define every single activity, every duration, every resource, every dependency before major execution even begins. The cost of changing that plan later is it's astronomical.
I can see that. I mean, if you're building a skyscraper, you can't just change the foundation halfway through.
It would be catastrophic.
So the counterpoint to that must be the environment where change isn't just expected, it's required. And that's adaptive work, exploratory work.
Precisely. And these are the high uncertainty projects. The scope is inherently unstable, or maybe it's just unknown. The requirements might shift significantly based on, say, rapid customer feedback or new tech breakthroughs.
Like developing a new drug.
Developing a novel pharmaceutical, or creating a product in a market that's just emerging. In that kind of environment, trying to plan everything up front isn't just inefficient.
It's a waste of time.
It's actively wasteful, because your plan will inevitably be wrong within weeks.
So how does the adaptive approach solve for that instability?
The whole approach shifts. It moves from planning the solution to discovering the solution. It requires you to constantly leverage subject matter experts, your SMEs, and these highly flexible cross-functional teams.
Okay, so they're solving problems as they pop up.
Exactly. They solve them collaboratively as they arise. The planning becomes continuous, tactical, incremental, and is focused only on the most immediate chunk of work.
So the goalposts move.
The key metric totally shifts. It's not about schedule variance anymore. It's about delivering tangible value and having these rapid learning cycles.
Okay, that makes the strategic distinction really clear. If you're building a known thing, you plan predictably. If you're discovering a solution, you have to plan adaptively. But what about those huge, complex projects?
The messy ones in the middle.
Yeah, like a big utility infrastructure upgrade. Maybe 70% of it is known engineering, so it's predictive. But the rest, the integration and deployment parts, that's all new tech. That feels adaptive.
You need a bridge.
You need something to connect the known certainty with that evolving knowledge.
And that mechanism, that essential bridge, is called rolling wave planning, or RWP. And it's a tremendously effective iterative technique.
Why is it so effective?
Because it strategically manages risk by just acknowledging the reality of the situation. That information accuracy just degrades so rapidly the further out you look in the timeline.
Planning in waves. It's a pretty elegant way to manage your commitment. So how does the actual structure of it work? How does it organize the work over time?
Structurally, it's all about deferring detail until it's actually useful. So the near-term work, the next few weeks or maybe months, that gets planned in painstaking detail.
Every activity, every resource.
Every single thing is defined and estimated with super high confidence. But the future work, the stuff that's maybe 6, 12, 18 months away, that gets aggregated into these larger, less defined blocks.
And those are called planning packages.
Planning packages, exactly. And you only provide high-level aggregate estimates for those future packages.
Okay, so if I'm managing a 2-year project, my first 3 months might be defined by hundreds of tiny one-day tasks.
Right.
But months 15 through 24 might just be grouped under 5 big system integration and testing packages.
That's the idea.
But what stops those from just becoming, vague placeholders on a chart?
The rigor of the process. That's what prevents it. Detailed planning doesn't just happen randomly. It occurs at these regular, defined intervals. a planning wave that always comes before the execution wave.
So it's a cycle.
It's a cycle. As the project progresses, as you complete those detailed near-term activities, those high-level planning packages are systematically decomposed down into detailed activities.
And you're using the latest, most accurate information you have at that time.
The most accurate information available, yes.
So the key assumption baked into this is that your planning effort should match your informational certainty. You're only putting in the hard work of refining the plan when the info is available and trustworthy.
That is the core strategic benefit. By delaying that detailed planning commitment, RWP minimizes the cost of planning errors.
It seems like it actively cuts down on risk.
It does. You avoid spending hundreds of hours defining activities for month 18, only to have all those assumptions completely invalidated in month 6.
Okay, but how does this integrate with something really traditional, like the critical path method or CPM?
That's a great point. Even when you use RWP in a CPM environment, those planning packages, even though they're high level, they still have to include fixed cost and resource estimates when they're first set into the project baseline.
Wait, hold on. If the activities aren't even fully defined yet, how can the costs and resources be fixed in the baseline?
They're fixed based on historical data and the scope defined at that high level. It's an estimate, but it's an informed one.
And what's the point of that?
It ensures that even the high-level plan maintains financial and resource integrity for your stakeholders. You've essentially locked down the budget and the resource envelope for Phase 3.
Which is still a planning package.
Right. Even if the specific sequence of tasks within that phase hasn't been finalized yet. And this is crucial for managing stakeholders and securing funding.
So you've locked down the budget. Even if the detailed method hasn't been picked, that's a really smart way to manage commitment. But what if, say, a regulatory change suddenly means one of those packages needs double the resources? What happens to the baseline then?
That's where your change management protocols kick in. A major change like that, one that invalidates a baseline assumption, it requires a formal change request.
And maybe a whole new baseline.
Potentially, yes. But the flexibility is in the decomposition. When you finally open that planning package up in month 12, you use the approved resource and cost ceiling, but you have the flexibility to schedule the activities inside it in the most optimal way possible with the new granular information you now have.
The crucial takeaway here for you, the listener, really seems to be its versatility then.
Absolutely. The sources are explicit about this. RWP is applicable to both predictive environments. When you're managing long-term, fixed scope and adaptive environments, when you're managing the uncertain evolution of requirements.
It's the perfect tool for managing evolving knowledge.
No matter what's causing that evolution.
Okay, that sets the stage beautifully for the more specialized tools. We've established the when predictive versus adaptive and the how, with RWP bridging the knowledge gap. But now we need to talk about specific high-rigor techniques that are really tailored to certain industries or certain types of work.
Right. We're moving from the philosophy of planning to the nuts and bolts of execution and optimization.
Here's where it gets really interesting. Let's start with a methodology that adds a spatial element. Location-based scheduling, or LBS. You mentioned this is big in construction. Why is managing physical locations so critical to the schedule?
LBS is foundational in construction because it recognizes that space is a finite, critical resource. Its genius is in optimizing resource utilization across multiple sequential work fronts.
So it's not just about time.
No. Traditional schedules often focus only on time and dependencies, but LBS brings in that spatial dimension. It shows both the physical location like floor numbers in a building or mile markers on a highway and the time of activities.
I'm not sure I follow. Why is the spatial element a scheduling constraint? Can't you have two different crews working in the same area?
Not if they disrupt each other, and disruption is waste. If you're pouring concrete on floor 12, the pipe fitting crew cannot be directly below you on floor 11 trying to hoist materials. LBS ensures continuous task progression.
So no stops and starts.
Exactly. You want to minimize stops and starts for specialized crews or expensive equipment. When a crew has to halt, you're paying for wasted resource time. LBS aims for a continuous, steady flow of labor across the available work locations.
Can you use that analogy from the source material to walk us through this? The one about the highway?
Sure. So imagine you're tracking two different types of work, let's say excavation and installation. And you're doing this along a single linear project, like a 10-mile stretch of highway that's divided into units, M1 through M10.
Okay.
The LBS chart plots time on the vertical axis and location on the horizontal axis. The work progression of the excavation crew gets plotted as a line, and the installation crew is another line.
And the goal?
The goal of LBS is to make sure that those lines maintain a consistent crew velocity and, critically, that the lines never, ever intersect.
An intersection means a collision. It means the pipe crew showed up to mile marker 5 before the foundation crew was even finished.
A physical clash and downtime. Exactly. So the technique is used heavily in horizontal construction, things like highways and pipelines, and vertical construction, like skyscrapers or standardized housing developments.
It's all about managing that linear flow of resources across the physical space.
Focusing on continuity and preventing physical resource collisions. And that optimization is vital for these huge capital projects, because if you can reduce idle time for specialized, expensive equipment, you drive down the whole project cost and duration.
Okay, so moving from the physical space of construction to the flow of the work itself, let's talk about the philosophy of lean and pull-based methods. These come out of manufacturing, but they're critical in adaptive environments too.
They are. And these methods are fundamentally about flow, efficiency, and eliminating waste. And waste is defined as any activity that consumes resources but doesn't add any value.
So let's start with on-demand scheduling. What's the core mechanism here? How is it different from a traditional push-based system?
On-demand scheduling is the classic pull-based approach. It's derived straight from lean manufacturing. Traditional scheduling pushes work downstream based on some upfront estimate of when it should start.
Right.
On-demand pulls work only when capacity is actually available. The mechanism is really simple. It rigorously limits work in progress, or WIP.
So if the team's capacity is 10 units of work, you never let 15 units into the in-progress queue?
You never do. By limiting that WIP, you achieve a balance between the demand for work and the actual throughput of delivery.
It's a just-in-time concept.
The ultimate just-in-time concept applied to any production flow, whether it's making cars or writing software. The goal, of course, is the rapid reduction of bottlenecks.
Which act like dams in the flow.
Exactly. And it minimizes the waste that's associated with partially completed work just sitting idle.
And that leads into the bigger idea of lean scheduling. If on-demand focuses on when to pull work, lean scheduling seems to be about applying those broader lean principles across the whole planning process.
It is. And this methodology relies heavily on these collaborative events called pull planning sessions. This isn't the project manager sitting in a room and dictating a schedule.
This is the team defining it.
This is the project team defining it together. These sessions bring together everyone who's needed, the electricians, the plumbers, the software testers, to collaboratively define the milestones, the activities, and most importantly, the necessary handoffs between tasks.
So it's planning backwards.
It's planning done from the desired execution backwards, and it focuses intensely on coordinating all the inputs.
The sources also break lean scheduling down into a 3-level hierarchy. This seems really important for adding structure to what could otherwise be a pretty chaotic flow.
The hierarchy ensures alignment from top to bottom. At the highest level, you have master scheduling. This just locks down the key milestones and the boundaries for the whole project.
And you have.
Below that is phase scheduling. This takes the work within a specific phase, say the structural phase of a building or the beta release of software, and it maps it into a detailed phase plan using those collaborative pull sessions.
And then the day-to-day.
And finally, the most granular level is look-ahead planning. This is your short-term, typically weekly work plan that guides the teams, often visualized on something like a Kanban board.
So it's a tiered approach. You get strategic alignment, but you allow for maximum tactical flexibility on the ground.
That's the idea.
Okay, we've covered LBS for space, lean for flow. Let's go back to something more visual and production-focused. What about projects that have a long duration but involve deeply repetitive tasks?
Like manufacturing, assembly lines.
Or installing the same components across hundreds of identical units.
For those highly repetitive scenarios, we use a technique called the line of balance, or LOB.
Okay, the distinction from LBS here feels really important. They sound similar.
It's critical. While LBS focuses on location progression and avoiding physical clashes,
Right.
LOB focuses intensely on production rate consistency, or crew velocity consistency.
Okay, I need you to break that down a little more because they both use lines on a graph.
They're related, but the focus is different. LOB is used specifically for processes where the task is long duration and repeated like manufacturing 50 identical turbines. The LOB chart usually plots cumulative production quantity against time.
And the goal is to track the actual rate against the planned rate.
Precisely. The line of balance is your planned, ideal production rate. If your actual production line falls below that ideal line, You know immediately that you have a bottleneck or a loss of velocity in that repetitive cycle.
So if LBS makes sure the crews don't physically crash into each other on a highway,
Yeah.
LOB makes sure that the team installing window frames finishes floor 10 at the exact same rate they finished floor 5.
It ensures a consistent flow rate of output. That's the key. By visualizing the rate of production as a single line, schedulers can quickly track performance and proactively fix those bottlenecks. It just goes to show that modern scheduling is intensely visual and analytical, far beyond just managing a sequence of tasks.
Speaking of data and visualization, let's pivot to the really cutting-edge stuff, technology and future trends. The areas where scheduling is getting a massive digital upgrade.
Yeah, the convergence of data science and project management is creating capabilities we couldn't have even imagined a decade ago. And the first major trend the sources highlight is the use of intelligent systems.
That sounds like we're moving from descriptive scheduling, telling us what will happen, to prescriptive scheduling, telling us what should happen.
That's a great way to put it.
What are the mechanisms described here?
It's the application of machine learning, or predictive analytics, to the scheduling process. The major benefit is the system's ability to learn not just from the progress of the current project, but crucially, from vast historical data from other projects.
Both successes and failures.
Both. The system can identify patterns that human schedulers, frankly, often miss.
How is that historical data practically feed into a prediction?
A key mechanism is using advanced simulations, specifically Monte Carlo analysis, but powered by all those historical actuals.
So instead of a single guess.
Right. Instead of relying on a single deterministic estimate like this task takes 10 days, the intelligence system uses the distribution of actual durations from hundreds of similar past tasks to run thousands of schedule simulations.
And then it optimizes based on that.
It optimizes sequencing and contingency planning based on the statistical probabilities of success. This allows the system to proactively identify the highest risk sequence paths and even suggest alternatives, reducing the overall exposure to schedule delay.
That is fascinating. So the schedule won't just reflect reality, it will start proactively shaping the most probable successful path forward. It's like a highly informed risk advisor.
It is. Then, specifically for construction, we have to talk about the integration framework of building information modeling, or BIM. This is so much more than a 3D design tool.
Right, we've heard of 3D models. But BIM takes it to a new level.
A new level of dimensional integration, yeah. BIM combines the 3D design geometry with the scheduling data, and that creates the 4D dimension time.
And then it adds costs.
Then it integrates cost data, linking schedule elements to budget lines, which creates the 5D dimension.
So what's the value of integrating geometry, time, and budget into one model?
The value is that the project team can engage in what's known as virtual construction and sequence testing.
So before a single shovel hits the ground, they can run the whole construction sequence digitally. What is the single biggest logistical or financial problem that this kind of modeling helps eliminate in practice?
Oh, the elimination of clash detection errors is massive. Without 4D, you might not realize that the crane needed to install the heavy HVAC equipment is blocking the only access road for the cement trucks during the critical foundation pour.
But in the virtual model?
In the virtual model, that clash lights up instantly. By running the sequence and visualizing it, seeing how long the crane is there, where the laydown yard needs to be, the team minimizes equipment delays, material wastage, and significantly reduces claims due to these unforeseen conflicts.
So testing the sequence virtually saves real money.
It massively reduces costs and contractual disputes.
We've covered the strategies and the techniques. Now let's talk about how all of the structured data actually gets processed and managed. There's a really specific, crucial distinction made between the scheduling tool and the schedule model. They sound interchangeable, but they're not.
No, and this distinction is absolutely foundational to maintaining rigor. If you think of a high-performance race car, the tool is the engine and the chassis, the physical machine.
Correct.
And the model is the highly tuned data set, the specific telemetry, fuel mix, and race strategy that's designed for that one specific track.
I like that analogy. So let's start with the scheduling tool. The engine. Conceptually, what is this software application?
It is the platform. It's the software application that contains all the algorithms, the components, the rules that are necessary for managing this complex interplay of project elements, activities, dependencies, resources. It's the powerhouse that does the intricate math for techniques like the critical path method.
And focusing on its core functionality, what are the highly technical capabilities this tool has to have for a scheduler?
It needs to be precise, particularly around managing dependencies and resources. First, defining relationship types. Not just finish to start, but also finish to finish, start to start, and start to finish.
Okay.
Second, it has to allow for adding supplemental data accurately, lags, which are purposeful delays, and leads, which allow overlap, and applying various constraints, like must finish by.
You stressed earlier that logic should drive the schedule, not a bunch of constraints. What's the practical difference in the tool between an activity sequenced by logic and one sequenced by constraint?
Logic, like a finish-to-start dependency, reflects the physical or logical reality of the work. If task A is pour concrete, task B, remove forms, cannot logically start before task A is done, plus some curing time.
Right, that's a physical law.
It is. A constraint, on the other hand, like task A must finish on Friday, imposes an arbitrary date. If you rely on constraints to just push tasks into slots you want, you lose the model's ability to dynamically recalculate when something shifts.
So if an earlier task is delayed,
The constraint stays fixed, creating an unachievable plan without any logical warning.
that sounds like a schedule that looks good on paper but just breaks the second reality hits.
That's exactly what it is. The tool also has to be hyper-capable in resource management. It has to let schedulers apply specific resource quantities and skill sets, assign priority levels to those resources.
And crucially, do what you called availability-based adjustments.
Yes.
Okay, let's get technical here. Can you explain the difference between resource leveling and resource-limited scheduling and how the tool handles both?
Resource management is vital for the model's integrity. Resource leveling is the process the tool uses to smooth out resource usage over time. It often moves tasks within their available float to avoid sharp peaks and troughs in demand.
So if an engineer is overbooked in April,
If the HVAC engineer is 120% utilized in April, the tool will try to shift some of their non-critical work into May, provided the overall schedule duration doesn't extend.
okay, and resource-limited?
Resource-limited scheduling happens when the resource is absolutely scarce. If the critical turbine installation team is only available for 10 days, but the task requires 15, the tool must extend the task duration or delay its start until that resource is available again.
And it calculates the impact on the finish date?
It calculates the precise impact of that scarcity on the critical path, potentially delaying the final project date. It's not just arranging boxes, it's figuring out if the right person is available at the right time and calculating the exact time impact if they're not.
So finally, the tool is for performance tracking.
Absolutely. It has to capture the original schedule baseline, the approved, fixed version record, actual progress, and, critically, allow for what-if analyses.
So you can run scenarios.
You can run scenarios. What if
Yeah.
we delay this shipment by 3 weeks? What if we add a second crew and see the resulting finish date without corrupting your baseline? It's constantly comparing schedule instances to find variances and trends.
That brings us to the schedule model, the data blueprint. If the tool is the engine, the model is the highly structured data set that the engine operates on.
The model is the management artifact created by the project team. It's the specific blueprint you create by inputting your project-specific data activities, durations, resources, dependencies into the tool.
And it's independent of the approach.
Conceptually independent, yes. Whether you're using LBS flow logic or CPM sequence logic, the schedule model is the specific representation of your project's reality.
And what's the main purpose of creating this rigorous project-specific model?
Its primary function is to be a simulation engine. It lets the team simulate scenarios to predict completion dates and milestones across a whole probability spectrum. But its role is also deeply managerial.
How so?
It's the main support mechanism for communication, for setting expectations, and for justifying changes to stakeholders. If someone asks, why is the deadline moving? The model gives you the simulated data-backed answer.
This all sounds completely dependent on data quality. Garbage in, garbage out.
Oh, 100%. The rigor has to start at the foundation. The model has to be rooted firmly in the work breakdown structure, the WBS and the WBS dictionary. This makes sure every piece of scope is accounted for.
And the activities themselves have to be defined in a specific way.
A very specific way. They have to be unique, always starting with a verb, and including specific objects and adjectives.
Give me an example. The right way versus the lazy way.
The lazy way is just design. The rigorous way, the one that allows for accurate estimation and tracking, is develop the final structural foundation plans.
The verb develop, the object structural foundation plans. It's specific.
It eliminates any confusion about scope boundaries.
You also mentioned sequencing rigor. Let's go deeper on the importance of logical relationships over constraints.
Yes. The activities have to be sequenced with logical relationships that reflect mandatory, discretionary, or external dependencies.
What's the difference?
A mandatory dependency is based on physical law. You must cure the concrete before you remove the forms. A discretionary dependency is based on best practice management, prefers the QA review to happen before the client demo.
And external.
An external dependency is outside the team's control, like waiting for a regulatory approval. Schedulers have to identify these specific types of logic because, as we said, using too many constraints just invalidates the model's predictive power. The schedule should breathe based on the work, not be choked by arbitrary dates.
And finally, the duration estimates. They can't just be a gut feeling.
Not at all. They have to be calculated methodically, taking into account available resource quantities, the skills and productivity of the assigned resources, and ideally, using historical data from similar projects.
It's a dynamic forecast.
A time-based forecast that has to respond dynamically to progress, updates, and changes.
So the model is always recalculating, always projecting the future, which leads us to the final step.
Yeah.
How do we communicate the output of this incredibly complex system?
That's where schedule model instances and presentations come in. And we need to define those two terms carefully because they do different things.
Let's start with the schedule model instance. What is that?
An instance is just a digital snapshot. It's the result of running the scheduling calculation on the model data at a specific moment in time.
So it could be a baseline?
It could be the original baseline, or an update based on new progress, or the outcome of a what-if scenario. They are the fixed, analytical versions of the schedule that we use for comparison.
And the schedule presentations are the visuals we generate from those instances, right? Tailored for the audience.
Precisely. The goal of the presentations is communication. The project manager might need a resource-limited schedule instance showing the latest possible completion date, but the executive sponsor might only need a master milestone schedule presentation showing the key delivery dates.
So bar charts, network diagrams.
All that. Bar charts, network diagrams, resource profiles showing peaks, cost reports, and high-level milestone schedules.
And for adaptive work, we have to include the Agile-specific visuals.
Yes, for adaptive projects, the presentations also include things like burn charts, which track work completed against time, and Kanban boards, which visualize the flow of work. But regardless of the method, the purpose is the same. Support analysis, facilitate decision-making, and ensure crystal-clear communication.
Okay, so if the tool calculates both an early start and a late start date for every single task, what is the strategic importance of communicating the difference between those two dates to the team?
That difference is the total float, and it is strategically vital. Total float is the amount of time and activity can be delayed without delaying the project's final finish date. Communicating that shows team members where they have buffer and where they are truly on the critical path.
And there's another kind of float.
Equally important is free float, which is the amount of time and activity can be delayed without delaying the early start of its immediate successor. Sharing this lets teams use that buffer for resource leveling or contingency as long as they don't impact the next team downstream.
We've touched on...
Correct. You shift from a fixed activity sequence to an iteration-based schedule. The structure is defined by these fixed-length pine boxes, usually 1 to 4 weeks long, called iterations or sprints.
And those iterations are the containers for the work.
They're the primary container, ensuring a regular rhythm of planning, executing, and reviewing.
And where does the work come from, and how is it prioritized before it even gets into an iteration?
The work starts in the backlog. The items in the backlog, user stories, features, identified by IDs like J, K, L, M, are prioritized using a strategic framework, high, medium, low priority, based on the value they deliver.
And they also have an effort estimate called story points.
Yes.
Story points are the currency of effort in Agile, but they're relative, not absolute units of time like days. So how do those translate into a predictable schedule for capacity planning?
That translation happens through a metric called velocity. Velocity is the key scheduling metric in Agile. It measures the average number of story points a team successfully completes and delivers as done working product during one iteration.
So if a team consistently completes 20 story points every 2 weeks,
their velocity is 20, and that metric is then used for capacity planning. The team knows they can commit to roughly 20 points of work in the next iteration.
That seems much more empirical than estimating a task duration 5 months from now. Velocity is based on the team's demonstrated actual throughput.
It's entirely empirical and dynamic. The scheduling model, in this case, tracks the total effort left in the backlog, say 300 total story points, and divides it by the team's current velocity of 20.
And that gives you a forecast.
It gives stakeholders a data-driven forecast of how many iterations are needed to complete the current scope. This is often visualized on a burn-down chart, tracking the effort remaining over time.
So if we look at a typical iteration, how does a high-priority item move through that process?
Okay, take a high-priority item, feature J, estimated at 17 story points. If the team's velocity allows, they pull feature J into iteration 1 during their planning session. Their commitment is to complete that work within the fixed duration of that iteration.
And as they work on it.
As the iteration progresses, the state of the work moves from backlog to in progress and finally to done, which means it meets their definition of done and is potentially shippable.
What happens if the team finishes an iteration but the backlog is still full, which seems common in exploratory work?
That's the perpetual state of adaptive work. The planning is continuous. If they didn't finish feature M in iteration 2, it goes back to the backlog, gets re-estimated if needed, and is immediately reprioritized for the next iteration.
So the model is always tracking capacity.
Constantly.
Eh.
And backlog items are continually reprioritized to make sure the highest value features are always tackled first. The strategic implication is a focus on maximizing value flow over just meeting a single final deadline.
So adaptive scheduling isn't about forecasting one date 18 months out. It's about maximizing value delivery every 2 to 4 weeks and providing a continuous high-quality forecast based on measured performance. This has been a tremendously comprehensive view. We've covered a vast technical landscape. To bring it all together, let's just recap the key transitions we covered. We moved from that philosophical split between defining known work,
The predictive approach for things like construction,
and exploring work, the adaptive approach you need for high uncertainty, things like software development.
and critically, we saw how rolling wave planning provides that essential flexibility, letting project teams apply more detail only when the information accuracy actually warrants it.
That strategy of delaying commitment.
It minimizes the cost of planning errors.
Yeah.
It's just a powerful tool for managing dynamic knowledge, whatever the project type.
Then we shifted into the sheer technical rigor that's required. We learned that effective scheduling relies on picking the right specialized methodology like location-based scheduling for optimizing resource flow in a physical space.
Or lean and on-demand methods for maximizing value flow and minimizing waste.
And all of this is built on a robust scheduling tool and the schedule model, the data blueprint. The emphasis here always has to be on data rigor.
Always. Making sure the WBS is the foundation. Activities are defined clearly with verbs and objects, and that logical dependencies, mandatory, discretionary, external, are what drive the sequence, not arbitrary constraints.
Those steps are mandatory to get accurate, dynamic forecasts.
Whether that forecast uses critical path method or agile velocity. And it's what enables meaningful communication with your stakeholders.
So what does this all mean?
It means that modern project scheduling is less of an administrative task and much more of an applied modeling science. It's about creating a dynamic digital twin of reality, optimizing resource flow, and managing informational uncertainty using data that, if you handle it correctly, is self-correcting.
The choice of methodology determines the path.
The choice of CPM, LBS, lean, or agile determines the path. But it's the quality of the schedule model, your data blueprint, that determines the integrity and accuracy of the whole journey.
And that brings us right back to the cutting edge. Intelligent systems. We discussed how machine learning can learn from current progress, ingest historical data from other projects, and then use that knowledge, powered by simulations like Monte Carlo, to proactively optimize the sequence and develop better contingency planning before a human scheduler even sees the problem.
That power forces a fundamental reevaluation of the human role in all this. If the tools we build, the scheduling tools, become powerful enough to statistically predict the future path of the project better than we can.
And if that data model becomes the single source of truth,
the most reliable source for optimization and resource allocation, then we have to ask a pretty profound question. Is the schedule model becoming self-aware? Is the primary role of the human scheduler evolving from detailed task planner to architect of the data system and steward of a machine intelligence that generates the optimal path?
That's something for you to mull over as you navigate the complexity and the future of project management.
Welcome back to the deep dive. You know, I think anyone who's ever managed a project, big or small, gets stuck in this really uncomfortable spot.
Mm-hmm.
On one hand, you absolutely need some kind of plan, some structure to guide a really complex effort.
Of course.
But on the other hand,
Yeah.
you have this paralyzing fear, of over-planning.
Yeah.
Spending months crafting this perfect, rigid blueprint that you just know is going to crumble.
The second it makes contact with reality.
Exactly. The moment that first change request comes in, the whole thing just falls apart.
That tension, that's really the central struggle of modern project management, isn't it? The world just moves too fast.
Yeah.
And the complexity is just too high for that. Let's call it the traditional model.
Yeah.
The one where you define every single thing up front, get everyone to sign off in blood on the requirements, and then, just execute rigidly for a year.
And hope for the best.
And hope for the best, because the minute you actually start building something, you learn something new, it's inevitable. And if your entire project structure can't handle that new learning, well, you've basically wasted that entire initial investment.
Exactly. And that's really what our source material today is all about.
Yeah.
It's a masterful guide to what we call adaptive project management.
Right.
It shows us how these modern frameworks, how they balance that agility with the structure you actually need.
Right.
We're talking about avoiding that classic 6-month planning trap. And the key seems to be distributing that planning effort across the entire project timeline.
It's a complete shift in philosophy. So our mission today is to really pull apart the core mechanics of these adaptive life cycles. We're going to show you how things like short build cycles, frequent deliveries, and this is key measuring interim benefits, not just checking off tasks, are used to manage that complexity.
Yeah.
We'll dive deep into the specific rhythms of an iteration, the tools people use for tracking progress, and the philosophical differences between frameworks you've probably heard of, like Scrum and Kanban.
So let's start right there with that fundamental idea, the planning philosophy itself. If traditional predictive planning says, plan big once, then execute strictly, what is the agile counter-philosophy?
The agile counter-philosophy, it really boils down to a move toward distributed planning.
Distributed planning.
Yeah, it completely decentralizes that planning function. So instead of, say, a handful of senior managers spending 6 months locked in a room designing the perfect plan.
The master plan.
The master plan, right? Instead of that, planning becomes this ongoing collaborative effort. It's shared by the entire team and even stakeholders across the entire life cycle of the project. It's not a phase at the beginning, it's a constant activity.
That sounds great in theory. You get more people involved, you get more continuous feedback. But in your experience, where do teams really fail when they try to adopt this? Is it like the temptation to just fall back on what they know, that detailed over-planning?
That's part of it, for sure.
Or is it more a fear of appearing chaotic to stakeholders who are used to seeing a big, thick document?
I think it's often the latter. The anxiety really comes from stakeholders demanding predictability. They want to know, when will it be done? What will I get? And a 500-page Gantt chart gives them a false feeling of security.
Right.
But the key goal of adaptive planning is to achieve this critical balancing act. You need sufficient upfront planning to minimize the most obvious rework, to get started in the right direction.
Just enough.
Just enough, without falling into that trap of detailed overplanning. And overplanning isn't just inefficient. I'd argue it's actually toxic to agility because it creates this immense sense of sunk cost and bureaucracy. People become emotionally and politically attached to the plan, and that makes them incredibly resistant to necessary changes, even when the evidence is staring them in the face.
I find that distinction you just made, the difference between minimizing rework and eliminating rework, to be incredibly illuminating. It's an admission, really. It accepts that in any complex environment, some discovery, some correction, it's just inevitable. You can't plan it away. So we're just planning enough to stabilize that first step.
Precisely. And to decide what sufficient planning is, teams have to focus only on the immediate horizon. They don't try to plan the whole year.
Okay.
They'll plan in detail for maybe the next 2 weeks, and they'll plan at a very high level for maybe the next 3 months. Anything beyond that horizon remains intentionally vague. It's a known unknown.
It sounds a bit like the difference between, say, writing a novel versus having a conversational debate.
That's a great analogy.
For the novel, that's predictive. You need a detailed outline, you need to know the ending. But for a debate, that's adaptive. You need to know your topic, your key arguments, but the actual flow, the back and forth, that's decided moment to moment based on what the other person says.
Exactly. And think about the cost of error in those two scenarios.
Oh, yeah.
If you just plan your next conversational turn and it doesn't really land, you can recover instantly in your next sentence.
Right, you just pivot.
You pivot. But if you've planned out an entire 400-page novel and you realize on page 300 that a core character choice you made on page 10 was fundamentally wrong,
You've lost everything. It's a catastrophic failure.
you might have to scrap the whole thing. And that logic leads directly to the core Agile focus, which is value over activity.
Okay, unpack that. Value over activity.
In a lot of predictive methods, success is often measured by, well, by task completion. The question is, did we finish writing the documentation, or is the database schema built?
Checking boxes.
It's just checking boxes. In adaptive methods, the focus shifts entirely to delivering short build cycles, frequent deliveries, and realizing interim benefits. The question is never, are we busy? It's, did we deliver something that works?
Can you give us a really tangible example of an interim benefit? Because I think when people hear value, they often only think of the final finished product.
Sure. Let's imagine you're building a complex financial application. The whole project is slated to be a year long. A traditional project would deliver the entire massive platform at the end of that year. Nothing before then.
The big reveal.
The big reveal. An adaptive project, on the other hand, might deliver something in its very first 2-week cycle. Maybe it's just a functional login page and a user profile management screen.
Okay.
That is an interim benefit. It has immediate demonstrable value. Even if users can't process payments yet, they can sign up. They can manage their basic details. They can start interacting with the system. That is a concrete, potentially shippable chunk of value delivered in week 2, not month 12.
Right. And you get feedback on it immediately. So why is this focus on short cycles inherently a better strategy for risk mitigation?
It all comes down to the feedback loop. Think of risk like investment volatility.
Yep.
If you limit the duration of any single commitment to, say, a 2 or 4 week time box, you are fundamentally limiting the amount of capital, time, effort, money that can be potentially wasted if your understanding of the requirements turns out to be wrong.
Because you're only betting 2 weeks worth of work.
Exactly. If a team works for 12 months in a silo, in a vacuum, and then they finally unveil a product that completely misses the mark with customers, that is 12 months of sunk cost.
And at that point, the risk has fully materialized.
Yeah.
It's no longer a risk. It's a failure.
It's a failure.
Right.
But if you deliver a working login page after 2 weeks and the stakeholders immediately say, wait a minute, we absolutely need 2-factor authentication, and by the way, the branding is all wrong, you haven't wasted 12 months perfecting and polishing the wrong thing. You've wasted 2 weeks, which isn't really a waste, it's learning. You pivot, you adjust the backlog, and the very next cycle is better aligned with what's needed.
So the shorter the cycle, the faster you get that concrete, real-world feedback.
And that allows you to course correct, to adjust the scope, and to ensure that all the subsequent work is truly aligned with the current evolving needs of the business or the user. I mean, that is the very definition of managing complexity through continuous learning.
That makes perfect sense.
Right.
But that kind of dynamic, learning as you go approach,
Yeah.
it needs a really robust structure to keep it from just dissolving into chaos.
Absolutely.
And this is where the adaptive life cycle comes in, which our source material maps out beautifully. It's broken down into 5 continuous phases. This is the rhythm, the heartbeat that's required to maintain both agility and structure at the same time.
Yes.
So let's map out that flow for everyone. Let's start with the highest level view, the very beginning of the process.
Okay, so we start with phase 1, the project planning meeting. This is really the one significant upfront meeting where we set the stage for everything that follows.
Kickoff.
Kind of the kickoff, yeah. The main goal here is to establish the release goals for the overall project. And I want to be really clear. This is not about creating a detailed Gantt chart.
Right.
It's about defining the major milestones and the overarching scope that's necessary to deliver the primary value proposition. We're basically defining the North Star for the project. Where are we ultimately trying to go?
And the artifact, the thing that comes out of this session, is absolutely crucial.
It's the foundation. This meeting generates the product backlog. This document becomes the single source of truth for the entire project.
Okay, so what is it exactly?
It's the definitive, prioritized master list of all the features, all the user stories, all the requirements that we think we need to build for the entire project.
The key word there being think.
The key word is think. It's so important to remember that it's high level and it's intentionally flexible. It's a living document that we fully expect to evolve as we learn more.
So the product backlog is like this flexible giant wish list, and is prioritized by business value. Once you have that established, how do you narrow that massive list down into something a team can actually work on right now?
That brings us right into phase 2, iteration planning. This happens just before the next work cycle or iteration begins. The goal here is focused entirely on the immediate future.
The next 2 weeks, for example.
Exactly. The team starts by collaboratively reviewing the product backlog, but they're only looking at the very top, the highest priority items that the product owner has put there.
And this involves the team pulling the work, not having it pushed onto them, which is a really key agile principle, right?
It is. It's fundamental. The people doing the work are the ones who decide what they can take on. So the team examines those high priority items, and then they perform the second crucial action, which is to estimate the iteration workload.
This is the commitment step.
This is the commitment. This is where they say, this is what we can do. They use various techniques, often collaborative methods like planning poker, to gauge how much effort they can realistically complete within that upcoming time box.
And they're not estimating in hours, usually.
Right. They're often measuring it in abstract units like story points. It's not just about estimating effort. It's about the team establishing its own sustainable pace or velocity.
Let's pause on planning poker for just a second, because I think it's a fantastic example of that distributed planning idea in action. Why is it better for the whole team to estimate together using these abstract points instead of, say, one senior architect just setting the schedule?
Well, the simple answer is that the team doing the work owns the estimate. They're the ones closest to the actual complexity. Using relative sizing, or story points, encourages a discussion about complexity and risk, not just time.
So it's not, this will take 16 hours.
No, this is more complex than that. If one story is estimated at 5 points and another is 8 points, the team is collectively saying that the 8-point story is roughly 60% more complex than the 5-point story, regardless of how many hours any single person thinks it'll take.
And the voting process is interesting, too.
Yeah, the entire team votes, often anonymously with cards, which is critical because it prevents cognitive bias. It stops junior members from just deferring to whatever a senior developer says. If the estimates come out wildly different, say one person says 3 and another says 13, that's not a problem. That's a gift.
A gift. How so?
It means there's a misunderstanding. It forces a critical discussion. Why did you think this was so simple? Why did you think this was so complex? And through that conversation, you uncover hidden complexities or unstated assumptions.
That discussion is the real value, then. It forces everyone to get on the same page about what done actually means for that specific item.
Precisely. And the hard output of this whole planning and commitment meeting.
What do you walk out with?
You walk out with the iteration backlog. This is a small, rigid subset of that larger, flexible product backlog. It contains only the specific tasks and stories the team has formally committed to completing during the upcoming cycle.
And once that's set, it's locked in.
Once it's committed, the team protects that scope fiercely. You don't just add things mid-sprint. That's the deal.
All right, so now we hit phase 3, the iteration itself. This is the engine room where the value actually gets built.
This is the execution phase, yeah. The duration for this time box, which in Scrum is often called a sprint, is typically anywhere from 1 to 4 weeks.
And consistency is the key here, I'm guessing.
Consistency is vital. If you choose a 2-week cycle, you stick to 2 weeks. Every cycle is 2 weeks. This fixed rhythm, this cadence, helps the team measure their velocity accurately and allows them to more predictably forecast their future capacity.
And to maintain that alignment and focus during those few weeks, there is one, and really only one, mandatory meeting that happens every day.
The daily stand-up.
The stand-up.
The daily stand-up is an absolute cornerstone of transparency and coordination. It's a very short meeting, ideally no more than 15 minutes, held at the same time and same place every single day.
And everyone answers the same 3 questions.
That's the classic format. Every participant answers 3 simple questions. What did I complete yesterday? What will I work on today? And what are my roadblocks or impediments? Is anything stopping me from making progress?
You know, the critique we often hear is that stand-ups frequently fail. They devolve into these long, rambling status updates for the manager, or even worse, they turn into problem-solving sessions on the spot.
And that is a critical failure mode. It's so important to understand that the daily stand-up is a coordination and synchronization meeting, not a problem-solving session.
So what do you do when a problem comes up?
If a problem is identified, a blocker, a dependency collision, the team notes it, and then the relevant people stay behind after the 15-minute meeting is over to resolve it. You don't hold the entire team hostage. Violating that time box just kills the rhythm and the transparency of the entire process.
And throughout this whole iteration, all of this activity, all this progress, it has to be made visible to everyone.
Absolutely. Visibility is everything. Progress is tracked using information boards. You might know them as task boards or Kanban boards. Physical or digital.
The wall with the sticky notes.
The wall with the sticky notes, exactly. These boards visualize the flow of work from the iteration backlog into columns like in progress, testing, and ultimately done. This real-time visibility prevents surprises and makes it clear immediately if anyone is overloaded or blocked.
Okay, so the clock runs out on that 2 or 4 week window. The iteration ends. We then move to phase 4, the iteration review. This feels like the moment of truth.
It really is. The iteration review is where the team demonstrates the output of their work. The first key action is to demo the features.
This is a live demo.
A live demo. The team shows the working software or the completed component to the product owner and other key stakeholders. It has to be a real working demonstration. You don't show PowerPoint slides of what you built.
No vaporware.
No vaporware. And secondly, after the demo, they discuss what is and what is not done. This is about managing expectations and providing brutal clarity on whether the iteration commitment was actually met. There's no almost done. It's either done or it's not done.
And the goal, the output of all that work and that demonstration, what are you aiming for?
The ultimate goal is the creation of a potentially shippable product.
What does that mean, potentially shippable?
It means the work that was completed in that iteration is stable, it's tested, and it's valuable enough that theoretically it could be released to the customer right then and there, even if the overall project isn't finished. It has to be a measurable, self-contained chunk of delivered value. This really reinforces that focus on interim benefits we talked about earlier.
So that closes the delivery loop. But the whole system would collapse if we don't also close the learning loop. And that brings us to the final phase, phase 5, the iteration retrospective.
This is, I would argue, the most defining and often the most underutilized part of the entire adaptive cycle.
Why is that?
Because the goal here is not about the product, it's about the process. In the retrospective, we review the completed iteration to identify areas for improvement in future performance. We ask questions like, what went well? What slowed us down? What assumption did we make that proved to be incorrect?
And importantly, it's not a blame session. It's not about pointing fingers.
Absolutely not. It has to be a psychologically safe space. It's a mechanism for continuous process optimization. The team collaboratively defines concrete, actionable things to implement in the very next cycle.
Like what?
Oh, it could be anything. Maybe they realize they need to change their estimating technique, or they need to improve the way they do testing, or maybe they need to adjust the size of their work items because they keep taking on things that are too big. This feedback is then immediately fed back into the next iteration planning meeting.
So it's a closed loop.
It's a closed loop. This systemic, continuous learning is what allows the entire process to adapt and get better at how it works every single cycle.
Okay, that 5-phase loop is really the adaptive DNA then. But how that DNA expresses itself? Well, it seems to depend heavily on the specific framework that a team adopts.
That's right.
Let's shift our focus now from that general life cycle to 2 very specific implementations, Scrum and Kanban. They're both adaptive, they both follow that general pattern, but they enforce structure and flow in fundamentally different ways.
They are, and they're powerful contrasts. You know, if you were building a brand new application from scratch with a dedicated product team, you might choose Scrum.
Okay.
But if you were, say, managing an IT help desk or a continuous maintenance pipeline, you would probably be better off with Kanban. The choice really depends on whether your highest priority is a predictable cadence or a continuous throughput of work.
Let's do the deep dive into Scrum first. We know it's structured, we know it uses those iterations or sprints, but what are its core mechanics?
Scrum is defined by its rigorous cadence and structure. It organizes all work into stories. And we should probably define that term clearly.
Yeah, what is a user story?
A story is not just a task. It's a value-driven narrative. It's always phrased from the end user's perspective, using a specific format. It goes something like, as a type of user, I want to perform some action so that I can achieve some goal.
Ah, so it's always tied back to a why.
Always. For example, as a customer, I want to be able to reset my password so that I can regain access to my account without having to call support. Every single piece of work is explicitly linked back to a purpose, to a user value proposition.
Got it.
And these stories are then completed in those fixed-length sprints we talked about, the time boxes of 1 to 4 weeks. This consistent duration, this fixed time box, it establishes a predictable, rhythmic heartbeat for the team. And that fixed time commitment is really Scrum's main constraint.
Our sources illustrate the planning for this pretty well. We can see an example where you start with a large overall product backlog, say, with 5 complex items like create shop drawings, obtain part numbers for materials, create a design verification test plan, and so on.
And from that large list, items are very carefully selected and formally committed to fixed sprints. And you have to notice the distinction here. The overall backlog is long and flexible, but the commitment for, say, Scrum Sprint 1 is fixed and rigid. It contains just 3 specific items. Scrum Sprint 2 has its own 2 specific commitments.
And what happens if an item that was committed to Sprint 1 doesn't get finished by the deadline?
This is a key rule in Scrum. It doesn't just spill over and magically finish itself in Sprint 2. It's considered not done. It goes all the way back to the product backlog, where it has to be re-estimated and reprioritized against all the other work for a future sprint.
That enforces some serious discipline.
It does. And the tracking mechanism during that fixed sprint is the Scrum board.
Right, the board we see in the source.
The Scrum board is there to visualize the flow of work, but only within the scope of that single sprint. The columns might be simple: to do, in progress, and done. Looking at the example, we can see that for a sprint that has 9 days remaining, the team is focused solely on completing its committed items. We can see create kitchen documentation is in progress, while the other 2 committed items are still waiting in to do.
And this highlights what you said is the most crucial mechanical characteristic of the Scrum board, the thing that really reinforces that fixed cadence.
Yes. The Scrum board resets after each iteration. Once Sprint 1 ends, boom, the board is cleared, all the done items are archived, any unfinished work goes back to the backlog, and a clean new board is set up for Sprint 2 with its new set of commitments.
So it creates this intense laser focus.
It does. It's designed to make sure the team is only ever looking at their current fixed commitment. It prevents the team from feeling distracted or overwhelmed by that massive backlog, and it fiercely protects the iteration's scope from mid-sprint changes or additions.
All right, now let's pivot completely and talk about Kanban. This methodology seems to throw that core idea of the time box right out the window.
It does. Kanban operates on a philosophy of flow over time box. The moment you remove the fixed iteration, you lose that predictable cadence of Scrum. What you gain is continuous motion. Kanban teams operate with no fixed iterations. They simply start a new piece of work the moment the previous one is finished.
Okay, but if they don't use a fixed time box as their main constraint, how do they enforce discipline? What stops the team from just starting 50 things at once and then not finishing any of them?
And that is the central question. That's where work in progress limits, or WIP limits, become the single most crucial constraint in the entire system.
So instead of limiting time, you limit concurrency.
Exactly. Kanban limits the number of items allowed in each stage of the workflow at any one time. For instance, the in progress column on your board might have a big red 3 next to it. That's the WIP limit.
And what happens when there are 3 items in that column?
If 3 tasks are currently in progress, the team is strictly forbidden from pulling a 4th task from the to-do column. Even if someone is free, they cannot start new work.
That must force a complete shift in mindset for a team.
It does. It forces the entire team to focus on finishing, not on starting. When that WIP limit is hit and a task is blocked or stuck, the team doesn't look for new work to stay busy. They immediately swarm the stuck item.
Swarm it.
Swarming means everyone temporarily drops their individual work and collaborates to fix the bottleneck. Whatever is holding that item up, the team works together to resolve it and get it flowing to the next stage. This discipline is what maximizes efficiency and throughput.
Let's visualize the Kanban board from our source material. The first thing that jumps out is just the sheer volume of items in the backlog column.
Exactly. A Kanban board shows the continuous pool of potential work. The backlog is huge. It might list 9 or more issues, everything from shop drawings to bills of materials. This reflects an operational reality where new requests are constantly flowing in.
And looking closely at the columns, you can see the WIP limits explicitly stated.
Right. You'll see the to-do column might have a limit, and in progress has its limit of, say, 1 or 2. This creates a pull system. You can only pull a new item into a column if there's available capacity under the WIP limit.
And crucially, unlike the Scrum board, the Kanban board does not reset.
Never. It is a continuous, perpetual visual representation of the team's pipeline. It maintains that view of continuous flow.
So it's better for certain types of work.
This non-resetting, continuous view is ideal for operational environments. Think of IT support or a maintenance team. Places where priorities can shift minute by minute and the focus is on rapid resolution and continuous service delivery, not on coordinating a fixed product release every 2 weeks.
That's a great distinction.
So yeah, to sum it up, Scrum is often favored by teams building a new product with a defined, albeit flexible, scope. Kanban is often ideal for teams focused on optimizing an existing workflow and handling unpredictable demands.
So Scrum uses a fixed time filter to pull work, which guarantees a predictable cadence.
Right.
And Kanban uses a WIP limit filter to pull work, which guarantees a continuous flow. They're both adaptive, but they're clearly optimizing for very different organizational needs.
That's a perfect way to put it. Now that we've established those two big methodologies, we really have to talk about transparency. Because whether you're enforcing cadence via Scrum or flow via Kanban, you absolutely need real-time tools to assess progress and risk.
You can't just trust that it's all going well.
You can't. You need data. And this is where some very specific charts and visualization tools come into play.
Okay, so probably the most famous visualization tool for iteration-based adaptive work like Scrum is the burn-down chart. How do these actually work, and what hidden truths about a project can they reveal?
Burn-down charts are, at their core, very simple. They're just graphical representations that track the remaining work over time.
Remaining work, not work completed.
That's a critical distinction. We're tracking what's left to do. This remaining work is usually measured in some proxy for effort, like the story points we mentioned, or in the examples from our source material, it's measured in hours.
And why are they so essential for, say, a manager's insight?
Because in one single picture, they show you progress, they show you pace, and most importantly, they show you whether the team is on track to meet its commitment for the iteration. It's an early warning system.
Let's analyze the first example from the source, the planned effort chart. This looks like the ideal, perfect world scenario.
It is. This is your baseline. The chart starts on day 0 of the iteration with a committed workload of, let's say, 400 hours of effort remaining on the y-axis. The line then plots a perfectly straight downward path, hitting 0 remaining effort exactly on day 9, the last day of the iteration.
The ideal burn down.
It's the ideal burn down. This straight line represents the constant, perfect velocity the team would need to maintain to finish exactly on time. It is the expectation. It's the plan.
But of course, reality is never a straight line. Which brings us to the next figure, which plots the actual remaining effort as a dotted line against that planned baseline.
And this is where the real risk assessment begins. If you look closely at the chart, you'll notice that from day 1 through day 3, the dotted line, which is the actual remaining effort, is tracking above the planned effort line.
What does that mean in practice?
It means the team is behind schedule. For instance, on day 3, the plan says there should be about 275 hours of work remaining. But the dotted line, the reality, shows there are still 350 hours remaining.
So they're significantly behind the planned pace. What could cause that?
A few things. It could mean they just got off to a slow start, or more commonly, they encountered unexpected complexity in a task. Or in a less disciplined team, it could mean that more work was added to the backlog mid-iteration, which is called scope creep.
So the burn-down chart immediately makes these kinds of issues visible to everyone.
Exactly. It flags a slow start or scope creep instantly. If that dotted line consistently tracks above the planned line, it is a massive high-risk indicator, and it forces an immediate conversation.
It's not something you can hide.
You can't hide it. The team has to ask, do we need to pull some work out of this iteration scope to succeed? Do we need to swarm on a blocker that's holding us up? Or do we need to adjust the way we're measuring effort because our initial estimates were just plain wrong? It forces you to deal with the risk early on day 3 rather than discovering you're hopelessly late on day 9.
The source also shows an example of smooth progress. It's the same data, but the jagged daily line is replaced by a smoother curve. Why would a team or a stakeholder prefer to look at a smoothed view?
Well, the daily fluctuations in actual effort can be pretty wild and sometimes misleading.
How so?
Imagine a really big 20-hour task gets completed at 4:58 p.m. on day 5. The line on the chart will suddenly plummet downward. Then, at 9 a.m. on day 6, a new, unexpected blocker arises. And resolving that blocker requires adding 10 hours of new tasks to the plan. The line will suddenly spike back up.
I see. That could cause panic.
To a high-level stakeholder who's just glancing at the chart, that daily volatility can be really distracting or cause unnecessary panic. Smoothing the data helps them visualize the overall trend. Is the team, generally speaking, tracking downward toward completion, even if they have these daily hiccups? It provides a calmer, more strategic view of the overall pace.
Okay, so these charts provide that real-time transparency for risk management, forcing the conversation about unmet commitments to happen early. But what about the biggest structural hurdle to any kind of smooth flow? Dependencies.
Ah, yes, dependencies. They are the necessary evil of any complex project.
You can't get rid of them.
You can't. While agile teams try to structure themselves to be cross-functional and as independent as possible, they can never eliminate dependencies entirely. Our source material points out three main categories that emerge.
What are they?
First, you have end-user dependencies. This is when you're waiting for a critical sign-off or feedback from a client or user. Second, you have decomposition dependencies, which is when a feature is just so large and complex that it has to be built in a specific sequence. Part B logically cannot start until Part A is finished.
And the third?
The third is technology-driven dependencies. This is a big one. It's when you're integrating with a specific external system or an API that is completely outside of your team's control.
The functional dependency matrix shown in the source is a really stark visual reminder of just how complex these interdependencies can become, especially when you have multiple teams working together.
It is, and it shows how quickly interdependence can spiral out of control. If you look at the matrix, take requirement 2, for example. To get it finished, Team D has to perform some work, and only then can Team E pick it up and do their part.
A simple sequence.
A simple sequence. But now look at requirement 5. It requires inputs from both Team B and Team C. So if Team B is blocked for some reason, requirement 5 is completely blocked. And then any subsequent requirement down the line that relies on requirement 5 is also blocked.
It's a cascade effect.
A single delay cascades across the entire system and can bring multiple teams to a grinding halt.
So in a traditional project, you'd try to manage this by meticulously coordinating a master schedule and just hoping nobody's ever late.
Which never works.
Right. In Agile, the approach is different. What are the primary mitigation strategies when a team hits one of these dependency walls?
There are 3 aggressive strategies that teams use to manage these risks and restore their flow.
Okay, what's strategy 1?
Strategy 1 is the simplest. Reprioritizing the tasks. This is the easiest adjustment to make. Let's say task A is dependent on task B, and you suddenly find out that task B is going to be delayed by 3 days.
You're stuck.
In a traditional plan, you'd just be stuck. The team would wait. In an adaptive approach, we don't just wait. We immediately pull task A out of the current iteration, move it back down the product backlog, and then pull up an entirely independent task from the backlog to fill that time box. We are consciously sacrificing the original sequence in order to preserve the overall team velocity.
You're keeping the team productive. Okay, what's strategy 2?
Strategy 2 is a bit more technical, using mock-ups to decouple the work streams temporarily.
Mock-ups, like a fake interface.
Exactly. Let's say Team A needs a specific data feed from an API that Team B is building, but Team B is held up for some technical reason. Team A doesn't have to wait. They can build a simulated or mocked version of that data feed.
A placeholder.
A placeholder, yes. They create a placeholder API that acts exactly like the real one will, but it just returns predictable dummy data. Team A can then proceed with all of their development work, building their features, making sure their code is correct, effectively decoupling their progress from Team B's immediate blockage.
And the real integration just happens later.
The final integration happens later, once Team B finally delivers the actual live data feed.
Okay, and then there's strategy 3, which you said is the most radical and really speaks to the heart of the whole adaptive philosophy.
This is the highest level of agility, and it requires a really collaborative product owner. The strategy is reworking the requirements to remove the dependency entirely.
So you change the plan?
You change the product itself. The team actively challenges the requirements. They go back to the product owner and ask, does this feature truly need the output from that blocking team? Is there another way? Can we simplify the design or change the technical approach or maybe redefine the scope of this feature so that the dependency just dissolves?
So you're not just managing the constraint, you're trying to eliminate it.
You are changing the solution itself to eliminate the external constraint. And by doing that, you're increasing the team's independence and restoring their flow.
You know, that's a fundamental change in the power dynamic of a project. You're taking what seems like a fixed logistical problem, a dependency, and you're transforming it into a variable design problem. But this leads me to a critical question about the practical limits of all this. Where does this continuous flexibility stop?
Right, and that's the perfect way to start synthesizing what we've deep dived into today. We've established that adaptive planning shifts effort away from that massive front-loaded planning phase and toward continuous distributed planning that happens throughout the entire life cycle.
And that new approach prioritizes getting frequent feedback and delivering those valuable interim benefits along the way.
Exactly.
We then mapped out the rhythm of that 5-phase adaptive life cycle. It starts with the project planning meeting, that creates the flexible product backlog, then moves into focused iteration planning, then the execution cycle itself, and finally the critical retrospective that builds continuous process improvement right into the workflow.
And we clarified that crucial distinction between the two main methodologies. Scrum, which is ideal for creating predictability, uses a fixed cadence that's enforced by those resetting sprints.
Right.
And then Kanban, which is ideal for continuous service and process optimization, uses WIP limits to enforce efficiency and flow through that forced swarming behavior.
We also saw how tools like burn-down charts provide that real-time risk assessment. They do it by comparing the remaining effort against the planned pace, which immediately flags issues like a slow start or scope creep. And when teams are faced with those inevitable dependencies, whether they're decompositional, end-user, or technology-driven, the Agile playbook prioritizes flexibility. You can rearrange the sequence, you can use mock-ups to decouple, or most aggressively, you can actively rework the requirements themselves to eliminate the constraint.
And that last point about the retrospective is so important. The structure of the adaptive lifecycle isn't just a mechanism for building a product more efficiently. It's a mechanism for building a better team and a better process every 2 to 4 weeks.
So the product gets better, and the factor that builds the product gets better at the same time.
That's it. That focus on process improvement, baked right into the retrospective, is what ensures sustained long-term high performance.
Okay, so here's where it gets really interesting for me, and this connects directly back to that idea of limitless flexibility. Since these agile teams aggressively seek to eliminate dependencies by reworking requirements, by literally changing the definition of the solution to remove external blocks, it forces you to confront the true immutable limits of your project.
What do you mean by that?
Well, if you could rework nearly all requirements to maintain flow, what are the few that cannot be moved? What are the hard constraints that defy all these agile mitigation strategies? Think about projects that are constrained by physics or by government regulation or by some ancient technology legacy.
I see where you're going.
For example, if you are integrating a new software module into a government's 40-year-old mandated mainframe system, you cannot rework the requirement that the data format must adhere to that mainframe's arcane specifications. That dependency is technologically immovable.
It's a hard constraint.
It's a hard constraint.
Yeah.
Or if you're building a nuclear reactor, the requirement that the concrete foundation must cure for 90 days before the heavy superstructure can be mounted on top of it. That's a dependency fixed by the laws of physics. You can't rework chemistry.
And that is the final provocative thought we want to leave you with. Those few immovable constraints, those non-negotiable technology-driven or physics-driven dependencies, they ultimately dictate the true final limits of a team's agility. They force the entire project, no matter how adaptive the team tries to be, back into a rigid sequential constraint. And that demands the highest level of detailed traditional management, but only within that one inflexible window. It's really understanding those few non-negotiables that truly defines a project manager's ability to maximize agility everywhere else.
Welcome back to the Deep Dive. Today we are diving into a topic that I think, for a lot of people, just conjures up these images of, dry spreadsheets and endless status meetings.
Oh, absolutely. Project scheduling.
Project scheduling. But if you really strip away all that paperwork, the schedule it's the dynamic blueprint. It's like the nervous system for any successful project.
That's a great way to put it. Most people see the schedule as this static thing, a necessary evil that only exists to report progress up the chain.
Right. Just for the stakeholders.
Exactly. And they miss its real function. A robust schedule model is the engine. It's what drives execution, what drives prediction, and most importantly, proactive risk control.
So if your schedule model isn't solid,
then the rest of your project management processes are basically built on sand. It's that fundamental.
And I think reliability is the first casualty when that schedule isn't built with, real rigor.
It is.
So our mission for this deep dive is, I'd say, pretty ambitious. We are going to try and give you a shortcut to mastering the principles, the concepts, and all the good practices you need to create schedule models that are genuinely dependable.
And we're really emphasizing flexibility here because modern projects, they just don't all look the same. We have to be able to move seamlessly from that very established predictive world of, say, the critical path method,
CPM,
all the way into the adaptive high change environments of Agile.
And the source material for all of this, for this deep dive, it's drawn directly from the foundational standards for scheduling. We're talking about the good practices that are associated with the PMI scheduling professional designation, the PMI-SP.
That's right. This content is basically the blueprint for creating schedules that can stand up to an audit. We're going to cover everything from the foundational models to detailed agile metrics, and maybe most crucially, the rigorous governance guidelines you need to keep that data clean and useful for forecasting.
Okay, let's unpack this. Starting with the two main philosophical approaches to scheduling. And I think most importantly, the key factor that determines which one you should actually be using.
To start, you really have to recognize that project management exists on a spectrum of project life cycles.
It's not a one-size-fits-all world.
Not at all. We talk about predictive, iterative, incremental, adaptive, and even hybrid approaches. And the choice you make, it's heavily, heavily dictated by one core variable.
And that is?
Project uncertainty.
Project uncertainty. So, okay, if you're building something like a refinery, the requirements are stable, the solution is well known, you'd lean heavily predictive.
The uncertainty is low, exactly.
But if you're launching, I don't know, a new AI-driven service where you're still discovering what the customer even wants, the uncertainty is through the roof.
And that's where you have to go adaptive. You have to fit the schedule to the problem. It's the most important first decision.
Makes sense.
So let's start with that bedrock of traditional project management. The predictive foundation. That's the critical path method, CPM.
The gold standard for massive, stable projects. I'm thinking construction. Big infrastructure.
Tightly controlled manufacturing, yes. It's the standard because it demands a fixed scope right up front.
And the core focus of CPM, a thing everyone's heard of, is defining the critical path.
Right. That longest sequence of activities that dictates the absolute earliest completion date of the entire project.
So if any activity on that specific path slips by just one day.
The entire project completion date slips by one day. Period.
No wiggle room.
And the mechanism it uses to figure this out is the precedence diagramming method, or PDM.
That's how you sequence everything logically, right? Your finish to start dependencies, your start to start.
All of it. It's how you rigorously calculate the early starts, the late finishes, and maybe the most strategically critical piece of information that comes out of a CPM schedule.
Yeah.
Float or slack.
Float is that flexibility, right?
Right.
The buffer zone.
What?
It is. It's the amount of time a non-critical activity can be delayed without pushing out the project end date.
So it's where you have some breathing room.
Yes, but strategically, float is pure gold. It's what you trade with. It's what you use to manage risk. A project manager's skill often comes down to how well they can utilize and protect the float on those non-critical paths.
Because if you waste the float,
the path becomes critical. And now your management focus just got wider and your risk just went up.
So what happens when the calculations spit out a number that's negative float? That sounds bad.
That is a major, major alarm bell. Negative float means that even if you execute every single remaining activity perfectly, with zero delays from this point forward, you are still forecast to finish late.
So the project is already unachievable as planned.
Officially unachievable. It demands a hard adjustment right now. You either have to shorten durations by adding resources, you have to relax the scope, or you have to go negotiate a later deadline. It's the ultimate reality check that the schedule provides.
And you mentioned earlier that modern tools have taken CPM way beyond just those initial calculations. We're not talking about dates anymore.
Oh, not at all. Modern CPM involves really advanced features like resource leveling.
What's that exactly?
It's where you strategically shift tasks that have float to smooth out the demand for shared resources. Think about it. If you have two activities that both need the same high-demand crane on the very same day,
You have a problem.
you have a big problem. A resource leveling algorithm will automatically move the task that has float to a later date when that crane is actually available. It's what turns a theoretical schedule into an achievable one.
But even with all that power, even with resource leveling, CPM still has its limits, especially around that resource contention you mentioned.
It does.
And that's what leads us to the next step, this refinement called critical chain, isn't it?
That is the big aha moment. Critical chain scheduling, which is based on the theory of constraints, is really an enhancement of CPM.
Okay, how so?
Well, CPM is an absolute master at managing the sequence dependency of activities, but it often fails to properly account for the single biggest cause of project delays in the real world.
Which is?
Resource constraints. That one critical engineer, that single piece of expensive test equipment. The bottleneck.
So ever the one senior security architect, and her approval is required for 3 different integration tasks that could otherwise happen in parallel.
Her availability becomes the defining constraint. It completely overrides the logical task sequence itself. The whole schedule now revolves around the availability of that one person.
That makes perfect sense.
And this is where the methodology forces a really profound cultural shift.
Okay.
Instead of everyone padding their individual task durations, which is a universal, often hidden practice where engineers inflate their time estimates just in case.
Everyone does it.
Everyone does it. Critical chain demands that you estimate your tasks aggressively, typically at the 50% probability level.
So if I think a task might take 10 days, but there's a good chance, a 50-50 shot, it'll only take 8. I have to estimate 8 days.
You estimate 8.
Okay, but where does my safety margin go? I feel exposed.
The safety margin is pooled. It's taken from all the individual tasks, and it's managed explicitly and, most importantly, visibly using buffers.
Buffers, okay.
You have a project buffer, which is a big chunk of time placed at the very end of the critical chain. That protects the project's finish date.
And you have feeding buffers.
Exactly. Feeding buffers are placed where the non-critical paths merge into the critical chain, and their job is to protect that critical path from any delays happening on those other streams of work.
Wow, that is a significant shift. If critical chain is so effective at managing resources and, discouraging that hidden padding, why isn't it the standard everywhere? What are the biggest cultural hurdles?
The cultural hurdle is immense. First, project managers have to completely shift their focus. They stop policing individual activity due dates and instead start proactively managing the rate of consumption of those buffers.
So you're just watching how fast you're eating into your safety net.
You are. And second, teams. They hate estimating at that 50% probability level. They feel completely exposed, like you said. It requires total trust and transparency.
And most organizations just revert to padding.
They revert to padding because it feels safer, even though that safety is an illusion. The padding usually gets wasted early on because of Parkinson's law work expands to fill the time available. Critical chain forces all of that proactive risk management out into the open for everyone to see.
Okay, so on one side we have this highly structured, sequence-driven world of CPM and critical chain. Now let's pivot hard to the other end of that spectrum.
The adaptive response. Agile scheduling.
Right.
We have to pivot because when requirements are in that high uncertainty state, constantly evolving again, think software development, R&D, market testing, the overhead of constantly updating a detailed 500-line critical path model every 3 days, it just becomes organizational waste.
You're planning things that you know are going to change before you even get to them.
Precisely. And that's where methods like Scrum or Kanban just excel. Their key characteristics are, frequent delivers of working product every few weeks and distributed planning.
So the team itself defines the detailed execution plan, but only for a very short cycle.
Right. Rather than relying on some top-down fixed master plan that was delivered months ago and is probably already wrong.
So the schedule here is less about a single fixed end date and more about a predictable rhythm, a rate of value delivery.
Exactly. It's all about rapid feedback loops. So instead of calculating float or monitoring buffers, they rely almost entirely on visual tools, on backlogs, and on a few specific charts to communicate progress.
The burn down and the burn up charts.
That's right. They use those to forecast based on observable actual performance.
So to just summarize this whole foundational part for the listener, if your project's requirements are stable and change is expensive, you have to use a predictive method like CPM.
You must.
But if change is cheap and highly likely, the overhead of CPM is waste, and you should be choosing an adaptive method.
And that choice sets the stage for literally everything else that follows.
Here's where it gets really interesting for me. If these adaptive teams are operating without a fixed critical path, without a rigid float calculation, how do they rigorously track progress? How do they manage stakeholder expectations and maintain accountability?
They do it with those visual metrics you mentioned, focused on deliverables and effort reduction. These charts are the heartbeat of an agile team.
And they communicate everything.
Everything. Progress, forecasts. They do it clearly to the team and to the stakeholders, and it minimizes the need for heavy documentation while maximizing transparency.
So let's start with the first one, the iteration burn-down chart. You call this the remaining view.
Yes. This chart is the foundation for tracking an agile sprint or iteration, which typically lasts, 2 to 4 weeks.
Right.
And it tracks the remaining effort, usually measured in ideal hours or task estimates, against the days of the iteration. The commitment is very simple: drive the work down to 0 by the deadline.
And the visual analysis is incredibly revealing.
It is. Imagine a chart. The horizontal axis is the iteration days. The vertical is the remaining effort. First, you plot a planned effort line.
The ideal path.
The ideal path. If you committed to, say, 400 hours of work over a 9-day iteration, that planned line is just a straight downward slope from 400 on day 0, aiming right for 0 on day 9. That line is your commitment baseline.
Okay, now let's talk about the real world. That actual line, the remaining effort line, it can deviate wildly from that plan.
It often does.
So let's take a scenario. What if that actual line stays consistently above the planned line?
That immediately signals trouble. The team is falling behind their schedule target. If that actual line stays high, it means the rate of work completion is just slower than everyone expected.
So maybe by day 5, the plan says you should have 200 hours left.
But your actual line is still way up at 300 hours. That large gap tells you 2 things. First, the team probably isn't going to meet its iteration commitment.
Yeah, second.
The initial estimates were likely too optimistic. The work is harder than they thought, or they've run into unexpected blockers.
The volatility of that actual line is also a key indicator, isn't it? What if the line stays flat for a few days and then just drops like a rock on the last day?
That high volatility suggests a critical flaw in the process. It usually means the team isn't breaking their work down into small enough pieces.
Or they're delaying integration.
Or they're delaying integration and testing until the very last moment. Work isn't truly done in small increments. It's being completed in these big, stressful batches right before the deadline.
Whereas a healthy burn-down chart.
A healthy chart should show small, consistent drops every single day. It reflects daily progress and incremental delivery.
But the chart can show good news, too. What if we see the remaining effort line drop below the planned effort line, especially early on?
That's a great sign. It means the team is likely ahead of schedule. Maybe the tasks were easier than they anticipated, or the team's capacity was higher than they thought.
So if you see a huge drop between, say, day 3 and day 5...
It means a significant chunk of work was completed and accepted really rapidly, and that provides this immediate high-fidelity feedback that allows the product owner to potentially pull more work into the sprint, or, more commonly, just start reprioritizing the backlog for the next iteration. It's powerful information.
Okay, now let's shift focus to the other big one, the burn-up chart. You call this the completed view.
Yes, and this one tends to be a favorite among stakeholders.
Because the line always goes up.
The line is always moving in the right direction. It focuses on value delivered. The burn-up chart shows completed work, and that's usually measured in story points done, rather than looking at remaining effort.
So the emphasis is entirely on what is finished and accepted.
It links progress directly to delivered value.
And there's a key governance rule here, which really aligns with that agile focus on a working product.
A very strict rule.
Story points only count when the feature or the story is 100% complete. It has to meet the definition of done.
That is non-negotiable. No partial credit for being 90% done. Done is a binary state. It is or it isn't.
So if we visualize this chart, we'd see a solid line tracking those story points done, moving upward against maybe a projected completion line.
Right. And if you see that solid line flatten out for 2 or 3 days, say around the middle of the iteration, it doesn't necessarily mean the team is idle.
What does it mean?
It often means the work is actively stalled. They're waiting on something. Critical external testing, a security review, integration with another system. The burn-up chart is brilliant at flagging where your value delivery bottlenecks are.
And these iteration level charts, they both tie into what is maybe the most strategic metric in all of Agile: velocity.
Velocity is absolutely crucial, not just for tracking, but for capacity planning and, frankly, for defending the team against scope creep.
So how is it defined?
It's simply the sum of story points that are completed and accepted within one iteration.
And by tracking this over time...
By tracking the average rate over multiple iterations, say the last 3 to 5, the team establishes a predictable, statistically sound rate of work delivery.
So velocity isn't just a number, it's the core defense against the business demanding, an unreasonable amount of scope in the next sprint.
It's a reality check, a data-driven one. If our team's average velocity is 30 points per sprint, we simply cannot commit to 50 points next sprint and expect to deliver reliably. It's not an opinion, it's a forecast based on historical fact.
And that average velocity is then applied directly to capacity planning for the future.
Yes, it allows the team to accurately estimate how much work they can realistically take on, which prevents that cycle of overcommitment and burnout that kills so many teams and destroys the reliability of their forecasts.
So velocity in these charts, they all feed directly into the longer-term high-level view. That's release planning. How is that structured, given how little detail you have so far out?
Release planning covers a much broader time horizon. We're talking 3 to 6 months across multiple iterations. The focus here is on high-level features and strategic epics, not granular day-to-day tasks.
And it's hierarchical, right, to ensure alignment.
Very hierarchical. You start at the top with the product vision. That's the ultimate goal, the strategic objective for the entire product.
And that vision then filters down.
It filters down into the product roadmap, which maps out those features over a longer timeline. The roadmap then drives the release plans, which establishes the specific iterations or sprints needed to deliver a chunk of functionality.
And only then do you get to the iteration plans, which schedule the actual feature development in detail.
That's the hierarchy. And the estimation breakdown reflects this perfectly, which is fascinating.
How so?
At the high level, features are delivered via user stories, and those stories are estimated in an abstract relative unit called story points.
Using techniques like planning poker.
Right, but when the team gets ready for the actual execution in an iteration plan, they break those stories down into concrete tasks. And those tasks are estimated in concrete hours.
So you shift from abstract story points, which measure size and complexity, to concrete hours, which measure effort.
That shift is essential for the day-to-day execution and resource allocation. One informs strategy, the other informs execution.
And finally, those releases themselves. They aren't all scheduled the same way, are they? They can be driven by different business priorities.
That's right. A release can be feature-driven, which means we release only when features X, Y, and Z are completely ready.
Cool.
It can be time-driven. We release every quarter, no matter what, to hit a market window.
And the third type?
Cost-driven. We release when the development budget runs out or hits a specific financial milestone. This flexibility means the scheduling rhythm is defined by the business objective, not just the development team's pace.
If we connect all this to the bigger picture, the best scheduling model in the world, whether it's the precision of critical chain or the fast feedback of agile.
It's utterly useless if the underlying data is unreliable, inconsistent, or unprotected.
So the governance around this schedule is what makes it a trusted source of truth.
It's the framework. It's everything.
This is the operational side of scheduling. The rules of the road that protect the integrity of your forecast. And that commitment has to start with the schedule management plan.
It does. The schedule management plan is the guiding document for the whole process. Think of it as the contract between the project manager, the team, and the organization.
Its purpose is to integrate all the scheduling efforts into the overall project management plan.
And it explicitly defines the how. The processes, the tools, the templates, the approach for creating, updating, and sharing the schedule model. It ensures consistency.
And it has to be integrated with everything else. It must align with the work breakdown structure, the WBS, to make sure every activity maps back to defined scope.
Guaranteed. And it must specify how you're going to measure performance. That means aligning the schedule with cost controls, using metrics like earned value management, EVM, and critically, earned schedule.
Let's pause on earned schedule, ES, for a second. It's a vital, but I think often overlooked, refinement on EVM.
It is. Traditional earned value calculates your schedule variance, your SV, as a dollar value. The problem is, once a project is past its planned due date, the Schedule Performance Index, the SPI, mathematically hits a ceiling of 1.0.
So it stops telling you how late you actually are.
The metric is effectively lying to you. It gives you this false sense of stability because you've technically earned all the value you could have earned by that point in time.
Even though you're still late.
Precisely. Earned schedule corrects this fatal flaw by using a time-based metric. Instead of asking, how much value have we earned, it asks, how much time should we have spent to earn this value? It replaces that dollar-based variance with a time-based variance. And this allows the performance metrics to accurately reflect delays even after the planned completion date, which gives you a far superior, more accurate forecast of the actual project completion time.
So integrating earned schedule is really a mark of a mature scheduling practice.
It really is.
Okay, so we have the management plan defining the process. But before we even build the model, We have to protect the raw data. That's the schedule data management plan. This is basically your insurance policy.
It's all about business continuity and data integrity. And you must have your project scope, your WBS, and your resource definitions established before you can create this plan. If you don't, you have to stop and define them.
And this plan addresses how the raw data, the actual schedule file itself, is going to be maintained, accessed, and recovered.
That's right. And there are several areas that demand real rigor.
What are the key ones?
First, user access. You have to define roles and responsibilities. Who can make changes? Who can only report progress? Who has read-only access? Strict access control prevents accidental corruption of the file.
Makes sense. What's next?
Backup frequency. Is it daily? Is it weekly? This has to be based on the volatility and the criticality of the scheduled data. If you're reporting daily, you have to back up daily.
And retrieval capability is key, right? Especially if you get into forensic analysis or a claims dispute.
Absolutely vital. Your data retrieval procedures must be established, and this is the key part, verified. You have to test that you can actually retrieve a previous schedule instance.
So you can reconstruct the timeline.
Exactly. You can prove when a change was implemented or defend against a claim. If you can't verify the retrieval, your backup is worthless. And then you have data retention policies, which are often driven by legal or audit requirements for how long you have to store that data after the project is closed.
And for global projects, those infrastructure risks are constant.
Oh, for sure. The plan needs rigorous risk management to address those infrastructure risks. You know, conflicts from global access across different time zones, which can corrupt files, backup replication failures, or even just planned maintenance that takes the system offline during a critical reporting period.
The goal is just simple availability.
Availability, accessibility, and recoverability, 200/47.
Okay, let's drill down into the structure of the schedule management plan itself. The source material lays out this detailed checklist of 12 core components.
This is the real governance structure. This is what transforms a simple list of tasks into a reliable forecasting model.
All right, number one, scheduling approach.
This is where you define the approved methodology, CPM, critical chain, agile based on the project's needs and your organizational standards. The key is consistency.
Number two, scheduling tool. This seems obvious.
It seems obvious, but selecting the right software is critical. It has to be compatible with your chosen approach and how you want to integrate data. Some tools are just better at integrating cost and resource data than others.
Okay. Number three, schedule model creation plan.
This defines the development methodology. Who is building the initial schedule? How long will it take? And most importantly, how are you going to manage stakeholder participation?
So are the teams who do the work actually defining the task durations, or is it being imposed from the top down?
And the former is always better for buy-in and accuracy.
Number four, schedule model ID.
Every schedule model needs a unique identifier. Simple as that. For tracking, for cataloging, it's vital for historical analysis across a whole portfolio of projects.
And number five gets even more granular. Schedule model instance.
This is a finer point of governance, but it's important. It's not just the model, but each snapshot, every saved, archived version of the schedule that needs a unique ID for auditing. When you publish a revised baseline, that instance has to be uniquely cataloged.
Got it. Number six is calendars and work periods.
This is the heartbeat of the project. You set the project's default calendar, your working days, your hours. But crucially, you also have to define resource-specific calendars.
Like an engineer who works 4 10-hour days.
Or a consultant who's only available on Tuesdays and Thursdays. But there's a big trade-off here. Using multiple calendars adds significant complexity and risk to the automated float calculations in the software.
So it could actually compromise the reliability of your critical path analysis.
It can. The advice is keep it simple if you can, but be accurate if you must.
Okay, number seven, update cycle and granularity. This one sounds bureaucratic, but I have a feeling it's a huge deal.
Oh, it's massive. This is where you balance that need for control against the reporting burden on the team. You have to set the frequency for status updates. Is it hourly for a system outage, weekly for an IT sprint, or monthly for long-term construction?
And that frequency is based on the project's volatility, its risk, its duration.
And this ties directly to granularity. The detail of your activities has to be optimized. Too much detail, the schedule is costly and unwieldy. Too little, and you lose control.
And there's a standard good practice here, a rule of thumb.
A very clear one. An activity's duration should typically be less than twice the update cycle.
So that rule is designed specifically to prevent something. The dreaded 99% complete syndrome.
That's it. We've all seen it.
Tell us more about that. It's the bane of every project manager's existence.
It happens when an activity is estimated to take, say, 6 weeks, but you only get a status update every week. For the first 5 weeks, the report comes back. 20%, 40, 60, 80, and then 99% complete. But the activity is still not finished.
And the scheduler has no real information about what went wrong.
None. The delay is only recognized when the task should have been 100% finished. It's too late. But if you limit that duration to 2 update cycles, for instance, a maximum of 2 weeks if you're updating weekly, the status has to be reported as either complete or late much, much sooner. It allows for immediate mitigation.
That's a great rule. Okay, number 8, coding structure.
This is all about making the data useful for analysis. You develop codes for things like phases, locations, responsible departments, and the link back to the WBS.
And the activity identifiers themselves have to be unique and separate from those codes.
Yes, for maximum reporting flexibility.
Number 9 is resource planning. This is what makes the schedule achievable.
Exactly. A resource-loaded schedule identifies your people, your equipment, your material needs, and it verifies their availability against calendars and required skill sets. This is what lets you generate usage curves, perform resource leveling, and accurately mitigate external impacts, like a weather delay.
Number 10, key performance indicators, or KPIs.
You have to define what success looks like up front. Use operational KPIs like activity starts and finishes, backlog metrics in Agile, or duration growth in predictive models. And these must include those crucial EVM and earned schedule indicators we talked about.
All right, 2 more. Number 11, master schedule model.
This is for organizational complexity. For massive projects, you need to structure the schedule as a master project with sub-projects linked together.
So by phase or by contractor.
By phase, contractor, delivery team, whatever makes sense. And you only link them at key delivery or acceptance points. This prevents the schedule from becoming one massive, unwieldy file that takes 10 minutes to load.
And finally, number 12, change control.
You have to plan for the inevitable. You use the configuration management plan to track changes, to mark affected activities, and to ensure that your baseline is protected. Changes have to be traceable and approved against that established baseline.
Okay, so moving from that management framework to the actual execution vision, creating the baseline schedule itself.
Yeah.
The schedule model can't just be a compliance document.
No, it has to be a dynamic tool that captures the team's actual execution vision.
And it has to be realistic and achievable.
It has to function both backward and forward. Looking backward, it has to support forensic scheduling analysis if litigation or claims come up.
So you can reconstruct the timeline.
And looking forward, it provides crucial lessons learned data for future projects. Ultimately, it defines the what the work, the who, what, and when, the resources and timing, and the sequence.
And to ensure that realism, the schedule has to be perfectly aligned with both scope and resources. Let's talk about that WBS connection first.
This is where scope creep is either prevented or enabled. Every single deliverable or work package from your work breakdown structure must be traceable to a single unique activity in the schedule.
So nothing gets missed and nothing extra gets added.
No scope gaps and no scope creep. This traceability is also your best friend in a claims defense because it proves every dollar spent was tied to a defined deliverable.
And resource verification is just as important. A schedule without confirmed resources is just a wish list.
It's a fantasy. The resource-loaded schedule must verify that your labor, equipment, and material are actually available when you need them. This means using structured resource IDs and attributes like organization, skill level, location, so you can do accurate resource leveling and reporting.
Without that verification, it's just a theoretical sequence, not an achievable plan.
Exactly.
Okay, let's get to the granular steps of actually creating that baseline. We start with the benchmarks. Milestones.
Milestones are your zero-duration, resource-free markers of progress. They are the non-negotiable benchmarks.
The start and finish of a project phase, a key sign-off, regulatory approval.
All of those. Every single project needs a start milestone and a finish milestone, at a minimum. And they have to include any milestones defined by the customer, the team, or other key stakeholders. They're usually the very first things you put into the schedule structure.
And then we get to the core of it, defining the project's activities. The standard has some very specific rules for what makes a well-defined activity. This is where accountability lives or dies.
These rules are essential. They're essential for timely progress reporting and for data integrity. First, activities should be defined by the team responsible for executing them, but critically, every single activity must have a single owner.
One person accountable for performance and progress reporting.
One person. Accountability cannot be split between two departments. If the task is approved design, one specific person must own that task and its completion date. No ambiguity.
That is a huge shift from the way a lot of places work, with that sort of collective, generalized responsibility.
It is one name, one task.
Okay, second rule. The description has to be precise.
It should start with a verb, include a specific object, and use adjectives for clarity.
Give us a strong example. The contrast between a bad one and a good one.
Okay, a bad description. Design system. It's completely vague. That could take a day or it could take a year.
Right.
A good description. Finalize user interface wireframes for mobile payment gateway. It starts with a verb, finalize. It includes a specific object, wireframes for mobile payment gateway, and it limits the scope. The good example is unambiguous. It enables clear reporting and real accountability.
Okay, third rule, continuity. Work should proceed without interruption outside of non-working periods from the calendar. Why is this one so important?
Because if an activity is defined to take 10 days, and on day 3 it has to stop for 5 days because you're waiting on external data, the activity must be split at that natural break.
The schedule has to reflect reality.
The schedule must reflect the reality that install foundation piers stopped on Tuesday and will restart next Monday. If you don't split the activity, you lose all your forensic accuracy and your progress reporting gets skewed. The schedule must be a truthful model of execution.
And finally, duration. This brings us right back to that governance rule we talked about.
Yes, duration should typically be less than twice the update cycle. If you report weekly, the activity shouldn't be longer than 2 weeks.
And you said this is the single best defense against the 99% complete syndrome.
It creates a high-frequency feedback loop. If a task lasts, say, 14 days, and you update weekly, at that first status meeting, the team has to report either on track, which is roughly 50% complete, or trouble, which is less than 50% complete. There's just nowhere to hide delays.
And that ensures the project manager can mitigate problems before they start to impact the critical path.
Before they cascade. Exactly.
The only potential exception to this rule is something called a summary activity.
Right. These represent broad, continuous efforts, like boring a tunnel, or maybe a long lead procurement that you're only tracking by its final delivery date, not by granular progress every 3 days.
So the software might just auto-summarize these, showing only the start and finish dates and the total elapsed duration.
Yes, they're treated as a broad bucket of effort. You're tracking a vendor's work only by its agreed-upon start and delivery milestones. And that distinction between a detailed task, which needs that single owner and that short duration, and the summary activity, which is tracked only by its boundary points, that really clarifies why that strict WBS linkage is so crucial. It determines the level of granularity and rigor you need for any given piece of work.
This has been an incredibly rigorous journey through the world of modern project scheduling. I mean, we've covered the entire spectrum, from the sequence focus of CPM and critical chain relying on buffers and resource leveling,
all the way to the flexibility and the constant feedback loops of adaptive and agile scheduling, where we're measuring velocity and tracking work visually with burn down and burn up charts.
And we dedicated a lot of time to the essential role of governance. Because whether your project is predictive or adaptive, that schedule management plan and the data management plan are they're the non-negotiable foundations.
They ensure data integrity, they define accountability, and they protect the data through backups and strict access controls, which allows your forecasts to rely on facts, not just hope.
What's really fascinating here is that whether you're using a complex critical path calculation or a simple burn-down chart analysis, the underlying good practices, they really remain constant.
They do.
Achieving reliability means clear communication. It means defining clear accountability with a single owner for every activity. And it means protecting the integrity of your data through rigorous backup and retrieval procedures.
And this raises, I think, an important question for you, the listener, to consider. If your current project schedule has activities that don't meet these core rules, maybe they're lacking a single owner, or they have durations so long they extend past 2 or 3 reporting cycles, violating that key duration rule.
What ripple effect might that lack of clarity and control have on your project's reliability forecast?
Is your schedule a model of reality, or is it just a list of wishes?
Something for you to mull over or explore on your own. Thank you for joining us for this deep dive into mastering modern project scheduling.
Until next time. Welcome back to the deep dive. If you've ever managed a complex project, you've probably felt that pain where the schedule starts as this beautiful document of hope.
And then reality hits.
Exactly. And it ends up as like a monument to disappointment. For most teams, a schedule is just a static calendar with deadlines that feel, well, kind of arbitrary.
Yeah, you draw some lines, you assign some names, and then you just cross your fingers that the chaos of the real world doesn't laugh you out of the room.
And it almost always does.
Well, that gap, the one between the plan and what actually happens, that's really the core challenge we're tackling today.
Right. So how do the pros build a schedule that doesn't just list tasks, but actually predicts the impact of a delay? One that can handle resource conflicts and keep everyone in the loop.
From the person on the floor to the sponsor in the executive suite.
Exactly. The scheduling world figured out a long time ago that for these massive projects, where millions or even billions of dollars are on the line.
Or even human lives.
Yeah. The schedule has to be treated like a sophisticated predictive model, just like an engineering diagram or a financial forecast.
And that's precisely why we dug deep into this really rigorous methodology championed by the PMI-SP, the scheduling professional. This framework, it takes you way beyond sticky notes and simple spreadsheets.
It's a whole different level.
It is. It's a formalized, defensible, 9-step process for creating the schedule, maintaining it, and performing some pretty complex risk analysis on it.
Okay, so let's set the mission here. For you, the listener, our goal is to help you quickly grasp the concepts that make a professional, robust schedule different from, that simple task list your software just spat out.
Right. We're going to move through the entire process, starting with the smallest piece, how you define work, and go all the way up to managing project-level risk with statistics.
Right.
We want you to understand not just the steps, but the consequences of skipping them.
And before we get into the nitty-gritty, you said there are 2 foundational concepts that have to be locked down first.
Absolutely. They underpin the entire structure.
So what's the first one?
The first rule is absolute scope coverage. The activity list you build has to account for 100% of the project work.
100%. Down to the last nut and bolt.
Down to the last line of code. No gaps, no assumptions, well, someone will probably handle that. It has to be in the model.
Okay, but that 100% rule immediately brings up a question, right? For these huge multi-year projects, how can you possibly detail every single step for work that's like 3 years from now?
And that is the perfect lead-in to the second crucial concept, rolling wave planning.
Rolling wave planning, so that's the flexibility piece.
Exactly. It's what allows the team to maintain that 100% coverage without getting buried in details that are, frankly, useless for the distant future.
So you're saying the stuff happening in the next 3 months needs to be super detailed?
Mm-hmm. That needs level 5 detail, the specific tasks, who's doing it, the dependencies. But for, say, phase 4, which is 18 months out, you only need level 2 or 3 detail.
The work is still defined, the scope is covered, but you're not breaking down every micro task just yet.
Precisely. Rolling wave planning is the mechanism that lets you respect the foundational rule of 100% scope while also respecting the natural uncertainty of the future.
It means your model is precise where it needs to be and flexible where it can be.
Yeah, it lets the schedule live and breathe without breaking the whole structure. It's a sign of a professional scheduler who understands that planning isn't a one-time event. It's continuous.
Okay, so let's dive into phase 1, building the schedule. This is where we hit the first 3 steps, defining activities, sequencing them, and setting the rules for the logic.
And right away, we have to move beyond just thinking of a task that takes 5 days. The methodology demands specialized activity types.
Why is that? If everything is just a task with a duration, what do you miss?
You miss modeling reality. You miss things like continuous support effort or high-level summaries for reporting. Professional modeling needs specialized tools to show how resources and reporting structures really work.
So we found 3 key types that go beyond that simple duration task. The first one is pretty intuitive, I think. Summary activities.
Summary activities are just containers. They're pure aggregation. They might take, the 500 individual steps of boring a tunnel and group them into something like Foundation Work Group A.
So they don't do any work themselves?
Nope. Their duration is just the span from the earliest start to the latest finish of all the little activities inside them. They're fantastic for communication because you can collapse a ton of detail for executive view.
Okay, that's straightforward. But the next type, level of effort, or LOE activities. This is where things get tricky.
Oh, absolutely critical, and so frequently mismodeled by amateur schedulers. An LOE is an activity that tracks resources over time, but doesn't produce a specific, measurable deliverable.
So it's necessary work, but it's not an event. It doesn't, advance the project on its own.
Exactly. Think about project management or admin support. Or, using the construction example from the source, tracking the resource of a crane. EQPO crane.
Right. The crane is needed for the foundation, the steel, the roofing. It costs money, it takes up time.
But the crane itself doesn't complete a deliverable. The foundation team completes a deliverable using the crane. The crane is just this constant, continuous background effort.
So if it's continuous, how do you model that without it artificially messing up your critical path?
That is the crucial rule. LOE activities should not drive the critical path. They were designed to follow the work, not lead it.
So they're slaves to the actual work or packages.
Precisely. And to enforce that, you have to use a very specific logic. Start to start and finish to finish relationships. You link it to the earliest starting and latest finishing task it supports. If the work runs from day 10 to day 100, the crane's LOE activity must also run from day 10 to day 100.
Okay, so you're modeling resource consumption.
Yes, and for that reason, you must avoid putting fixed constraints on LOE activities. Don't touch their dates. If you do, you break the logic of the entire model.
Now, let's compare that to the third type, hammock activities. They also use that start to start and finish to finish logic, but for a different purpose.
Hammocks are, they're essentially time bridges. Unlike LOEs, which track continuous resources, a hammock activity summarizes the span of time between two other fixed points.
So you could use a hammock to show the total elapsed time between, say, architectural review complete and permit submission start.
Exactly. Maybe that's a key performance indicator you need to report on. The hammock's duration is dictated only by those two milestones you tie it to, whereas the LOE's duration is dictated by the work package it supports.
So summarizing time versus tracking a continuous resource.
That distinction is a hallmark of truly professional scheduling. It's moving from just generic groups to functionally specific models.
So once we have our activities defined, we need to bring order to them with sequencing. This is step 2, the language of dependencies.
And this is absolutely vital. Every single activity, except for the very first start milestone and the very last finish milestone, needs what the source calls a driving relationship.
Meaning it has to be connected to something before it and something after it.
At least one predecessor and one successor. Any activity left dangling is called an open end, and it's dangerous. It creates uncertainty because if it gets delayed, you have no idea what the downstream impact is. A pro scheduler flags those for immediate correction.
Okay, let's run through the 4 relationship types that build this sequence. The main one, the one everyone should default to, is finish to start, FS.
FS is the cleanest, most reliable logic. Activity X must be 100% finished before activity Y can even begin. It's the preference because it's simple and it makes the calculations clear.
But reality isn't always that clean. Sometimes you need overlap.
And that's where the other 3 come in. The 2 main overlap types are start to start, or SS, and finish to finish, or FF.
Okay, so SS, start to start.
SS lets activity Y start only after activity X has already started. Think of laying a long pipeline. You can start testing segment 2 after you've started laying segment 1. Y trails X.
And finish to finish.
That means Y can only finish after X is finished. You often see this with coordinated activities, like 2 different software modules that have to be certified and go live at the exact same moment.
And then there's the rare one, the one that kind of twists your brain a little bit. Start to finish, or SF?
Yeah, SF means activity Y cannot complete until activity X has started.
It sounds backward.
It does, but it has very specific uses, usually for things like shift handoffs. The night security shift, activity Y, cannot finish until the morning security shift, activity X, has started and is on duty.
So it's for continuous coverage scenarios.
Exactly. It's highly specialized. And the main caution for all 3 of these non-FS relationships is that their exact implementation can vary a little bit depending on your software. They add complexity, which is why the rule is use FS unless you have a very, very good and well-documented reason not to.
This rigor leads us to the 2 things you said a professional scheduler avoids like the plague. You call them the cardinal sins. Let's talk about lags and constraints.
Absolutely. Let's start with lags. A lag is just adding a delay. A plus 5 days on a relationship. The PMI rule here is ironclad. Lags must only be used for physical necessities.
Physical necessities. So things dictated by the laws of physics, not by people or bureaucracy.
Precisely. The classic example is concrete curing time. That's a physical process that requires time, not labor. You must not use a lag to model work or waiting time.
What if that 5-day wait is for a government permit to come through? That's not physical, but it's a necessary delay. How do you model that without a lag?
You model it as its own separate activity. Sometimes it's called a schedule visibility task, or SVT. That waiting period for the permit is a risk. If you use a lag, it's invisible, you can't assign someone to it, you can't track its progress.
But if you make it an SVT,
Then you can assign a project manager to monitor the permit status, you can load the hours they spend following up, and you can measure the variance if the wait is longer than you planned.
so a lag hides the risk, and an SVT makes the risk transparent and measurable. That's a huge distinction.
It's the difference between a hidden time bomb and a visible warning sign on your dashboard.
Okay, now for the second cardinal sin. Constraints.
Constraints are those rigid dates you impose on an activity, like must finish on or start no earlier than. The big problem is people use them as a lazy substitute for proper logic.
So if you just force task Z to finish on Friday, November 1st, with a constraint,
You're telling the software to ignore everything upstream. You're breaking the predictive model. If an earlier task is delayed by 2 weeks, the schedule can't dynamically show you that task Z is now impossible. It just shows a massive negative number. Or, even worse, it just breaks the logic silently.
so constraints destroy the schedule's main purpose, which is to predict the impact of change.
Exactly. You should only use them for true contractual obligations, a legally binding delivery date, for instance. And even then, you have to document them heavily in the activity notes. If your schedule is full of constraints, your model is probably broken.
All right, if our activities and logic are sound, we're ready for phase 2. Quantification. This is where we figure out how long and who is doing the work.
And the order of operations here is non-negotiable. The methodology is strict. Define activities, sequence them, then estimate resources, which is step 4, and only then do you estimate the duration, step 5.
Okay, so resources first. Why? Why do you have to figure out the materials, labor, and equipment before you can say how long something will take?
Because the resource is the fundamental driver of duration. If you estimate duration first, you are making a hidden assumption that you'll have the perfect resource available at the perfect time.
You're saying a junior developer might take 8 days, but a senior developer could do it in 4. If I just put 4 days in the schedule first, I've already assumed I have that senior developer.
And you might not. Resource estimation forces you to confront the reality of your team's capacity and capability. Are they shared across 3 projects? Are they senior or junior? Once you define the resources and their availability in step 4, then you can calculate the working time required in step 5.
And this all feeds into the critical path, because a resource conflict, like that one senior developer being booked 150% next month, can change the critical path, even if the task dependencies don't change.
That's right. Resource constraints act like another layer of logic that the schedule has to solve for.
So once resources are set, we finally get to duration estimation. And this is where a simple spreadsheet really falls apart, because the pro methodology says you have to acknowledge uncertainty.
Every duration estimate is just that, an estimate. You have to look at productivity rates, skill levels, known risks, and crucially, you have to document all of your assumptions in what's called the basis of estimate.
So you can trace back why you got it wrong later?
Right. But yes, it's about traceability. Now, the sources talk about 2 types of schedule models based on how they handle this uncertainty. The simple one is a deterministic schedule.
Static durations, fixed dates.
Fine for simple stuff. But for anything complex, you immediately want to move to a probabilistic schedule. This is where you use ranges, distributions. And it leads us directly to a very powerful tool, PR.
Program evaluation and review technique. This is where we stop guessing a duration and start statistically analyzing the risk of that duration.
That's the leap. It's the difference between saying, I think this will take 10 days, and saying, I am 68% confident it will take between 8 and 12 days.
So how does it work?
PERTERT forces the estimator to provide 3 points for every activity: an optimistic estimate, a most likely, and a pessimistic. Just the act of considering the best, most probable, and worst case helps fight our natural human optimism bias.
And then it uses a formula to calculate a statistically weighted average. The standard is the beta distribution.
That's right. And the formula is key. It's optimistic plus 4 times the most likely plus pessimistic, and you divide that whole thing by 6.
So it gives 4 times the weight to the most likely estimate. Why is that weighting so important?
It's a way to minimize the impact of wild outliers. The optimistic and pessimistic numbers can sometimes be based on emotion, if a meteor hits the site. The most likely is usually based on actual historical data. By weighting it heavily, the beta distribution grounds the estimate in reality while still accounting for risk.
The source also mentions a simpler version, the triangular distribution.
The triangular is just optimistic plus most likely plus pessimistic divided by 3. It's simpler, but because it gives equal weight to all three, it can be easily skewed by an overly optimistic or pessimistic number. Beta is generally preferred for rigorous planning.
But the real power here is the statistical confidence it gives you.
That's the game changer. Peer 2 also calculates this standard deviation, or SD, which is a measure of the risk in that estimate. If your duration is calculated at 10 days with a standard deviation of 2 days, you can now say there is a 68.26% statistical confidence the activity will finish somewhere between 8 and 12 days.
And as a project manager, that's priceless information. It tells you exactly how much buffer time or contingency you might need to hold to get to a higher confidence level, like 95%.
It transforms decision-making from subjective guesswork into objective, calculated risk management. That's the real leap from amateur to pro.
Okay, we've defined the work, sequenced it, and quantified it. Now we hit phase 3, the engine room. This is step 6, the calculation, where the software takes all that input and spits out the dates and the float.
Right. This is where the critical path method, or CPM, really comes to life through 2 fundamental calculation passes: the forward pass and the backward pass.
Let's start with the forward pass.
The forward pass is like hitting the gas. It starts at the very beginning of the project and works forward through all the logic, calculating the early start and early finish dates for every single activity.
And the result of that is the absolute earliest the project can possibly finish.
Exactly, the shortest possible project duration.
And then the backward pass sounds like hitting the brakes.
That's a great analogy. The backward pass starts at that project end date and works its way backward through the network, calculating the late finish and late start dates for everything. It's figuring out the absolute latest you can do something without delaying the whole project.
And the magic happens in the gap between those early dates and late dates. That gap is the single most important output for a PM float.
Float is your buffer. It's your flexibility. It's the breathing room in your schedule. And monitoring how your float is changing day to day is the early warning system for project trouble. The PMI methodology is extremely clear about the 2 types: total float and free float.
Okay, let's really nail this distinction down, because this is where a lot of people get tripped up. Total float, TF, is the big picture number.
Right. Total float is calculated as late finish minus early finish. It's the total time an activity can be delayed without pushing out the final project end date. And the key thing is, it is shared across an entire path of activities.
So if one activity on a path uses up the float, it's gone for all the other activities on that same path.
Exactly. And total float can also be negative.
Which is the big red flashing light.
It's the check engine light.
Yeah.
Negative total float means your project is currently scheduled to finish after your required end date. The plan is infeasible, and you need to take immediate action.
Okay, now compare that to free float, or FF.
Free float is very localized. It's the amount of time an activity can slip without delaying the earliest possible start of its direct successor. It's only about the relationship between 2 specific tasks.
And it's never negative.
Never negative. It's purely activity-specific.
Let's use that example from the source activities A, B, and E to make this really concrete.
Okay, so look at activity A. It has a total float of 0 and a free float of 0.
That one's easy. It's on the critical path. Any delay at all immediately affects its successor and the whole project.
Right, straightforward. Now look at activity B, which is off the critical path. It has a total float of 10 and a free float of 10.
What does that tell us?
It means B has 10 days of buffer. It can slip 10 days before it affects the next task in its chain, and it can also slip 10 days before it has any impact on the overall project deadline. It's a very flexible task. You could probably borrow resources from B to help out on A.
Okay, and now the tricky one. Activity E total float is 10 days, but its free float is 0.
This is a classic scenario. The 10 days of total float means the entire path that E sits on has a 10-day safety margin relative to the project deadline. The project isn't in immediate danger.
But the 0 free float.
The 0 free float means that if activity E slips even 1 day past its early finish date, it immediately delays the start of the team waiting for its output. Its successor is now waiting.
So E is the source of inter-team friction, even if it hasn't put the contract at risk yet.
Exactly. The team waiting for E's work is now idle or inefficient, and that's a resource problem. Total float is your big external delivery metric. Free float is your internal coordination and efficiency metric. Understanding that difference is huge.
And that deep understanding of float leads us right into the last part of this phase, resource leveling.
Right. After you do the calculation, the software is probably screaming at you that your lead engineer is scheduled for 15 hours of work next Tuesday, but she only have 8 available hours. Resource leveling is how you fix those overallocations.
And we already said you can't just use constraints to fix it, so how do you do it?
The professional way is to adjust the logic. You use the available float on non-critical activities to move tasks around. You're basically balancing the project duration against your resource capacity. The key is to do it with manual logic adjustments, changing the sequence of non-critical tasks, not by just locking in dates, which again breaks the model.
So we've built it, sequenced it, quantified it, and calculated it. We're now in phase 4, finalizing the schedule. This is where the technical model has to survive contact with, well, reality and politics.
And that starts with step 7, approving the schedule model. The calculated schedule has to be reviewed by all the stakeholders, sponsors, managers, the technical leads. Is the end date realistic? Are the milestones achievable? Can we actually afford the resources this thing requires?
And this is usually where the sponsor looks at the end date and says, nope, too long, make it shorter.
Which leads directly to schedule compression techniques. If the shortest duration calculated by the math is unacceptable, you have 2 primary options to shorten that critical path. The first is crashing.
Crashing is the money option. You throw more resources or spend extra money to get critical path activities done faster.
That's it. If a design review on the critical path takes 10 days, you might crash it by bringing in 2 extra senior reviewers and paying them overtime to get it done in 5. It costs more, but it definitely shortens the duration.
And the second option is fast-tracking.
Fast-tracking is the risk option. You overlap critical activities that would normally be done one after the other.
So instead of waiting for 100% of the design to be final before starting engineering, you start engineering when the design is 80% done.
Exactly. You change the dependency from a finish to start to a start to start with a lag. The duration shrinks, but your risk of rework and change orders goes way up because you're working with incomplete information.
And the scheduler has to document that increased risk.
Absolutely. So once everyone is reviewed, compressed, and finally agreed on a schedule, we hit step 8, baselining. This is the moment it becomes official.
Line in the sand.
The approved schedule becomes the baseline schedule model, and it is the single standard against which all future performance is measured. The rule is absolute. You establish the baseline before work starts, and any change to it has to go through formal change control.
And that baseline is what identifies your original critical path, your original float, your original risks. It's the historical marker.
Without a reliable baseline, any report on whether you're ahead or behind schedule is just meaningless chatter. The baseline provides the objective truth for the project.
Okay, finally. Step 9, the last part of creation. Schedule levels. We have this incredibly detailed model, but you can't show all that detail to an executive.
No, you'd get thrown out of the room. Effective communication is all about matching the granularity of the data to the audience. The source outlines a clear hierarchy from level 0 up to level 5.
Let's run through them quickly. Level 0.
That's the project summary. 1 or 2 lines for strategic partners. It answers one question: are we green, yellow, or red?
Level 1.
The executive summary. High-level milestones for sponsors. They see the big-ticket decision points.
Level 2.
The management summary. This is for managers coordinating across different teams, like design and construction. It shows the handoffs and interfaces.
Wow, level 3.
The publication schedule. This is the first level where you really see the execution detail and the critical path. This is for project coordinators.
Level 4.
Execution planning. This is for the work package managers. It's a tighter focus, maybe the next 4 weeks, making sure materials and resources are ready to go.
And finally, level 5.
Detailed planning. This is the task level, daily or weekly schedule for the supervisors and the team members on the ground. It's their to-do list. This hierarchy means everyone can trust the model without being overwhelmed by it.
Okay, the model's built. Now the hard part. Maintenance. Phase 5 is like the pit stop. You have to keep the model relevant as things change.
And the whole maintenance process hinges on one critical definition: the data date.
The data date, also called the status date, the update date.
Time now date. It's the moment of truth. The data date is the specific point in time that separates historical fact, the actuals, from the future forecast. When you update the schedule, all progress is reported as of that date.
The maintenance cycle is pretty tight. Step 1 is collecting the actuals.
Right. You're gathering actual start and finish dates, percent complete, remaining duration for things that are in progress, and actual resources used. And this has to be verifiable data.
And once you have those actuals, you move to step 2, update and recalculate.
You plug in those actuals, you update the remaining durations based on what the team is telling you, you add any approved changes, and then you hit recalculate. And a new forecast and potentially a new critical path emerges.
Which brings us to step 3, where the real analysis happens. Variance comparison. You take that new schedule and compare it to the baseline.
This is where you identify the deviations. And you need to know how much deviation is too much.
That's defined in the schedule management plan, right? The thresholds.
Exactly. The plan might say a variance of more than 5 working days triggers a formal review. The key metric is the finish variance, the difference between the new early finish date and the baseline finish date. If you're 20 days late against a 10-day threshold, you have a major problem that needs a mitigation plan.
The schedule is always adapting, but the baseline stays put, unless
something truly fundamental changes. And that brings us to the gravity of rebaselining.
this is the nuclear option.
It absolutely is. You should only rebaseline if there's a major scope change or a cataclysmic event, a total redesign, a natural disaster that makes the original plan completely useless for measuring performance.
So if you miss a deadline by 6 weeks because of poor performance, you don't rebaseline, you just manage the variance.
Correct. But if the client says, we need to add 2 entirely new wings to the building, that requires a new baseline. The original plan is no longer recognizable.
And when you rebaseline, what happens?
You have to document the justification, get stakeholder agreement, and archive the original baseline. Then you create baseline 2. And the critical consequence is that it resets all your past performance stats. The remaining work is now measured as on schedule against the new plan. You're essentially starting a new game.
And the foundation for this whole maintenance cycle is the last 2 steps, traceability and change control.
Meticulous documentation. The source insists that the initial logic, every decision, every change, has to be documented in activity logs or notes. If you change your relationship, you need to log why and when. This ensures configuration control.
And it's critical for legal defensibility if a dispute comes up.
Absolutely. And all changes, internal or external, have to go through integrated change control. You have to understand the ripple effects. This whole record is vital for audits, and it's how the organization actually learns from its projects.
This cycle really reinforces that the schedule isn't just a report. It's an engineering model designed to predict and absorb change.
And that predictive power comes from constant analysis. Let's just quickly bring it back to some of the tools we talked about.
The most important analysis is always the critical path, right? Identifying it after every update.
Constantly. It can and will shift. And a big risk indicator is when you have multiple critical paths. That means any delay on any of those paths will delay the project.
We also need to differentiate the critical path from critical activities.
A crucial distinction. A critical activity is vital for reasons other than just time, high cost, high risk, safety. Every activity on the critical path is critical by definition. But a high-risk task can be considered critical even if it has 20 days of float. That float doesn't reduce the danger if the task fails.
And of course, monitoring the loss of total and free float is your early warning system.
If a path loses 90% of its total float in one update, it's now near critical and needs attention. And if free float is disappearing, your internal coordination is failing.
Okay, one last thing. Let's tie that probabilistic estimation back into this with Monte Carlo simulation.
Right. PERT gives you a statistical duration for one activity. Monte Carlo simulation takes those 3-point estimates for all activities and runs thousands of simulations using random sampling to calculate thousands of possible project outcomes.
And what's the practical output of that?
A complete probability distribution for the project completion date. Instead of saying, we finished July 1st, you can say, we have an 85% probability of finishing by July 15th. It allows management to set reserves based on their actual risk tolerance. It's true quantitative risk management.
That really is mastering the model. It's about building something that predicts failure before it happens.
And gives you data-driven options to fix it.
Okay, let's wrap this up with the core takeaways from this deep dive into the PMI scheduling methodology.
First, I'd say really get that distinction between total float and free float. Total float is about the project end date, it's shared, and it can be negative. Free float is local, it's about the very next task, and it's never negative. One is about contractual risk, the other is about coordination efficiency.
Second, that non-negotiable sequence. Resource estimation before duration estimation. Resources and their constraints are the true drivers of realistic timelines. You have to face capacity reality first.
And third, embrace probabilistic analysis. Get beyond a single guess. Using PERT and the beta distribution weighted average giving 4 times the weight to the most likely number grounds your estimates in reality while letting you report your confidence level to stakeholders.
I spent a lot of time today talking about managing the critical path, the longest path, the one with zero float that demands all the attention. But that leads to a final, provocative thought for you, the listener.
We talked about those critical activities, the high-risk, high-cost, safety-related tasks that are sitting just off the critical path. They might have 10 or 20 days afloat. We call these the near-critical paths.
So if you're a truly proactive scheduler, the question isn't just about the critical path. It's how do you strategically manage your attention on those vital activities that currently have float? How do you make sure they don't burn through their buffer and become the new critical path, derailing the whole project?
The zero flow path gets attention by default. But the near-critical paths, where high risk is hiding behind a temporary buffer, that's often where the real unmanaged threats are. Shifting your focus from fighting the current fire to preventing the next one, that's the mark of a master scheduler.
Food for thought for your next project model. That's it for this deep dive. Thank you for diving in with us. Okay, let's unpack this. If you've ever managed a major project, you know that the schedule is so much more than just a list of due dates.
Oh, absolutely. It's the operational DNA of your entire effort.
But I think most people, maybe even some seasoned professionals, operate on what really just amounts to a high-level checklist, a glorified timeline.
That's a perfect way to put it. A timeline, not a predictive model.
And that's what we are diving into today. We're moving far past that basic checklist approach.
Right.
We're getting into the engineering of the schedule itself, exploring the advanced controls, and the mathematical rigor that differentiates a quick timeline from a truly professional, defensible, predictive model.
This is really where you get into specialization. It's what sets apart a project document from a true project forecast.
A forecast, I like that.
And what's fascinating here, the core principle, is that a schedule is only as good as its underlying logic. It's not just about when tasks are due. We are auditing the architecture beneath the surface. I think a lot of project managers mistakenly treat the schedule as this static document.
Right, you print it out, you stick it on the wall.
Exactly. But it must be a living mathematical model. It has to be a simulation engine for future events.
So our mission today is crystal clear then. We need to identify and explore those subtle flaws, the hidden structural weaknesses.
Things like constraints, open ends.
Out-of-sequence work, all the stuff that totally undermines a schedule's validity.
Because if the logic is broken, your forecast is, well, it's worthless.
It's the difference between guessing and knowing.
And once we fix that foundation, we'll move into quantifying uncertainty. We're going to reveal the statistical tools, things like PERT and more powerfully Monte Carlo simulation,
Right.
which are used to manage all that real-world variability in duration and performance. We'll be focusing on the control points and advanced metrics that prove not just what will happen,
But the probability of success.
Precisely. This is all about taking the uncertainty inherent in complex projects and transforming it into manageable risk.
So we're going from simply listing tasks to building an ironclad system. Let's start by becoming the schedule logic police. When you look at where schedules typically fall apart, it's not usually because, a duration estimate was off by a day or two.
No, rarely.
It's because the internal logic was flawed right from the very beginning.
That's the root cause, almost always.
You mentioned 3 major logic flaws. Let's start with the one that gives project managers an immediate but often dangerous sense of control. Date constraints.
Ah, the date constraint. It's truly a double-edged sword, and it is perhaps the most commonly abused tool in the scheduler's toolbox.
I can believe it.
So, constraints are used to set fixed dates for specific activities. In theory, they're necessary for handling immovable external factors.
Like a contractual deadline.
Exactly. A contract mandates delivery by a specific date, or maybe key government-issued equipment has to arrive on a calendar date that's totally independent of your internal construction progress.
But the moment you impose that constraint, you are essentially overriding the logic model, aren't you?
You are.
You're telling the software, ignore the chain reaction of predecessors. This date is fixed, period.
That's a perfect description. You immediately choke off the schedule's flexibility. You sever its ability to react dynamically to changes upstream.
So if something before it is late, the model doesn't care.
It doesn't care. And fundamentally, you destroy its connectivity to comprehensive risk analysis.
So if the constraint is arbitrary, you set a date just because it looks better on a report for a stakeholder, not because of a real requirement.
You've replaced mathematical logic with arbitrary control. Wishful thinking, really.
And what's the real danger in that? If I put a constraint that forces, say, activity B to finish earlier than the logic says it should, where does my critical path go?
It can become invisible, or at the very least, severely
Just
distorted.
invisible.
Yeah. If an activity is constrained, it may report having float or slack, even if, logically, it's a direct driver of the end date.
So it looks safe, but it's actually the thing that's going to kill you.
Exactly. When the schedule is forced to meet a date that violates its natural flow, the software has to create things like negative float or use these artificial workarounds. And that makes the true critical path, the actual longest path of dependencies, extremely difficult for a person to identify.
And that's a massive issue when it comes to delay claims or just honest forecasting.
A huge issue.
So the core best practice here is just absolute self-discipline. Only use constraints when logic alone cannot address the need.
Absolutely. The rule has to be crystal clear. Avoid constraints unless they are genuinely required to meet a contractual obligation or some external fixed dependency.
And if you must use one.
You must document its purpose and rationale thoroughly in the activity notes.
Why is that so important?
Because if you don't document why that date is fixed, anyone looking at the schedule in 6 months, including you, will just assume you are hiding an issue or fabricating a timeline. It destroys credibility.
Okay, let's talk about the nuances here, because constraints aren't just this one monolithic concept, right? There are different types that allow for varying degrees of flexibility.
That's right. We can categorize them based on how much freedom they give the scheduling software.
So what's the best case scenario if you're forced to use one?
The most preferred, by far, is as soon as possible.
That doesn't really sound like a constraint at all. It sounds like the default state for any project task.
It is, and that's precisely why it maintains the most model integrity. It gives you full flexibility. It allows the schedule to calculate dates purely based on the network logic.
So if the predecessors finish early, the activity just moves early, no harm, no foul.
Exactly. It follows the flow.
Okay, so what's the next level down in terms of restriction?
The next level introduces some real restriction. Start no earlier than, or SNET.
SNET. Okay.
This constraint forces an activity to wait until a specific calendar date, even if its predecessors finished weeks ahead of schedule.
So it's used to model a mandatory wait, like we can't start construction until January 1st because of regulatory permits, even though we finished the design back in October.
Precisely. And critically, if the predecessor finishes late, the activity still moves later. It maintains that logical influence.
Ah, I see. So the integrity is somewhat preserved because the predecessor still drives the timing if it slips past the SNET date.
Right. The activity just can't be pulled forward beyond that SNET date. It's less flexible, for sure, but it's manageable.
And then we get to the nuclear option, the one that project managers use when they're desperate or, maybe trying to hide something.
That would be the must start on constraint, the MSO or its twin, must finish on MFO.
And these provide zero flexibility.
Absolutely none. If you set an MSO date, the software forces the activity to start on that day, no matter what happens upstream.
Okay, let's run a disaster scenario. Activity A has a finish to start relationship with activity B. Activity B has an MSO constraint for June 1st, but activity A slips by 2 weeks, and now it's going to finish on Juneteenth. What happens to activity B?
Activity B is still forced by the software to start on June 1st.
But that's impossible.
It is. The schedule calculation essentially violates the planned logical sequence. It creates negative float, it invalidates the forecast, and if you relied on that output to order your resources or inform your stakeholders,
You've built a model that is designed to fail.
yes, you're relying on a false assumption that activity A will magically catch up, or that activity B can just start without its prerequisite work being complete.
So if a scheduler finds a must-start-on constraint in a schedule they're auditing, that's an immediate, massive red flag.
It requires rigorous investigation and almost always elimination.
The key is to prefer flexible constraints over rigid ones to maintain the model's integrity and let the logic drive the dates.
Let the logic do the work. That's the mantra. So, moving from intentional damage via constraints, we can turn to the second major flaw, which is often just born of neglect. Open-ended activities.
Open-end. So these are activities that are just floating.
Pretty much. They're activities that lack either a predecessor, a driving activity, or a successor, which is a driven activity. The only exceptions are the project's start and finish milestones.
This seems so simple, but I can imagine it causes massive headaches in complex schedules. Why is just failing to link up a task such a critical issue?
It creates what we call a logic vacuum. And the consequences are profound. They obscure the logic chain. They make any network analysis totally incomplete.
And the big one.
And most critically, they generate false float. or slack.
False float. Explain that.
Because an activity isn't linked, either directly or indirectly, to the final project finish milestone, the scheduling software may incorrectly report that it has infinite float.
Infinite float. That makes it look like a completely non-critical activity, even if it's essential for the project's completion.
It does.
So I might ignore it for weeks thinking I have all the time in the world, only to realize I've missed a key dependency and now the whole project is late.
Exactly. You could have a multi-million-dollar activity that is actually delaying the ultimate project completion, but because it's not properly linked up, the software just treats it as non-critical.
Our sources define two main types of these open ends. The first one sounds pretty simple.
The first one is omission. This is just straightforward user error. This scheduler just, failed to assign the necessary relationships when they were building the network.
So you have sequence A, then B, then C, but activity C is just left hanging because the scheduler forgot to link it to B.
That's all it is.
That sounds like a simple audit could probably fix it. But the second type, the virtual open end, that sounds far more insidious.
Oh, it is. It's much more subtle
Yeah.
because it occurs after the schedule has already been baselined and you've started reporting progress.
So it appears later in the project.
Yes. A virtual open end often arises with relationships that allow for parallel work, specifically things like start to start or finish to finish.
How does just reporting progress break the relationship? That's the part that's confusing.
Okay, so imagine you have a start-to-start relationship between activity X and activity YX starts, and then Y can start 5 days later.
Got it.
Once the data date, which is the cutoff date for reporting progress, moves past the start of activity X, the logic that drives Y to start is now satisfied. It's in the past. It's been neutralized.
Okay.
So if activity Y still has remaining duration and there is no other finish-start relationship driving it, it essentially becomes virtually open. It's no longer constrained by its original predecessor link.
It's just left writing the data date, as the source says.
Exactly. It's floating with that false float.
Yeah.
The logic that was supposed to keep them connected has been satisfied and passed, but the work hasn't finished, and now the successor is just floating free in the timeline.
But so the resolution here, there has to be a hard and fast rule.
The rule to resolve both types of open ends must be treated as mandatory. Every single activity must have at least one valid predecessor, either a finish to start or start to start, and at least one valid successor, either finish to start or finish to finish.
And that dense network of driving and driven relationships is really the cornerstone of a credible, mathematically sound schedule.
It is. The only exceptions are the initial project start milestone and the final project finish milestone. Everything else must be connected.
Okay, so if constraints are willful damage and open-end or neglect, then out-of-sequence logic, or OS, is that inevitable moment where real-world chaos just crashes right into your beautiful planned model.
That's a great way to put it. It's the collision of the plan with reality.
And this happens all the time on complex sites, right?
All the time. OS occurs when the actual progress on the ground violates the planned logical relationship. The scenario is classic. The plan dictates a mandatory finish-to-start relationship between activity A, let's say pour foundation, and activity B, erect walls.
Okay, so you have to finish the foundation before you can start the walls. Simple.
Simple. But the field crew, maybe due to optimized site access or a really tight deadline, starts framing a section of walls before the last corner of the foundation is fully cured.
They start B before A is 100% finished, breaking that FS link.
Precisely. The causes can range from incorrect initial planning that just didn't reflect reality, to field personnel making what they see as pragmatic decisions, to just simple errors in progress reporting.
But if you leave that unhandled in the software, that OLS severely distorts your key performance indicators, right?
Oh, it corrupts your float calculations?
Yeah.
And it renders any completion date forecasts completely unreliable.
This is where the choice of your scheduling software's configuration becomes absolutely critical. Our sources highlight two fundamentally different ways that software can handle this conflict.
And this distinction is arguably the most important decision a scheduler makes in their settings. The two modes are progress override and retain logic.
Progress override. That sounds like the easy path.
It's the easier path for the software, but it's the far more dangerous path for your project forecast.
Tell us what progress override does. It sounds like exactly what it is. It's just overriding the plan.
It is. So if activity B starts early, even though activity A hasn't finished, progress override just ignores the original logic entirely for the remaining duration. It just assumes the work is now proceeding in parallel.
And the risk there is what?
The risk is that it completely severs the link between the remaining work of A and the remaining work of B. So if activity A suddenly hits another delay, the schedule, under progress override will not show the corresponding impact on activity B.
Because that driving logical relationship has just been tossed out the window.
It's gone.
So the schedule becomes an instant lie the moment OS occurs. It completely loses its predictive power.
It forfeits its validity. And this brings us to the recommended choice, the professional and defensible choice, which is retained logic.
Okay, so how does retained logic handle that exact same scenario activity B starting early?
Retained logic acknowledges the actual start of activity B, but, and this is the crucial part, it preserves the original logical relationships for the uncompleted portion of the work.
Ah.
It recognizes the variance, but it will still delay any downstream activities that rely on the completion of activity A until that proper predecessor condition activity A finishing is officially met.
So if activity B starts 5 days early, the schedule accepts that progress has been made, but the finish of activity B and everything that comes after it is still held hostage by the completion of activity A.
Exactly. It maintains validity by refusing to eliminate the dependency simply because the sequence was violated on the ground.
It holds the sequence accountable.
It does. And for professionals who are building schedules that might be used in potential litigation or delay claims, retained logic is non-negotiable. It maintains the contractual defensibility of the schedule.
So the goal for the scheduler is always to avoid OOS in the first place.
Right. Either by decomposing the activities into smaller, more sequential steps that accurately reflect how partial work can be completed, or by correcting the initial planning logic if it was wrong.
But when OS inevitably happens, using retained logic is the mechanism that ensures the integrity of your forecast remains intact.
It's your safety net for reality.
We've cemented the foundations of our schedule by ensuring perfect logic. Now we have to look at the techniques people use to manipulate the flow of time within that network, often driven by, optimism or maybe just laziness.
Yeah, leads and lags are a primary culprit here.
They seem so useful, though.
They are powerful, but they are frequently misused. A lag is essentially a deliberate waiting period. It's a fixed duration of delay that you introduce after the logical condition is met, but before the successor activity can start or finish.
So you're just saying wait 10 days after the predecessor finishes before you start the next thing.
That's it.
Let's use the source example. Writing a draft is followed by editing the draft, but with a start-to-start relationship that has a 15-day lag.
Right. So editing starts 15 days after writing begins.
Mm-hmm.
That 15 days is just pure, fixed, non-work delay.
Then why is that risky?
That fixed duration introduces unnecessary schedule risk because it's opaque. What is that 15 days for? Is it cure time? Is it a review period? If it's not modeled as actual work, it can't be resource allocated, and it can't be easily modified if the project accelerates or decelerates.
I see the managerial risk there. If I just look at a number, 15 days lag, I don't know who's responsible for that wait time or what event even triggers the end of that wait. It's just dead time.
That's why the best practice is to model lags as discrete activities whenever possible.
So instead of just putting a 15-day fixed lag,
You create an activity called client review period or concrete cure time.
and when it's an activity, you can assign resources to it, you can assign a cost to it, and most importantly, you can assign risks to that period.
By turning it into an activity, you made the delay visible, manageable, and auditable. If it's just a number in a box, it's opaque, and it can really distort the critical path calculation, especially when you have multiple calendars involved.
What do you mean by multiple calendars?
Well, the complexity just multiplies if, say, the predecessor activity uses a standard 5-day workweek calendar, but the 15-day lag uses a 7-day calendar because it's a natural cure time for concrete.
Ah, I see.
If you don't model that carefully, the calculation of the lag can easily span holidays or weekends incorrectly, and that just distorts your final forecast date.
Wow.
Lags have to be defined clearly and documented, or preferably just replaced with work activities.
Okay, now for the time thief, the lead.
The lead is just a negative lag. It's used to accelerate a successor activity by forcing an overlap.
Okay.
The typical use is a finish-to-start relationship, but with a negative time value. For example, using a finish-to-start relationship with a negative 2-week lead between complete punch list and performed landscaping.
So we're starting the landscaping 2 weeks before the final punch list efforts are finished. We're intentionally overlapping work that should technically be sequential.
And this is a very common shortcut for fast-tracking projects.
Yeah.
It creates efficiency, for sure, but it introduces immediate execution risk.
How so?
You're basically gambling that the work that is finished will be enough to support the start of the next task, If that punch list effort drags on, the landscaping crew might arrive on site and find that the necessary preparatory work in their zone isn't finished.
Which creates resource conflicts, idle time, and all the costs you were trying to avoid in the first place.
Exactly. Leads must be monitored aggressively because they force parallelism where the plan initially dictated sequence.
We briefly touched on the different relationship types, and there's one that deserves a specific warning label, the start to finish, or SF relationship. It's so counterintuitive, and it often seems to be a sign of some underlying confusion in the planning.
It is the least common and, I'd say, least intuitive link in the deterministic planning world. Its definition is that the successor activity finishes before the predecessor activity starts.
That just sounds like backward planning. Why would you ever use this?
It defines a very specific situation where the availability or the finish of a successor task is dictated by the future start of the predecessor task.
So it's less of a typical dependency and more like a conditional deadline.
That's a great way to think about it. The source example is perfect. Ensuring the completion of an equipment delivery, that's the successor, is timed to finish precisely when the construction crew that needs it, the predecessor, is scheduled to start using it.
So the finish of one task is constrained by the start of another. It's essentially saying the delivery window must close at the exact moment we open the construction site.
Yes. Another less common but classic example is shift work. You might need the outgoing security guard shift, the successor, to finish its rotation only when the incoming shift, the predecessor, starts its rotation.
So it establishes a necessary deadline that's derived from a future start point to maintain continuity.
Exactly.
And because it's so complex and so rarely needed for basic construction or IT projects, its presence should be a major red flag for any scheduler who's performing an audit.
Absolutely. It demands intense review. If it's used incorrectly, it can introduce massive circular logic errors or just impossible schedules that only surface when you start to report variance from your progress.
So the rule is,
Schedulers must ensure absolute logical integrity, or they should just find another way to model it, maybe using a finish-to-start relationship that's linked to a milestone instead.
this brings us to what feels like a planning cardinal sin: linking summary activities. I'm sure every professional scheduler has seen this shortcut used, and it always seems to lead to disaster.
The rule here is not a guideline. It is an absolute mandate. You must avoid linking summary activities entirely.
Why? What are summary tasks exactly?
Summary tasks, sometimes called hammocks or WBS elements, are simply organizational groupings of detailed tasks. They are containers for work, not work packages themselves.
So if a manager tries to link, say, phase 1 design to phase 2 construction, what specific problems are created?
First and foremost, you destroy your critical path identification. The critical path depends on knowing which low-level activity, say final drawing sign-off, which is a detailed task, is the ultimate driver.
Right.
When you link two high-level summaries, the scheduling software has to make assumptions. It might link the earliest activity in phase 1 to the earliest in phase 2, or the latest activity in phase 1 to the earliest in phase 2. The result is almost always an arbitrary and misleading critical path.
So the path becomes opaque because the software is relying on these proxy dates instead of definitive granular work dependencies.
Precisely. If final drawing sign-off is the real driver, but your summary link is using initial requirement gathering as its anchor, your entire forecast is based on the wrong dependency.
And the second problem.
Second, linking summaries significantly increases the risk of circular logic errors.
How does that happen at the summary level? It seems like it would be obvious.
It's much harder to spot. Circular logic, where task A drives B, B drives C, and C then loops back to drive A, is much harder to find when the links are hidden inside these complex summary groupings. A small, detailed task deep within Summary 2 might depend on an outcome from a task in Summary 1. But if the summaries themselves are linked, you can inadvertently create a feedback loop that makes the entire network mathematically unsolvable.
So what's the only acceptable practice?
You must use detailed, low-level activities for all of your relationships. The logic network has to be built at the granular level for the calculations to hold up. Otherwise, you're just creating a schedule that's impressive to look at, but is fundamentally useless for predictive forecasting.
Okay, we've perfected the logic network. It is sound, it's sequential, it's defensible. But a perfect network that's built in a vacuum of unlimited time and resources is still just a fantasy.
It's a nice theory, but that's about it.
We have to introduce reality. And in project management, reality means resources, people, equipment, materials.
Resource integration is the necessary step that turns a theoretically sound schedule into an actual executable plan. It involves incorporating all the human and equipment constraints that define your real capacity.
So you have to account for specific factors like productivity rates,
Availability limits, and the interfaces between different specialized teams. A schedule that ignores these elements is just a wish list. It's not a plan.
and this leads us directly to the great reality check. Resource leveling.
Oh, yes.
When a scheduler first develops a network, they usually just assume infinite resources, right? If two tasks need the same person, the scheduler assumes that person can work double shifts simultaneously.
The software doesn't know any better. Resource leveling is what fixes that fictional scenario.
So what is it exactly?
Resource leveling is the systematic process of adjusting activity timing or durations based on established resource availability thresholds. You input the constraint, engineer Tom can only dedicate 40 hours this week, or we only have one specialized crane available, and the software adjusts the schedule to eliminate those overallocations.
Let's delve into the mechanics of that adjustment. The classic example of Tom and Sue illustrates the trade-off perfectly.
It does. So imagine Sue is our specialist, and she has an 8-hour daily capacity. In the initial unleveled schedule, we have activity A and activity B, both requiring 8 hours of Sue's time, and the logic allows them to run in parallel on day one.
So the schedule is showing Sue allocated for 16 hours of work on day one.
Which is impossible. That is the resource overload.
That's the classic red flag you see on the resource histogram, right?
Correct. So when we engage the leveling function, the software has to eliminate that overload. It performs a sequencing adjustment.
How does it decide what to move?
Well, since Sue can't work 16 hours, the software typically prioritizes one task. Let's say activity A remains on day one, and then it pushes the non-critical task, activity B, to day two, where Sue can work another 8 hours.
And the crucial insight here is the trade-off. We solve the resource conflict, but we pay a price in time.
Absolutely. The leveling process, almost without exception, extends the overall project duration.
So if your critical path took 100 days when you assumed infinite resources,
It might now take 110 or 115 days once you've leveled. And this is a vital moment of honesty in the project planning cycle. You are finally realizing the true duration based on constrained reality.
and what if that schedule adjustment causes a new path to become critical?
That is extremely common. By delaying activity B from day one to day two, you might have created a domino effect that impacts a dependent downstream activity, and that transforms a previously non-critical path into the new critical path.
So these resource-loaded schedules require constant scrutiny.
They do. And the management conversation changes. It's no longer, can we finish by June 1st? It becomes, we can finish by June 1st if we hire 2 more Sues, otherwise we finish on June 15th. It's about choices.
Once the software has performed this mechanical adjustment, what must the scheduler do before they just hit save?
The scheduler's work is not finished. They have to review the results meticulously. If they accept the new, longer duration, they need to manually adjust the underlying logical relationships to save that outcome.
For example,
They might need to add a mandatory finish-to-start link between activity A and activity B to explicitly code the resource-driven sequence.
and the goal is to avoid using those fixed constraints we talked about earlier to hold the new sequence in place.
Exactly. You want the schedule to remain driven by its own logic, even if that logic is now dictated by resource capacity rather than by fixed dates. You're relying on resource-driven logic, not arbitrary constraints, to maintain the model's integrity.
Okay, let's shift gears from the certainty of resource capacity to the inherent uncertainty of time itself. Every single activity carries risk.
It does.
Relying on a single deterministic estimate, task X will take 10 days, it's just naive because in reality it could take 8 days, or 15 days, or 25.
Deterministic estimates are really relics of simpler projects. For anything complex, we have to model uncertainty using probability distributions and acknowledge that time is variable.
And the most common and robust technique for this, at least at the activity level, is the Program Evaluation and Review Technique, or PERT.
Right.
So PERT relies on a 3-point estimation approach. Let's lay out those 3 points for the listener.
Okay, so we need 3 duration estimates for any given activity.
Right.
First is the optimistic, or O. This is your best case scenario duration, assuming everything goes perfectly and no major risks materialize.
The happy path.
The happy path. Then you have the most likely, or M. This is the standard estimate, assuming normal conditions and typical resource availability. This is often the deterministic estimate a manager would just throw out initially.
Right.
And finally, you have the pessimistic, or P. This is your worst-case duration, assuming significant but anticipated risks occur and delays mount, though, stopping short of a truly catastrophic event.
And the real power of PERT is in how it weighs these three inputs to calculate a statistically expected duration.
Exactly. The formula used for the PERT weighted average is designed specifically for what's called the beta distribution curve, which is the distribution we use to model activity durations.
And that formula calculates the statistically sound expected duration.
Right, it is. The optimistic plus 4 times the most likely plus the pessimistic all divided by 6.
That 4 times multiplier on the most likely estimate seems like the key insight here. Why is the most likely duration given 4 times the weight of the extreme estimates?
Well, the beta distribution is deliberately used because it allows for skewness. That 4xm weighting reflects the statistical tendency for project durations.
Meaning what?
Meaning that while the optimistic scenario is possible and the pessimistic scenario is possible, the most probable outcome is concentrated around the most likely time.
But it's not a perfect bell curve.
It's not. The distribution is often slightly skewed toward the pessimistic side. Delays tend to be more probable and larger than equivalent accelerations. So giving the most likely value 4 times the weight anchors the estimate in reality, while still incorporating the range of risk defined by the extremes.
That's a crucial insight. It builds a mathematical element of caution right into the estimate itself.
It does.
So once we have this weighted average, we can then talk about the risk spread using the concept of standard deviation, or sigma.
Right. Standard deviation, or sigma, quantifies the volatility of that duration estimate. It helps you visualize the risk spread. The wider the standard deviation, the greater the uncertainty and volatility of that task.
So if an activity has a PERT average of 10 days, but a very high standard deviation.
It means that while 10 days is the expected time, the actual time could easily swing between, say, 5 and 20 days, the high-risk activity.
And we use the normal curve to visualize what this means in terms of confidence intervals.
Precisely. If we assume the activity duration follows a normal curve distribution, we can use sigma to define specific confidence levels for the project manager to commit to.
For instance,
in a well-modeled scenario, 68.26% of the time, the actual duration will fall within the mean plus or minus 1 sigma.
that's a reasonable range, but it's often too risky for a firm commitment.
It is. So if you need to be more certain, 95.44% of the time, the duration will fall within the mean plus or minus 2 sigma. This is a much safer commitment for external stakeholders.
So if a project manager commits to a date that is only 1 standard deviation out, they are implicitly accepting a 32% chance of failure, which is a pretty high risk.
Exactly. If the commitment is absolutely critical, they have to move out to a mean plus or minus 3 sigma range, which captures 99.73% of the possible outcomes.
Which means the probability of exceeding that duration is extremely low.
Right. When a project manager commits to a date, they are committing not just to a number, but to a confidence level derived from statistical analysis. And that shift in thinking from a single guess to a quantified probability is the hallmark of advanced scheduling.
So PERT is indispensable for handling the uncertainty of individual tasks, but as you said, a project is a sprawling network. The risk doesn't just add up, it compounds through dependencies and parallel paths.
It absolutely does.
So to analyze the risk profile of the entire network, we need to move beyond single activity statistics and engage the most powerful forecasting engine available, the Monte Carlo simulation.
Monte Carlo is the gold standard for schedule risk assessment, particularly when you're dealing with complex projects. Its function is expansive. It's used to validate the contingencies you've built into the schedule, to identify which risks should be prioritized for mitigation, and to monitor how any change, a new constraint, a resource loss, impacts the overall probability profile.
For the listener who hasn't encountered this, we should think of it as running the entire project thousands of times in a simulated universe.
That's the core concept. The process uses the probability distributions we establish with PERT, the optimistic, most likely, and pessimistic ranges, not just for duration, but also for costs, resources, and specific risk events.
So in a typical simulation, the software runs, what, 1,000 or even 10,000 iterations?
At least. And in each iteration, it randomly selects a duration for every single activity based on its probability distribution, calculates the resulting project end date, and it records it.
So if I run the simulation 1,000 times, I get 1,000 different possible project completion dates.
And those 1,000 outcomes are then compiled to produce a sophisticated probability distribution for the overall duration and costs of the project. This is data that's far beyond the capability of a deterministic critical path analysis.
Which only gives you one single end date based on the most likely estimate.
Exactly. Monte Carlo provides the managerial answer to the question, what is the probability that we will finish by our contractual deadline?
Okay, let's talk about the outputs. What are the key pieces of information generated by this rigorous process that a project executive absolutely needs to see?
The outputs are pure, actionable managerial intelligence. First, and most critical, is a completion probability table.
And this is the table that shifts the entire conversation.
It does. Instead of the scheduler just stating the project finishes on June 10th, the table provides specific dates that are tied to probability thresholds. The simulation might show something like 50% probability of completion by June 11th,
Okay.
a 75% probability of completion by June 13th, and a 90% probability of completion by June 15th.
And this instantly turns risk into a quantifiable management choice.
It does. If your contract deadline is June 12th, and the table shows you only have a 65% chance of hitting it, the executive knows exactly the risk they are taking on. And they can decide whether to spend the money needed to pull that date forward to, say, a 90% confidence level.
That's a powerful tool. A second critical output is the identification of the critical path frequency. This is a major insight that deterministic scheduling completely misses.
It's revolutionary. A deterministic schedule gives you one and only one critical path, the sequence of activities with the least float. But because activity durations fluctuate in reality, the critical path itself actually shifts.
So Monte Carlo identifies which paths are most often critical across those thousands of iterations.
Yes.
So I might have a path that looks safe on paper. Let's say it has 15 days afloat. But the simulation shows that due to the high variability of the tasks on that path, it becomes the overall project bottleneck 45% of the time.
That's the managerial conclusion. That path, which you previously ignored because it wasn't deterministically critical, is now a high-priority risk that demands mitigation and monitoring. It challenges the scheduler's initial assumptions and forces attention onto paths that are volatile, not just long.
And the third major output.
Identifying the high-priority risks. By linking the simulation results back to the individual activity durations, Monte Carlo pinpoints the specific activities, resources, or inherent risks that contributed most frequently to the longest project durations.
And that tells you where to spend your contingency money and your management time for the maximum protective effect.
Exactly. Maximum bang for your buck.
Okay, so we've established that PERT is great for individual activities, but Monte Carlo is necessary for the network. Let's address the key weakness of relying solely on PERT for an overall project estimation. The flaw known as merge bias.
Merge bias is the fundamental mathematical reason why just simplistic PERT summation underestimates the total project duration risk. It's a network-level problem.
Can you break down what merge bias actually is? It sounds complex.
Let's use a simple analogy. Imagine 3 different feeder woes, all leading to a single bridge. That bridge is your merge point activity. So activity A, B, and C all have to finish before activity D, the bridge work, can start.
Yeah.
Each of those roads, A, B, and C, has its own duration variability. It has its own risk.
Right.
A simple P-ERT analysis might calculate the expected time for A, B, and C and just assume they'll all arrive at the merge point pretty close to their average times. But in reality, there's a high probability that at least one of those 3 roads will experience a significant delay.
Because they're independent.
Exactly. If A, B, and C are all independent paths, the delay on the latest path, even if it's not the deterministic critical path, will delay the entire project at that merge point, activity D.
So even if path A is the mathematically critical one on paper, if path B has a really high standard deviation, it might become the bottleneck simply because there's a high chance it will be delayed.
That's it. Simple methods underestimate the cumulative effect of risk from all parallel paths converging onto the same point. Merge bias means the true expected completion date is always later than the date you'd calculate by just summing the average durations of the critical path.
And Monte Carlo corrects for this by testing thousands of combinations. It recognizes that in some iterations, path B is delayed, and in others, path C is delayed.
And it aggregates the resulting overall project delay. It simulates the ripple effects across the entire network simultaneously, accounting for those merging paths, and providing a far more reliable view of the probability of late completion. It's a necessary safeguard against our inherent optimism in network planning.
One final point on modeling risk here. What about those leads and lags we talked about earlier? If a scheduler failed to model them as discrete activities, how does Monte Carlo handle them during the simulation?
This is where sloppy initial modeling comes back to haunt you. For Monte Carlo to properly model uncertainty, Every variable has to have a probability distribution assigned to it.
Okay.
If the scheduling software can't assign an optimistic, likely, and pessimistic duration to a fixed lead or lag relationship, and many advanced tools still struggle with this, that fixed duration remains rigid throughout all 1,000 iterations.
That rigidness completely undermines the simulation, doesn't it?
It creates a deterministic backbone inside a probabilistic model. If your 15-day lag is fixed, but the activities around it are fluctuating wildly, that lag can artificially constrain your risk assessment.
So the solution, once again, is conversion.
Once again, you must manually convert that fixed 15-day waiting period into a discrete waiting period activity, and then you can assign an O, M, and P duration to that new activity so that the simulation can include it in the overall uncertainty modeling.
And if you don't?
If you don't, you run the risk that a significant portion of your project's risk profile is being calculated using deterministic, rigid inputs, and that renders your sophisticated output fundamentally flawed.
We've mastered building the perfect logical network, and we've quantified our uncertainty using Monte Carlo. Now we need to transition to the execution phase. Once the project is underway, we have to measure performance. And for the most comprehensive time-based control, we need to talk about earned schedule.
Earned schedule, or ES, is a crucial advancement because it corrects a fundamental limitation in traditional earned value management, or EVM.
Right, EVM is brilliant for tracking cost and budget variance, but its schedule variance metric, the SV, becomes really unreliable late in a project.
It does. The classic failure point is when the project hits 100% completion, even if that project is 6 months late. Your earned value and your planned value both equal the final budget at completion.
Meaning the traditional schedule variance reads as 0, which gives a completely misleading sense of health.
It reports 0 variance when you are demonstrably, painfully months late. Earned schedule shifts the analysis away from cost-based tracking and focuses purely on time variance.
So what's the core concept?
The core concept of ES is simple yet profoundly effective. Earned schedule is the exact point in time when the current earned value, your physical percentage of completion, was originally planned to be earned.
Let's ground that in a practical example. Say today is day 100 of the project and we've completed $150,000 worth of work. That's our earned value.
Good.
We look back at the baseline schedule and we find that we were originally supposed to hit $150,000 of completion back on day 85.
Correct. So day 85 is your earned schedule, or ES. Day 100 is your actual time, or AT. The difference tells you precisely how many time units, in this case 15 days, you are behind schedule.
That's incredibly intuitive, immediate, and it remains accurate even after the project budget is fully spent.
It provides a clarity that EVM schedule variance simply can't offer near the end of the project lifecycle.
Okay, let's detail the critical time-based metrics that are derived from this concept.
The foundational metric is schedule variance in time, or SV of T.
And the formula for that?
SV of T is simply the earned schedule minus the actual time. So in your example, 85 days minus 100 days equals negative 15 days.
A negative value clearly indicates you are 15 days behind schedule. If SV of T is positive, you're ahead. Simple.
And this leads to the index metric, the schedule performance index in time, or SPI of T, which is crucial for forecasting future performance.
So this tells us how efficiently we're spending our time relative to the plan.
Exactly. It's the ratio of earned schedule to actual time. So ES divided by AT. If your SPI of T is 0.85, it means that for every hour or day of actual time you spent, you only earned 0.85 hours or days of planned progress.
So an SPI of T below 1.0 is the clearest signal that you are consuming time faster than you are earning progress.
It is.
And the managerial implication of a low SPI of T is profound, right? It forces managers to adjust their expectations.
It forces brutal honesty. If your SPI of T is chronically low, you immediately look at the suite of time-based forecasting tools that ES provides. For example, the To-Complete Performance Index in Time, or TSPI.
And what does TSPI tell the team?
It tells you the minimum efficiency or the performance rate you must achieve for the remainder of the project to finish exactly on the planned schedule date.
So if your current SPI of T is 0.80,
your TSPI might come out to something like 1.15, indicating you need to perform 15% better than you originally planned for the rest of the project just to catch up.
and that's a critical metric for resource allocation decisions.
Absolutely. And finally, we get to the core forecasting output, which is the independent estimate at completion in time, or IEAC of T.
So this uses the current performance trend to forecast the new realistic completion date.
It does. It uses the current SPI of T trend to project the final completion time. This provides an unbiased, mathematically derived forecast that perfectly complements the risk-based forecasts that we produce with Monte Carlo.
And the difference between the planned finish date and this new forecast is?
That's the variance at completion in time, or VAC of T. Earned schedule integration means your time-based control and your forecasting are now comprehensive, rigorous, and logically consistent. It all ties together.
This has been an absolutely essential journey into the engineering of advanced scheduling. We started by being the logic police, understanding that structural integrity is everything.
Right, eliminating constraints, open ends, and recognizing that retained logic is really the only choice for a schedule that needs to remain valid when reality hits.
We then moved into that crucial step of incorporating reality through resource leveling, accepting that a longer but resource-balanced project duration is an honest appraisal.
And we quantified uncertainty, moving from the individual task risk modeling of PERT to the comprehensive network analysis and probability forecasting offered by the powerful Monte Carlo simulation.
Right, which guards against those tricky issues like merge bias.
Exactly.
And finally, we made our performance management future-proof with earned schedule, shifting the focus from misleading cost variances to clear, time-based schedule variances that remain accurate even when the project is late.
And this mastery allows you, the listener, to move from being a simple tracker of dates to a true project forecaster, someone capable of handling complex, real-world uncertainty with statistical precision.
That's the goal.
And if we connect this all to the bigger picture, the ultimate purpose of this rigorous scheduling and resource analysis isn't just to track dates, it's to turn probability into predictability.
And that raises an important question that every professional has to internalize.
It does. When your leadership asks for a commitment on a major contractual due date, are you relying on a single deterministic most likely duration, which, let's be honest, carries a 50% chance of being wrong?
No.
Or are you utilizing the depth of Monte Carlo simulation to explicitly tell them we have an 85% chance of hitting that date if we accept a $3 million contingency buffer? Otherwise, the risk level is unacceptable. That level of knowledge is the difference between hoping you finish on time and truly knowing your risk exposure.
That distinction, the move from hope to quantified confidence, is where the real value lies. And here's where it gets really interesting. Something for you to mull over until our next deep dive.
Welcome back to The Deep Dive, the show that takes the complex, dense research and distills it into the knowledge you need to be immediately, thoroughly well-informed.
Today, we are moving far, far beyond just, drawing boxes on a calendar.
Right.
We're really tackling a universal experience for anyone involved in managing complexity, and that's the creeping dread that comes with a fixed deadline.
I know that feeling.
Every massive project, whether you're engineering a new aircraft or you're managing a huge infrastructure overhaul, it eventually faces a time problem. You're spending money, you're busy, but the real question is, are you actually on track?
Exactly. And that illusion of progress, that's one of the most dangerous things in project management. You look at a schedule, and if it's complicated enough, you might just fall back on instinct.
And instinct just isn't enough.
Not when millions of dollars and, critical deadlines are on the line. Understanding the true velocity of a project and predicting its actual completion date with any kind of credibility, it requires moving past that basic tracking.
It requires a scientific, standardized, and an extremely rigorous approach to performance measurement and future forecasting.
So our mission today is a deep dive into the core methodology of advanced schedule management.
And we're specifically drawing on the comprehensive, structured framework outlined for the Project Management Institute Scheduling Professional, or the PMI-SP. This is really the global standard for scheduling rigor.
We are going to unpack the specific metrics, especially those focusing on time, not just cost, and the required data components, the reporting structures, that all transform a rudimentary timeline into a robust, auditable, critical path method, or CPM, scheduling model.
So the goal for you, our listener, is to really understand the specific mechanical components and the mathematical indicators that allow expert schedulers to accurately predict project outcomes, to manage massive risks proactively, and most importantly, to maintain absolute stakeholder credibility.
Regardless of the project size or complexity.
And that journey, it starts not with the schedule itself, but with the foundational governance required to make that schedule credible. So let's unpack this, starting with how scheduling has to be integrated into the larger project ecosystem.
Okay, let's start there. Integration. That seems like the first place where these systems always break down.
It often is.
So when we talk about schedule management in this advanced context, It's not just the act of drawing the schedule, right? It's the governance around it.
That's right. The source material emphasizes again and again that schedule management must be actively integrated into the project planning process through a tailored schedule management plan.
A schedule management plan.
And that plan is, it's absolutely foundational. Think of it less as a document and more as a constitution for how the project timeline is going to be treated, maintained, and communicated.
A constitution. I like that. So it covers the whole life cycle.
The entire life cycle. It dictates the rules of engagement for every single person who interacts with the schedule.
So what are the key elements this constitution, as you call it, has to nail down?
Well, it needs to address critical governance issues. Things like training protocols, making sure everyone who inputs data or updates progress uses the same conventions.
So everyone's speaking the same language.
Exactly, for things like progress measurement or task definitions. It also sets the data management policies, dictating how often you update, what software to use, the methods for version control.
Okay.
And crucially, it establishes the processes for managing updates, revisions, baselines, and of course, change requests. Without this tailored plan, your scheduled data is going to be inconsistent and unreliable from day one.
That sounds less like a scheduling task and more like pure project control.
It is. It's quality assurance.
And critically, the schedule model can't just exist in a vacuum. It has to be dynamically aligned with two other key areas: the project scope and the work breakdown structure, the WBS.
That linkage is completely non-negotiable. If it fails, the entire control system just collapses. The WBS defines what work needs to be done, breaking the project scope into manageable chunks. The schedule model defines when those chunks will be performed. If there's any dissonance there.
Like if the schedule has activities that aren't in the scope.
Precisely. Or if the WBS has deliverables that aren't scheduled, your entire performance measurement and resource allocation system becomes instantly useless.
So if a project manager starts adding buffer tasks that aren't tied to an approved WBS element, even if they think they're being prudent, they're actually breaking that fundamental alignment.
They are. They're introducing phantom work, and that compromises the integrity of the performance baseline. Every single activity in that schedule has to be traceable back to an approved work package in the WBS.
Traceability is the cornerstone.
It is.
Okay, so moving on to the schedule model itself. What's its core purpose beyond just listing activities and dates? What's the why that justifies all this massive administrative and, frankly, intellectual effort?
It's the enabling mechanism for comprehensive project control and foresight. Yes, it provides a timeline of activities with start and finish dates, but its critical uses are strategic.
So what's the first one?
First, it enables precise resource management. It tells you not just that you need 5 engineers, but when those 5 engineers need to be working on which specific tasks for how long.
And resource allocation is almost always the biggest limiting factor in any large project.
It is. Secondly, the model allows for daily control of the work execution. It gives task leaders the ground-level data they need to manage their daily assignments.
Okay, so control. But you also said foresight.
Right, and that's maybe the most critical part. The schedule model is the only tool that allows for crucial threat mitigation and opportunity capture based on calculated reality, not just gut feeling.
How does it do that so effectively? How does it enable that risk foresight?
By continuously calculating and monitoring dependencies, constraints, and most importantly, the critical path.
Ah, the critical path.
The model immediately isolates which activities are absolutely non-negotiable for project completion and which ones have total float or flexibility. This lets you prioritize resources and manage threats before they eat up that float and turn into actual delays.
And a delay on a critical path activity means
An immediate delay to the final project completion. There's no slack there.
that ability to just isolate those critical activities sounds like an efficiency driver all by itself.
Absolutely. And because the project is a living, evolving thing, the model has to be flexible enough to produce varied report formats based on the current stage, specific needs, and most critically, the recipient's role.
If you can't tailor the message gets lost.
And the messenger, the scheduler, loses all credibility.
And that takes us directly to communication tailoring. I mean, if you do all this rigorous analysis, but then you just drop a 500-page schedule on a senior executive's desk.
You've not only wasted your time, you've completely obscured the essential information they need.
The source material provided a phenomenal, really strategic breakdown of this the 6 levels of schedule model presentation.
This is a master class in strategic communication. It's the mechanism for building and maintaining stakeholder credibility. You have to tailor the depth of the information to the specific audience. The CEO and the foreman cannot and should not be looking at the same schedule.
Let's walk through this hierarchy because it forces a real discipline in reporting. We start at the very top, the highest possible strategic view. Level 0.
Level 0 is the executive snapshot. It's often just a single-line project summary, maybe a start date and a planned finish date. That's it.
And the audience for that.
Strategic partners, senior executives, portfolio or program managers.
Why do they only need one line? Isn't that a little dangerous?
Because their primary decision-making context is comparative performance. They're looking at a dashboard with 10 projects on it. They just need to know that Project Alpha is 80% complete and $1 million over budget compared to Project Beta, which is 50% complete and on time.
So it's a triage tool.
Exactly. The classic example is information used for comparison with other projects in the portfolio. Give them a detailed Gantt chart, and they will miss the forest for the trees.
Okay, so from there we step down to level 1. This one's targeted at executive management and the project sponsor.
Still highly summarized, but now it adds financial gravity. They need key information only: project start and finish dates, key milestones, and the associated costs.
So this is tying money to the big milestones.
Right. This view often ties major contractual or project milestones directly to financial gates and funding releases. They're less worried about comparison with other projects and more worried about the critical health of this project.
Okay, so level 1 confirms we're hitting our major financial targets. When do we start to see actual activities?
That happens at level 2, which is designed for project management and the core project team.
The people in the weeds.
Well, sort of. The content here shifts to tracking key project milestones and their progress against the baseline. It keeps them focused on the immediate high-impact goals. If they're mired in the daily detail of, say, a level 5 report, they can lose sight of the quarter's strategic achievements.
So it's the strategic operational view.
Exactly. Level 2 ensures the core team tracks major accomplishments and knows how their collective effort is contributing to the high-level critical path.
I'm guessing level 3 is where the real coordination work starts, bridging that gap between the big milestones and daily execution.
Absolutely. Level 3 is aimed at project coordinators, functional leads, maybe mid-level managers. This level focuses on summary tasks, often tied directly to control counts or high-level WPS elements.
So you're seeing high-level activity bars broken down by work streams, that kind of thing.
That's it. The schedule here has to provide enough definition to outline the scope for each work group, control progress within those groups, and provide mid-range forecasts for deliverables.
Okay, so that's the management view. It's high enough to forecast, but detailed enough to spot a bottleneck in a specific department. Then we hit the implementation phase with level 4.
Level 4 is tailored for work package managers or contract managers. Here, the data becomes dense, but it's specifically segregated by the contract work package they own. The focus is on contractual obligations and detailed deliverables within their specific statement of work.
So a contract manager doesn't need to see the entire project. They just need forensic detail on the one specific $10 million package they're accountable for.
Exactly. They care about their immediate successors and predecessors, resource allocation within their work, and making sure they hit their contractual completion dates.
And finally, the granular view, the absolute ground truth. Level 5.
That's the ground level. The recipients are the task leaders and the actual execution teams. They get the most detailed information broken down by individual tasks. This is their daily checklist.
The nuts and bolts.
The actual scheduled data-detailed resource assignments, specific relationships, required start and finish dates, everything they need to physically execute their scope.
This tiered structure is a massive governance tool. It solves the information overload problem while making sure everyone, from the CEO to the person turning the wrench, gets the precise information they need for their role.
That's the key takeaway. You start with a single, robust model, and then you apply rigorous communication tailoring to deliver the required output. But to ensure that model is robust, we have to use the right tools to measure its performance.
And address the limitations of the traditional metrics.
Exactly.
Which is a perfect transition. Let's move from governance to hard math, and specifically address the time problem that traditional cost-based measurement systems just fail to solve.
Okay, so when you're dealing with large, formalized projects, especially ones that need complex audits or government reporting, the standard mechanism for tracking progress is Earned Value Management, or EVM.
Right. EVM is the standard.
And it's essential. It's fantastic for integrating scope, cost, and schedule to measure cost performance and scope completion. It uses metrics like schedule variance, SV.
But you mentioned a fatal flaw when it comes to time. We've all seen a project hit its budget, but still completely miss the deadline. So where does traditional EVM fall short?
The flaw is in the cost-based nature of its main schedule metric, schedule variance, or SV.
Which is calculated how?
It's calculated as earned value, EV, minus planned value, PV, but because this calculation uses dollar values, it becomes increasingly unreliable as a measure of time progress late in the project.
Can you walk us through that classic scenario, the one where it breaks down?
Of course. Imagine a project with a total budget at completion, the BAC, of $10 million. The planned duration is 10 months. Now, by month 10, the project manager reports that 100% of the scope is complete.
So their earned value, their EV, is $10 million.
Correct. And since the budget baseline said they should have $10 million worth of work done by month 10, the planned value, or PV, is also $10 million.
Okay, so EV minus PV is 10 million minus 10 million, which is 0. Schedule variance is 0.
Exactly. Traditional EVM reports 0 schedule variance, which indicates the project is perfectly on time. But what if that project actually took 14 months to complete? The SV metrics still report 0 at the moment of completion. It stops being a sensitive measure of schedule performance because it pegs the final schedule performance to the final cost baseline. Once EV hits BAC, SV stops moving, even if you are months or years late.
That is deeply misleading. It's suggesting success when there was a massive failure in timeline control. We need a metric that stays sensitive to the passage of time, regardless of the cost completion.
And that is precisely why the concept of earned schedule, or ES, was developed. ES provides improved reporting integrity by shifting the focus entirely from the dollar curve to the time axis.
Okay, so it uncouples time from cost.
Exactly. It stays mathematically sensitive to time variances even when the project is substantially complete, and that enables accurate time forecasting right when traditional EVM falls silent.
Earned schedule, then, is the dedicated analytical engine for our timeline. It allows for, what? WBS-level analysis to pinpoint exact time deficiencies and forecast the ultimate completion time accurately.
Yes, and in terms of time units, not dollars. So let's define the core concepts that make this work. We still rely on the 3 pillars of EVM.
First, planned value, PV. That's the budgeted cost of the work that was scheduled to be completed by a certain point in time. It's the planned S-curve.
Then actual cost, AC, simply the cost incurred for the work actually performed to date.
And earned value, EV, which is the budgeted cost of the work that was actually performed. This measures scope completion in dollars.
Now we introduce the 2 new time-based metrics. First, the most straightforward one, actual time, AT.
That's just the clock on the wall.
Yep. The number of periods, days, weeks, months that have executed so far since the project started.
And now the heart of the innovation, earned schedule, ES.
Earned schedule is defined as the point in time at which the current earned value was planned to be completed.
Okay, say that again.
It's the time on the plan when you were supposed to achieve the value you have right now. To calculate it, we use the formula. ESCOM equals C plus I. C is the number of complete periods where the planned value was fully achieved, and I is the incomplete portion of the current period.
Let's solidify that with a simple hypothetical. Let's say we plan to achieve $100,000 in value every month for a 12-month project.
Okay.
We are currently 6 months into the project, so our actual time, our AT, is 6 months.
Correct. Now, let's say at that 6-month mark, we look at our performance and see we've only completed $450,000 worth of work. Our earned value, EV, is $450,000.
So to get our earned schedule, we look back at the original plan. Where did we plan to hit $450,000? If we planned $100,000 a month, we should have hit that halfway through month 5.
Exactly. In this case, the time at which we were scheduled to reach $450,000 was 4.5 months. Therefore, our earned schedule, our ES, is 4.5 months.
So that defines the delay purely in time. We've spent 6 months of actual time, but we've only achieved 4.5 months worth of planned value.
Right. And that immediately makes the underperformance glaringly clear. And it uses time as the common denominator, totally independent of cost performance.
Now we can use those ES and AT values to calculate the really critical indicators.
The first is the most intuitive one, schedule variance in time, SVT. It measures the schedule delay, or how far ahead you are, in time units. And the formula is beautifully simple. SVT equals ES minus AT.
So using our example, 4.5 months of ES minus 6 months of AT equals negative 1.5 months. You are definitively 1.5 months behind schedule. Clear, quantifiable, no ambiguity.
Next, we determine the Time Efficiency Index, the Schedule Performance Index in Time, or SPI. This measures how efficiently you're using your time relative to the plan.
And the formula for that?
SPIT equals ES divided by AT.
In our example, that's 4.5 divided by 6,
Yeah.
which gives us 0.75.
Right. And here's the analyst insight. An SPIT of 0.75 means you're performing at only 75% of the planned schedule efficiency. You're burning through calendar time faster than you are earning schedule progress.
So if that trend continues, the project is headed for a major delay. An index below 1 is a massive red flag.
It's a huge red flag, and this is a critical point for you to remember. SPIT is about efficiency, not just variance. It tells you the systemic rate of time consumption.
There's also a percentage variance.
Yes. Schedule variance percentage, SV% AT, which is just ES-AT divided by ES. In our case, that's negative 1.5 divided by 4.5, so negative 33.3%. The project is currently 33% behind planned rate of time completion.
This shift in metrics is powerful because once we know our current time efficiency, that SPIT, we can immediately shift from looking backward to forecasting the future.
And that's where we bring the biggest value to stakeholders. That's where the predictors come in. The first is the To Complete Performance Index, TSPI.
I call this the pressure cooker metric.
That's a good way to put it. TSPI measures the performance efficiency you need for the remaining work to finish on time. It asks, given how inefficient we are now, how much better must we be moving forward to still hit the original deadline?
So we're 1.5 months behind. How hard do we have to sprint to catch up?
The formula for TSPI is the remaining work divided by the remaining time. So planned duration, PDES, divided by planned duration, PDAT.
So if our total planned duration was 12 months.
And we use our values, ES is 4.5, AT is 6. The remaining work is 7.5 months worth of value. That's 12 minus 4.5.
Okay, 7.5 months of work.
And that has to be completed in the remaining 6 months of calendar time, which is 12 minus 6.
So we need to achieve 7.5 months of work in 6 months of time.
Which gives you a TSPI of 1.25. This means for the rest of the project, you have to be 25% more efficient with your time than you originally planned just to hit that original deadline.
And if your current SPI is 0.75, needing a 1.25 efficiency going forward that's often an impossible hurdle.
It is. It requires immediate and often costly action, like adding a ton of resources or cutting scope. It's a massive, quantifiable warning sign for management.
But the ultimate prediction tool has to be the independent estimate at completion in time, the IEACT.
Yes. The IEACT provides the official, data-driven forecast for the actual project completion time. And there are two main ways to calculate it, which lets you test different scenarios.
The first one assumes consistency, right?
Yeah.
That things won't change.
Exactly. Formula 1 assumes that our current schedule efficiency, that SPIT of 0.75, will continue for the rest of the project. It's calculated as IEAAC equals planned duration divided by SPI.
Okay, so if our planned duration was 12 months, and our SPIT is 0.75, the calculation is 12 divided by 0.75, which gives us 16 months.
And there it is. The independent, quantifiable truth is that unless performance improves, the project will finish 4 months late. This metric is critical because it gives a realistic forecast that stops management from just clinging to an outdated or, an unrealistic baseline.
Okay, so what about the second formula? Why would we need another way to calculate it?
The second formula is a bit more flexible. It's often used when management believes they can implement specific corrective actions right away, and so you can adjust the predicted performance factor, the PFT. The formula is IEACT equals AT plus PDES divided by PFT.
So actual time completed plus the remaining duration, adjusted by a new performance factor.
Precisely. The core benefit of both of these formulas is giving stakeholders a credible, auditable, data-driven forecast of when the project will truly end. It allows for mitigation, resource changes, or scope adjustments before the delay becomes irreversible.
And finally, there's the variance at completion in time, VACT.
Right, which just measures the expected total time variance, PD minus IEACT. It's the final delta, how many months late we expect to be relative to the original plan.
So earn schedule is essential because it corrects that huge blind spot in traditional EVM.
It gives schedulers a pure, objective measure of time performance and reliable time forecasting formulas that actually hold up under scrutiny.
But none of this analysis, not the SVT, not the IEACT, and certainly not the complex CPM calculations, is even possible if the underlying data structure is weak. We have to make sure the scheduling tool itself is built to handle this level of rigor.
Correct. And that moves us to the architecture of the scheduling tool itself. We're leaving the math for a moment and diving into the raw data components that make all these calculations possible.
Okay, so we're going under the hood.
We are. When you open a professional scheduling tool, you aren't just looking at a timeline. You are looking at a highly structured database. Section 4 of the Practice Standard for Scheduling provides a comprehensive catalog of all the potential data components used in a critical path method, or CPM, scheduling tool.
And that catalog is the blueprint for a professional-grade model.
It is. This standardization ensures clarity, consistency, and most importantly, auditability across different projects and organizations.
So it's not enough to just have a field called duration. The catalog defines what kind of duration it is, how it should be input, how it should behave.
Precisely. But the most crucial element for our deep dive is the classification based on necessity. The components are categorized as required R, conditional C, or optional O.
Okay, so this defines the non-negotiables.
It does, and the required components, the Rs, are then broken down even further into 4 mandatory groups. And this is where the model gets specialized.
What's the benefit of that?
This structure immediately tells an auditor what features a schedule model supports just by checking which groups of required components are populated.
Okay, let's list them again because they frame this whole discussion.
We have 1. Core required components, CRC, which are mandatory for all schedules to function logically.
The absolute basics.
2. Resource required components, RRC, which are only mandatory for resource-loaded schedules.
3.
EVM required components, ERC, mandatory only for earned value management integration. And 4. Risk required components, KRC, mandatory only for schedule risk analysis.
This means if a scheduler tells a client, this is a resource-loaded schedule, they are making a professional promise that every single component in that RRC group is present and populated correctly.
It's a contractual promise. So let's start with the core required components, the CRCs. These are the non-negotiables that must exist in every professional schedule model for the fundamental CPM calculation to even run.
So the CRC ensures we can calculate the critical path, track basic progress, and figure out our flexibility.
Yes. The emphasis here is on defining the scope of time. Under duration, you have to track multiple concepts. Activity original duration, that's the baseline activity remaining duration, activity actual duration, and activity total duration.
And the project-level versions of those two.
Right. If you don't track the original duration, you can't measure variance against your baseline. It's that simple.
Then we get into the dates, which are the outputs of the CPM calculation engine.
Absolutely. We require the activity actual start and finish dates to track execution. But the CPM engine's real power comes from calculating the activity early start-finish date and the activity late start-finish date.
And those are the calculations' truth.
They are. They define the absolute earliest and latest an activity can start or finish without delaying the overall project end date.
And that truth, that calculated window of time, is defined by float.
Both free float and total float are core required components. Total float is the essential measure for identifying the critical path. It tells you the total amount of time an activity can be delayed without delaying the project finish date.
Okay, so what's the distinction between free float and total float? Why are both required?
It's a great question. Total float measures flexibility relative to the end of the project. Free float is much tighter. It measures how much an activity can be delayed without delaying the start of its immediate successor activity.
No.
You need both, because free float is often the trigger for immediate action at the task leader level, while total float is the measure of risk exposure for the project manager. If you consume total float, the project is closer to being delayed. If you consume free float, you risk messing up the next team's work right now.
That's a great distinction. Finally, for the core components, we have to track physical progress.
Yes. You have to track progress using either the activity physical percent complete or the activity duration percent complete.
And I'm guessing using physical percent complete is usually considered the better practice for accuracy.
Typically, yes. Duration percent complete just assumes that the remaining effort is proportionate to the remaining time, which is often false in the real world. Physical percent complete relies on quantifiable milestones like foundation poured or code reviewed, which aligns much better with earned value calculations. You just have to choose one method and apply it consistently.
And to make the whole calculation network work, you need the logical relationships.
The finish to start FS relationship is the core required logical dependency. Activity A must finish before activity B can start. Without FS, you don't have a logical sequence of work, and the critical path calculation is completely compromised.
Okay, that covers the baseline. If your schedule model has all those core required components, you have an auditable, functional CPM baseline. But now we add the layers of sophistication. Let's start with the resource required components, RRC.
These are only mandatory if you have a resource-loaded schedule. That means you're using the schedule to track and manage specific resource capacity, demand, and availability.
So if I just allocate a lump sum of money to a task, RRCs aren't mandatory. But if I assign John, the welder, and his specific welding machine to that task, then RRCs kick in.
Exactly. The focus shifts to the definition and quantification of those resources. You need the resource calendar, which specifies when John is available, holidays, shift times. You need the resource ID and resource type. And you need the resource assignment, which formally links John and the welding machine to that specific activity.
And you also need to quantify the work they're actually doing.
That's the quantification layer. Activity, resource, actual quantity, remaining quantity, and total quantity. You need these metrics to run resource leveling algorithms, to manage potential overallocations, and to forecast your exact resource needs months in advance. Without these RRC components, any attempt at professional resource management in the schedule it's merely guesswork.
Okay, let's move to cost integration.
Yeah.
The EVM required components, ERC. This is where schedule rigor meets financial accountability.
And this is non-negotiable for large-scale federal, defense, or highly regulated projects. If you claim EVM integration, you must have these components. They directly tie the schedule activity to the financial tracking system.
So give us the bridge components. How do we link time to money?
We need activity, actual cost, the money spent to date. We need the ultimate financial baseline value, the budget at completion, BAC, which sets the total planned cost. And we need the forecasting values. Estimate at completion, EAC, and estimate to complete, ETC. These define the financial scope and reality of the project.
And crucially, we need the organizational alignment to make sure the reporting lines up.
Precisely. To ensure the schedule activity reports the right dollar value to the right reporting structure, you need the identification components. The EVMS work package identifier, the control account ID, and the WBS ID.
The control account is the critical intersection.
It is. It's the management point where scope, schedule, and budget all meet. If you can't link your activity to a control account, you can't perform credible earned value reporting.
That makes the ERC components the absolute interface between the timeline and the accounting department.
They're the translator. And finally, the most advanced layer, risk-required components, KRC. This is mandatory only if you're performing advanced schedule risk analysis, like using Monte Carlo simulations to understand the probability of completion.
So if the schedule needs to move from a static plan to a dynamic model of uncertainty, we need KRCs.
Exactly. A deterministic schedule using only CRC gives you one answer. The project finishes on June 1st. A probabilistic schedule using KRC gives you a range of answers. There's a 50% chance of finishing by June 1st, and an 80% chance of finishing by July 15th.
And to do that, you can no longer operate on single-point estimates.
Correct. So we need the 3-point estimates for duration, often used in PERT analysis. KRC requires 3 duration fields for every activity. Activity most likely duration, optimistic duration, and pessimistic duration.
That requirement alone fundamentally shifts the entire effort of schedule management. Instead of arguing about a single date, you're now arguing about the range of uncertainty for every single task.
And you need components that report the findings of the risk analysis. Things like the Activity Risk Criticality Index, which tells you how often a specific activity falls onto the critical path when you run thousands of simulations.
That sounds incredibly useful.
It is. An activity that's not critical in the baseline but has a 70% risk criticality index is more dangerous than an activity that is critical but has very low variability. You also need the activity cumulative probability risk distribution to communicate likelihoods and, of course, a risk ID to link it all back to the project's formal risk register.
Wow. That catalog is a profound demonstration that a professional schedule model isn't a simple picture. It's a highly structured database designed to support specific, rigorous analytical methods like EVM and Monte Carlo analysis.
It is. But now we have to address the strategic dilemma that's embedded within the system, the components that don't play by the rules. We need to talk about the dangers highlighted in the source material. Components classified as not scored, NS.
Not scored. This sounds like where reality clashes with calculated logic.
It is exactly that. The NS classification overwhelmingly applies to the constraint components. These are elements that impose date restrictions, effectively overriding the standard CPM calculation. We're talking about components like as late as possible, finish on, mandatory finish date, and start not earlier than.
So why are they not scored?
Because they impose a fixed reality that is independent of the network logic. The CPM engine calculates the early and late dates based on durations and dependencies. That's the math.
Right.
But if an executive or a contract imposes a mandatory finish date of May 30th, and the logical calculation says the earliest I can finish is June 10th, I have now forced the schedule to accept a date that the math does not support.
So the critical insight here is that these NS components potentially override the calculated truth of the standard CPM logic.
They do, and this is a very common practice, driven by business needs or contractual mandates. However, good practices dictate minimizing their use precisely because they risk creating a fundamentally flawed schedule model. When you use a mandatory constraint, you may be hiding underlying logical risks.
But if I'm told by the client that this must finish on May 30th, what choice do I have but to use the mandatory finish date?
And that's the professional dilemma. If you use the constraint, the schedule's resulting take. Total float numbers become misleading. If the CPM calculation says the activity should finish June 10th and you force it to May 30th, the software will often calculate massive negative float.
But that float isn't real.
It's artificial. It's a constraint violation, not an inherent logical problem. And the danger is that schedulers might then try to mask that negative float by introducing other flawed logic, which further degrades the model's integrity.
So the goal is to resolve the conflict between the calculated truth June 10th and the mandate May 30th by changing scope, resources, or logic before you input a constraint, to make the schedule calculation driven.
Absolutely. The professional scheduler's job is to tell management the calculated truth, even if it is uncomfortable. Using these NS constraints too often creates a schedule that is merely a document of intent rather than a predictive model of reality.
Okay, finally, let's briefly touch on the optional components. These are the elements that enhance the schedule but aren't strictly mandatory for the base R, RRC, ERC, or KRC requirements to be met.
These provide flexibility and depth. For instance, many of the advanced earned schedule metrics we just discussed, ES, PV, SPIT, CPI, are often classified as optional.
Wait, hold on. If earned schedule is so critical, why isn't it required for every EVM integrated schedule?
Because the basic ERC requirement focuses on ensuring you have the data fields necessary to report cost variance EV, PV, BAC. While ES is analytically superior for time, a tool could theoretically meet the minimum ERC requirements without explicitly generating the ES components.
So it's about the letter of the law versus the spirit of the law.
In a way, yes. Any professional scheduler would still pull in ES and SPI to enhance their analysis, which is why they exist as key optional components.
What are some other examples of optional flexibility? More complex relationships.
Yes, relationships like finish to finish or start to start. They add complexity, but might not be required for the basic critical path calculation, which can run using only finish to start. Or detailed financial tracking, like resource rates or prices. They enhance the model, but their absence doesn't inherently break the core required analytical function.
What a detailed breakdown. We've gone from the high-level governance plan through the necessity of tailoring communication to all stakeholders, down into the scientific accuracy of time metrics like earned schedule, and finally, into the forensic details of the components needed to run a professional CPM engine.
And the synthesis is clear. Schedule management requires total integration. The schedule management plan aligns everything, including training and data policies, with the WBS and the scope. If that alignment breaks, control is impossible.
And the primary goal of these advanced scheduling metrics is to accurately measure time, not just cost. Earned schedule is essential because it corrects that critical EVM blind spot late in the project and provides objective IEACT forecast.
Giving you the true time variance, SVT, and the time efficiency, SPI.
And consistency is maintained through that component catalog. Knowing whether a data point is core required, resource required, EVM required, or risk required ensures the model actually supports the specific advanced analysis it claims to perform.
Absolutely.
We've established that a project schedule model is so much more than a timeline. It is a critical communication, risk management, and forecasting engine. Effective project control relies entirely on adapting your reporting level to your audience, from the level 0 executive summary to the level 5 task detail, and choosing the right combination of required components to accurately model reality.
This mastery of the clock requires discipline, governance, and an unwavering commitment to calculation over assumption.
Which brings us right back to that thorny issue we closed on. The power and peril of those not scored constraint components.
The mandatory finish date? The start not earlier than.
These are elements that override the logical, calculated network truth that the CPM engine generates.
Right. So if the calculation tells you one thing, but a constraint dictates a different date, we have to ask, does that mandate automatically become a fixed reality just because management decreed it?
Or, when a constraint is imposed that violates the critical path method's calculated truth, is the scheduler merely inserting the project's biggest self-imposed risk directly into the baseline?
Think about the professional position you're in. How often does a not scored element end up dictating the entire project's success or failure simply because the scheduler wasn't allowed to report the critical path's calculated truth?
And instead had to mask that internal conflict with an imposed unrealistic date. The integrity of your entire project control system hangs on that one decision.
Until next time, keep diving deep into the data.
Okay, let's unpack this. We are moving past that, that glossy project presentation, the simple multicolored Gantt chart that everyone loves to hate, and we're diving deep into the technical architecture that sits underneath it.
Right.
Our mission today is to figure out why some project schedules actually function as reliable, predictive roadmaps, while so many others are essentially just expensive wish lists.
Exactly. They're just doomed to fail the moment the first activity slips. And that's the core distinction we need to make clear for you, the listener. We're really defining schedule maturity here.
We are. We're focusing on what separates a robust, world-class schedule Model 1 that gives you real performance forecasting and genuine risk management from a basic document that's only used for administrative tracking.
So our deep dive today, it's really anchored in professional scheduling standards, and we are going to walk you through this whole catalog of specific data components, the required architecture, really. Yeah, the architecture that elevates a schedule to that mature predictive status. And this knowledge is, it's immediately practical.
How so?
Anyone reviewing a project plan, whether you're a stakeholder or a project manager, you can use this classification system to immediately spot whether the schedule is built for true project governance.
Meaning it contains the data required to achieve robust control.
Precisely. Or if it's just, relying on hope and a bunch of rigid deadlines.
Okay, so let's lay out this architectural hierarchy first. The sources organize all these components into really distinct categories, and it's all based on their function and their mandatory status. This is sort of the scaffolding we need to understand.
It is. And at the absolute foundation, you have the CRCs. That's core required components.
The non-negotiables.
Absolutely. The bare minimum data fields and structural elements that are essential for any schedule model to calculate a valid critical path. If you are missing these, you don't have a schedule. You just have a timeline.
A pretty picture.
A pretty picture. That's it.
And then we move into the conditional requirements. These components are mandatory only if you decide to engage in more specific, more advanced project management practices.
Exactly. And we have three main conditional categories there. First, the RRCs, which are resource required components. They're mandatory if you are resource loading the schedule.
Okay, makes sense.
Then you have ERCs, the earned value required components. Mandatory if you're applying earned value management, so linking time and cost together for performance reporting.
And the third?
The KRCs, or key risk components. And those become mandatory if you're performing schedule risk analysis, like a Monte Carlo simulation.
So those three, RRC, ERC, KRC, they really define the project's ambition. Is it resource aware, is it cost controlled, or is it risk aware?
That's a great way to put it. And beyond those, you have the optional components.
So these enhance functionality.
They do. They're still part of a maturity assessment score, but they aren't mandatory for the schedule to be valid. A perfect example is using an activity code. It allows for complex filtering and customized reporting based on, say, work breakdown structure or contract type.
And finally, and this is the category I find most revealing, the NS, or not scored components.
These are so crucial to understand. NS components are typically constraints, fixed dates that schedulers use to lock down certain tasks.
And they're not scored for a reason.
A very important one. Their very existence has the potential to completely disrupt the logical critical path method, or CPM calculation. If you see a schedule that's just riddled with NS components, it honestly doesn't matter how good its CRCs are.
Why not?
Because its logical integrity is compromised from the start.
Wow, so that distinction between the required components that build mathematical integrity and these not scored constraints that actively disrupt it, that's really the core lesson we need to internalize today.
It's the difference between managing a network and simply tracking a calendar.
All right, let's start with that absolute foundation then. The core fundamentals, the CRCs, the things that form the backbone of the critical path method. If you're building a schedule that you intend to trust, these are the ingredients you just cannot skip.
And we have to begin with the critical path itself. It's a required component, a CRC, and it is the calculated sequence of activities that dictates the project's shortest possible duration.
Okay, hold on. It's the longest path of linked activities through the network, but it determines the shortest duration. That seems a little counterintuitive. Can you break that down for us?
I can, yeah. It's a common point of confusion.
Yeah.
Think of it like this. Every other activity in your project has some kind of margin, some slack, or what we call float.
Meaning if it slips a day or two, it doesn't immediately delay the project finish date.
Exactly. The critical path has zero float. It is the one sequence of activities where one slip means the whole project slips. Therefore, the longest path of tasks, the path that takes the longest total time to complete when you add up all the durations, that's the one that controls the overall end date.
So if you shorten an activity on the critical path, the project duration shrinks.
And if you lengthen one, the project lengthens. That's what makes it the cornerstone of CPM scheduling.
So it's absolutely essential for identifying exactly which activities are the true drivers, the ones that have to be managed most closely to prevent any overall delays.
That's it.
So what are the good practices for making sure that critical path is actually valid and not just, a line on a chart?
Validity really requires three things. 1, logical, well-defined relationships between activities. 2, durations that are empirically derived, so based on past data or expert judgment, not just arbitrary guesses. And 3, and this is crucial, structural integrity.
Structural integrity.
You have to avoid open-ended activities. Every single activity, except for the absolute project start and the absolute project finish milestones, needs both a predecessor, something before it, and a successor, something after it.
If activities are just left dangling,
Then they don't contribute to the critical path calculation. The path the software shows you becomes fictional. It's meaningless.
that makes perfect sense. I mean, if you're missing the logic, the CPM can't actually calculate the duration. It's just showing you a disconnected list of tasks.
Right.
Okay, moving on. Another vital CRC is the activity original duration.
This is one that's often overlooked in its significance. It's the initial planned duration for an activity that you set before any progress is reported.
And the key here is that it doesn't change once work starts.
It remains fixed forever. It is the historical baseline against which you measure all your actual performance.
It's the promise you made at the beginning of the project.
Yeah.
If you go and change it later, you completely erase your ability to measure deviation accurately.
Exactly. And the sources are very clear on this. You need to document the estimation method. Was it based on historical data, expert input? That documentation supports accountability. But what's really fascinating is the rule attached to it.
The duration rule.
Yeah, the rule is to keep activity durations shorter than 2 to 3 reporting cycles.
And that's the management tool aspect you mentioned earlier.
Yeah.
How does that ratio of, say, 2 to 3 cycles directly translate into better control and visibility?
Let's just run a quick scenario. Imagine your project reports progress monthly, right? And you have an activity that's scheduled for a 10-month duration.
Yeah.
You report 0% complete for month 1, maybe 10% for month 2, 20% for month 3. You might think you're on track, but then you get to month 6, you realize the complexity is way higher than you thought, and you still have 60% of the work left.
And by then, you've lost 6 months of recovery time. The problem wasn't visible until it was huge.
Precisely. But now imagine if that 10-month activity had been broken down into 5 smaller 2-month activities.
You'd have much faster feedback. You'd know after the first month if you were on track for that smaller piece of work.
Exactly. If your cycle is monthly, a 2-month activity duration means you get feedback at 50% completion during the first reporting cycle. Hitting that 2 to 3 cycle limit ensures every activity is frequently reviewed and its status is actionable before it becomes an irreversible problem.
So it's not just a guideline, it's a rule.
The standard says if a task is longer than 3 reporting cycles, you must decompose it further. This forces managers to segment work into controllable chunks.
It turns duration into a mandatory control mechanism, not just a time marker. That's brilliant.
It is.
Okay, next CRC, the data date, or the as of date.
Think of the data date as the moment the camera shutter closes on your project's status. It's this specific temporal anchor that separates the project world into 2 distinct universes.
Which are?
Reported historical data, everything before that date, which is fact, and all future forecasts, so everything after that date, which is pure prediction.
And this has to be manually advanced, right? That software doesn't just do it for you.
That is so vital. A scheduler must actively move the data date forward at every single reporting interval. It defines the point where your actual stop and the remaining scope begins.
Why is maintaining that strict line so critical?
Because if the data date isn't advanced consistently, or if some activities report status after that date, the schedule model becomes internally inconsistent. You end up with illogical things like negative float or tasks that appear to be starting and finishing at the same time.
Basically, if your historical facts start bleeding into your future predictions, the accuracy of all your forecasts, including the calculated project finish date, becomes immediately suspect.
It is the temporal anchor for all performance analysis. If you see a schedule where the status is clearly from last month but the data date hasn't moved, the logic engine is running on outdated information. You're steering the project with a broken compass.
And finally, within the CRCs, we have milestones. They sound simple, but they're essential.
They're deceptively simple. A milestone is just a significant event with no duration and no resources. Fundamentally, it's calculated as a Boolean flag. It's either complete or not complete.
And good practice says you need at least 2.
At a minimum, a project start and a project finish milestone. But using milestones throughout the project provides these crucial checkpoints for tracking key progress. And visually, they have to stand out, with that unique diamond shape on the Gantt chart.
They represent decision points or completion points, not effort. They define the boundaries of the whole network.
Exactly. They are the markers on the road, not the journey itself. A project without a defined start and finish milestone, well, it isn't really a project. It's just an endless pursuit.
Okay, so here's where we take this schedule to the next level. Once those core CRCs are established, a project can decide to raise its maturity by integrating financial management. And when we integrate earned value management, or EVM, the schedule transforms from a simple time tracker into a crucial financial control tool.
Right, and this requires specific, conditionally required components, the ERCs.
And their main function.
The primary function of the ERCs is to force the team to project forward realistically, both in terms of cost and in terms of the time remaining. This leads us straight to 2 crucial calculated components: estimate to complete ETC and estimate at completion EAC. Both are mandatory ERCs if you're using EVM.
Let's start with ETC. That's the anticipated costs needed to complete the remaining scope. What makes this so different from just looking at what's left in the budget?
The crucial distinction is that the ETC is independent of the original authorized budget. It has to be a realistic forward projection of the actual cost required.
Can you give us an example?
Sure. Let's say the original baseline budget had, $100,000 remaining for task X, but halfway through, because of scope changes or material price increases, the team realizes it will actually take $150,000 to finish. The ETC must be $150,000.
Not the $100,000 that's left in the budget line item.
Exactly. It forces the team to look at actual projected costs, to assign values that reflect current realities, not just historical budget promises.
That sounds like a point of high tension in a project. If the team reports an ETC that is significantly higher than the remaining budget, who signs off on that? Doesn't that immediately trigger conflict with management?
It absolutely does, and that tension is the behavioral component of true EVM forecasting. An honest ETC signals a variance to the baseline, which requires management intervention, maybe a budget replan. That honest projection is the value of the ERC.
The pressure is always to make it look small.
Always. But a mature schedule demands that the project manager resist that pressure and input the honest projected costs to complete.
And the estimate of completion, EAC, builds directly on that realism.
Yes. The EAC is the definitive total cost forecast for the project. It's simply the actual costs, or AC, incurred to date, plus that newly projected estimate to complete, the ETC.
And this gives us our final honest prediction for total project costs.
That's it. If your original baseline budget was $1 million, but your calculated ESC is now $1.2 million, the schedule is objectively forecasting an overrun. And that allows the organization to plan for that outcome now, not discover it at project closeout.
So that separation, looking forward realistically, independent of past budgetary plans, that's the key difference between simple budget tracking and genuine EVM forecasting.
It's proactive, not reactive. Without EAC and ETC, you are merely reporting historical expenses.
Okay, now for the system linkage. How does the schedule actually communicate its planned value and earned value to, say, the main financial system? That requires another ERC, the EVMS Work Package Identifier.
This is a critical administrative component. It's just an alphanumeric designation, a code that links a specific schedule activity to a specific EVM work package or cost account.
So it's the bridge.
It is the physical manifestation of cost schedule integration. It ensures traceability. Without this identifier, the schedule activities can't contribute their planned value or earned value correctly to the financial reporting system. Think of it as the project's social security number. It links all the performance data back to the original source of funding and responsibility.
Speaking of responsibility, we have the Control Account Manager, CAM, which is an optional component.
It's optional, but so valuable. Including the CAM field identifies the specific person accountable for a control account's cost performance and scope achievement. It enhances accountability significantly, ensuring a name is linked to the performance metrics.
Now, to make all these EVM calculations work, to know how much value has actually been earned, we need to know how much progress has been made. That brings us to activity physical percent complete.
This component is conditionally required. You have to choose between this or duration percent complete, but physical percent is, overwhelmingly preferred in mature EVM systems. It measures the proportion of physical work completed as a percentage of the total expected work.
And you mentioned earlier that objectivity here is absolutely key because subjective estimates are so easily manipulated. We've all seen the 90% complete syndrome where everything is perpetually almost done.
That's the danger. To counter that subjectivity, good practice strongly favors objective EVM-based rules. The two most common are the 50-50 rule and milestone-based credit.
Walk us through those.
The 50-50 rule is very straightforward. An activity receives 50% earned value credit the moment it starts, and it gets the remaining 50% only when it is physically finished, nothing in between.
So it prevents someone from claiming, say, 80% completion on a subjective guess.
Right, and the milestone-based rule is even stricter. Credit is earned only upon hitting a specific, verifiable, and predefined milestone like delivering a signed architectural drawing or pouring the final piece of concrete for a foundation.
So an auditor or a reviewer should be able to look at a schedule using these rules and verify the reported progress against an actual document or a physical achievement.
Exactly. It mandates auditability. If a task claims 100% complete, the auditor confirms the final deliverable like a signed acceptance certificate actually exists. This level of objectivity ensures accurate performance reporting linked directly to physical progress, and it removes the guesswork entirely.
So once all these components are in place, the budget, the actual cost, and the earned value based on objective progress, the software can calculate these really powerful optional EVM performance metrics, things that give us the so what for progress.
Right. Let's look at a few of the most important ones, starting with cost efficiency.
Which would be the Cost Performance Index, CPI.
That's arguably the most crucial ratio. It's calculated as earned value divided by actual costs, EV over AC. If your CPI is 1.0, you are earning exactly what you spend. If it drops to, say, 0.75.
That means for every dollar you spend, you're only generating 75 cents of value.
Exactly. It's a universal ratio, which makes it invaluable for executives comparing project performance across different industries or geographies.
And then you have the related deviation measure, cost variance, CV.
Right. CV quantifies the cost deviation as an absolute monetary number. It's calculated as earned value minus actual costs, EV minus AC. If that result is negative, you are over budget by that exact dollar amount.
So CPI tells the executive how efficient the spending is, but CV tells the manager how much money they are over or under budget.
Exactly, which is critical for local management action. And for quick stakeholder reporting, you often see the percentage version.
The cost variance percent, CV percent.
Yeah, this is a relative measure calculated as the variance divided by the earned value times 100. It just provides stakeholders with a quick, high-level understanding of the severity of the cost deviation.
And linking back to schedule performance, we still use the budget to measure that, the schedule variance percent. SV%.
Right. SV% measures relative schedule deviation using the same EVM logic, but it uses plan value, or PV, as the divisor.
Right.
A positive percentage means you are ahead of schedule, but not necessarily in time.
What do you mean?
It means you're ahead in terms of earned budget value. A negative percentage means you're behind in terms of the value you should have earned by the data date. It's a useful early warning signal. But we'll discuss shortly why time-based metrics actually offer a more precise picture of actual time delay.
A mature schedule doesn't just track the plan and the budget. It has to anticipate the pitfalls, it has to quantify uncertainty, and that level of foresight brings us directly to the risk-focused components, the KRCs.
Yeah, the conditionally required components for risk. If a project schedule is going to be subjected to detailed risk analysis, like using Monte Carlo simulation software, it is absolutely mandatory to use KRCs.
And this is the big shift.
It's a fundamental shift from deterministic scheduling, where we assume everything will happen exactly as planned, to probabilistic scheduling, where we actually quantify the chances of success.
And the most fundamental KRC for that is the activity pessimistic duration. We've already talked about the activity original duration, which is the baseline plan. What does the pessimistic duration add to this process?
It adds the worst-case reality check. The pessimistic duration is the longest possible duration for that activity under worst-case yet still reasonably possible conditions. It's the upper limit of uncertainty, and it's defined by experts considering all the variables, weather, supply chain issues, technical failure, you name it.
And this pessimistic duration can't exist in a vacuum for the risk model to work, right?
No, exactly. For a complete risk model, you need a 3-point estimate for every critical activity. You need the activity optimistic duration, which is the fastest possible time, the best case scenario. You need the activity most likely duration, the typical time, often your original duration. And you need this activity pessimistic duration.
And that trio defines the potential distribution of outcomes.
It defines the probability curve for that task. The software then runs what's called a Monte Carlo simulation, which involves executing the entire project schedule thousands of times, sometimes 10,000, or more, randomly drawing durations for each task from their defined 3-point distribution.
And the result isn't a single finish date.
No. The result is a range of finish dates with associated probabilities.
So it tells the stakeholder not, we will finish on July 1st, but something more like, there is an 80% chance we will finish by August 15th.
Precisely. And that is the crucial shift from deterministic to probabilistic. We talk about the p-value. The p50 is the date where you have a 50% chance of completion. The p80 is the date where you have an 80% chance.
So an astute project manager will always commit to the p80 date.
Always. Because that significantly accounts for realistic uncertainty and risk. It ensures the schedule accounts for the things that will inevitably go wrong. If a schedule doesn't have these KRCs, it cannot mathematically defend its finish date.
And this forward-looking dynamic continues. The sources discuss advanced time forecasting, moving beyond the cost-centric nature of traditional EVM metrics. These are optional but really valuable components.
Yeah, they're often associated with what's called earned schedule methodology, and this addresses the limitations of that SV% we just talked about. Well, when a project is heavily delayed, the traditional EVM schedule variance, SV, can often flatline near zero. And this gives the misleading impression that performance has stabilized even while the project is months and months behind.
Earned schedule fixes that.
It does, by measuring time against time, not value against time.
So let's look at the time-based equivalents of ETC and EAC, using that little T notation for time. First, estimate to complete time, or ETCT.
ETCT forecasts the periods, the time units, the weeks or months needed to complete the remaining scope. And just like its cost counterpart, it is independent of the original authorized duration. It is the most realistic projection of remaining time required.
Which is vital for resource planning and communicating delay to the client.
Absolutely. And then you have the estimated duration, ED.
Okay.
The estimated duration is the total estimated periods for the task or the project. It just sums the actual time spent to date, or AT, plus that forecasted time to complete, the ETCT. This gives the project manager a highly realistic total time projection.
Independent of the original and possibly flawed authorized duration.
Right. Using these time-based forecasts, you get a much, much clearer picture of time performance separate from cost performance.
And speaking of time performance, we have schedule variance time, SVT.
SVT is the pure measure of time deviation. It's calculated using earned schedule methodology, measuring the difference between the earned schedule, or ES, and the actual time, AT.
Can you define earned schedule for us?
Earned schedule is defined as the point in time when the value you earned was planned to be earned. So SVT measures true time deviation. If you are negative, that's how many days or weeks you are truly behind schedule. It's a robust, time-based performance tracking measure that complements and often corrects the traditional EVM metrics.
So if we connect this to the bigger picture, using these time-based forecasts and these risk inputs, it really moves the schedule from a static plan that just reports the past to a dynamic, forward-looking predictor of delays and overruns.
That's it. It's the difference between driving a car only looking in the rear view mirror versus using a GPS to look ahead at the next traffic jam. A mature schedule is designed to alert you to future problems and quantify your uncertainty, rather than just recording past failures.
You know, one of the clearest differentiators between a healthy schedule and a fragile one, between a mathematical model and just a calendar display, is how it handles dependencies. The sources are so strong on this, advising we favor logical relationships and actively avoid rigid constraints. This is where most real-world schedules fail, isn't it?
This is absolutely where they fail. This is where we transition from what you must have to what you must avoid. Schedulers, especially when they're facing pressure from a client, they feel compelled to lock in dates. But that act of locking a date in fundamentally breaks the critical path method's ability to calculate, float, and adapt.
Okay, so let's focus on the preferred practice first, using logical relationships. These ensure that dynamic flexibility. The default is finish to start, but for efficiency, we really rely heavily on overlaps created by finish to finish and start to start relationships.
These overlaps are essential for compression and parallel work. We often call it pipelining. Let's look at finish to finish, FF first.
FF means the successor activity cannot finish until its predecessor finishes. Can you give us a relatable example of that?
Of course. Think of a technical document review process. You have drafting the technical manual, that's the predecessor, and final QA/QC sign-off, that's the successor. The sign-off process can't finish until the drafting is complete.
But you can start the QA/QC review while the last sections are still being drafted.
Exactly. That overlap is efficient. FF controls the endpoints, but it allows for weeks of parallel work in the middle.
And the start-to-start SS relationship, that facilitates the start of parallel work.
Correct. SS means the successor cannot start until the predecessor starts. If you're building a complex IT system, installing the server rack must start before cabling the network switch can start. You don't need the server rack installation to be finished to start cabling. You just need the physical activity to begin. This is essential for enhancing efficiency.
And the sources highlight a really crucial good practice for network logic here. They say all activities, except for the project's start and finish milestones, should have at least one FS or SS predecessor and one FS or FF successor relationship.
Yeah.
Why is that mandate so important?
It creates a closed loop of dependencies. It ensures the schedule model is continuous and fully calculated. If an activity is missing a successor, if it's open-ended, the software cannot push the logic forward. That activity effectively drops off the critical path calculation, even if it has massive duration.
It becomes an island.
An island. And conversely, if it lacks a predecessor, it can start immediately, which might be completely unrealistic or hide critical dependencies. A healthy schedule is a fully connected, verifiable network.
We should also briefly mention the last type, start to finish, SF.
Yeah, SF is the least common and most unintuitive. It means the successor's completion depends on the predecessor's initiation. It's almost never used in standard projects because, honestly, the logic can usually be modeled more simply with FS or SS.
All right, now for the antagonists of schedule integrity, the constraints. And these are categorized as not scored components, the NS components, precisely because they are so structurally disruptive.
This is maybe the most important practical takeaway for you, the listener. A schedule analyst should immediately go and examine the constraint log. The worst offenders are the mandatory fixed dates, things like finish on, mandatory finish date, and start on.
These sound so appealing to project sponsors who want certainty, but why do they actively break the CPMF?
They override the very logic the CPM is built on. CPM is designed to calculate dates based on the sequence of work and durations. When you impose a mandatory constraint, you are forcing an activity to start or finish on a specific date, regardless of whether its predecessors are ready.
And this impacts everything.
It impacts both the forward pass, which calculates your early dates, and the backward pass, which calculates your late dates simultaneously.
And the consequence of affecting both of those passes.
The net result is the activity having zero total float. The scheduler has artificially designated that activity as critical, completely overriding the software's mathematical ability to determine the true critical path based on the network logic.
So wait, if I see a schedule where, say, 20% of the activities have mandatory constraints, I should immediately suspect that the critical path shown on the screen is not the actual path controlling the project duration,
Not at all.
but rather a path that's been designated by management decree.
That's exactly right. You are tracking a calendar, not managing dependencies. I once worked on a massive capital project where management mandated a finish-on constraint for every major deliverable. When we actually ran the CPM logic based on the work required, the true critical path was 6 months longer than the mandated deadline.
It's a nightmare scenario.
It was. Because the mandatory constraints zeroed out the float on the path management wanted, the team spent 6 months frantically managing the wrong tasks, while the real drivers were slipping completely unnoticed.
That's what happens when rigidity replaces logic. What about the slightly less aggressive constraints, the soft constraints?
Okay, so these are things like start-finish, not earlier than, and start-finish, not later than. They're less damaging because they only affect one pass of the schedule population. For instance, start not earlier than June 1st only affects the forward pass. It sets the earliest possible date, but the backward pass still calculates the latest possible finish date based on the end of the project.
Which means float can still exist.
It can, unless the constraint is impossible to meet. They limit flexibility due to external factors, like the permit won't be issued before this date, but they don't zero out the float completely.
But the warning remains. Use sparingly.
Sparingly. They should handle external limitations like material availability, not replace the network logic. If you find yourself using a soft constraint because you just don't want to bother linking the predecessor activities properly, you're just hiding bad logic behind a fixed date.
And this raises that crucial point again. Why are mandatory constraints categorized as not scored?
It's a statement about logical integrity. They effectively remove the scheduling software's ability to provide objective feedback. If you introduce too many of these fixed dates, your schedule stops being a predictive, dynamic model and it just becomes a static display of management deadlines. The project manager loses the most powerful tool, the float calculation, that shows where they have room to maneuver and where they must focus recovery efforts.
And we have to remember the caveat here, tool variability. The source notes that component behavior, especially how constraints react to the data date, can vary a lot between platforms.
That tool variability is massive. Some software will automatically move a start-on constraint forward if the data date passes it. Others will leave it behind, instantly generating a nonsensical schedule paradox. Internal project standards have to be incredibly strict on constraint usage to mitigate these risks.
To wrap up our deep dive into schedule maturity, let's just summarize the key takeaways that will allow you, the learner, to immediately spot the difference between a mature plan and, well, a flimsy wish list.
First, maturity requires the presence and integrity of all the required components. The CRCs, your critical path, data date, milestones, original duration, they must be there and they must be correctly modeled. And on top of that, the necessary conditional components, the RRC, ERC, KRC, they must be present based on the project's need for resource, cost, or risk integration.
So if you're doing EVM, you absolutely must have EAC, ETC, and that work package identifier.
No exceptions. Second, good practices overwhelmingly emphasize logical relationships, like finish to finish and start to start, over constraints. This is fundamental to maintaining the mathematical integrity of the CPM calculation. It ensures the schedule can dynamically predict changes rather than being dragged along by fixed dates.
And third, the schedule has to be transparent and objective in its creation and its tracking.
Yes. This means documenting how all your durations are estimated, using historical data or expert input, and relying on objective, auditable EVM-based rules like 50/50 or milestone completion for progress measurement. You have to aggressively avoid subjective estimates that just mask performance problems.
So what does this all mean for someone who's just reviewing a project schedule? It means looking beyond the pretty pictures, looking past the presentation layer, and checking the fundamental plumbing.
That's right.
If you open the schedule and see that the constraint column is heavily populated, or if you can't find clear ETC and EAC numbers on an EVM project, or if the average duration is 10 times the reporting cycle, you know that schedule is fragile.
It is. A schedule that only reports percentage complete is miles away from one that calculates ETCT, EAC, and activity pessimistic duration. You now know what data points to hunt for.
So let's end with a final thought for our listener to take away.
We've established that constraints like finish on actively disrupt the mathematical integrity of the critical path. They zero out float, and they often force project managers to focus on the wrong tasks. So if you encounter a project schedule that's just riddled with mandatory constraints, ask yourself this one fundamental question. Is this schedule actually calculating a true critical path based on the sequence of work? Or is it merely displaying a series of fixed political deadlines that'll utterly fail the moment the first task slips? The challenge for every project manager is not just creating the schedule, but ensuring its continued logical integrity, even when external pressures demand artificial rigidity. Only that logical integrity allows the schedule to truly predict the future, rather than just record project history. Okay, let's unpack this. We are diving deep into the architecture of project planning, and we're zeroing in on a really crucial question. How do the leading bodies in project management actually assess the quality, the reliability, and I guess the sheer maturity of a schedule model?
Now, for anyone who's building or, relying on these complex project schedules, I'm talking especially about those built using the critical path method or CPM.
Right.
That the difference between a schedule that works and one that's broken can be the difference between success and catastrophic failure. We're trying to move past just software features here and really focus on the structural integrity.
That's the core of it, isn't it? We are taking a highly targeted approach today. Our mission really is to give you, the listener, a shortcut to expertise on Section 5 of the practice standard for scheduling what's known as the PMI Conformance Index.
Exactly.
I mean, if you need to evaluate a multi-million-dollar schedule and quickly figure out if it's a viable plan or if it's just, aspirational art, this framework is your answer.
And this index, it's so much more than a simple checklist. It really represents a global consensus on what makes a schedule model robust, reliable, and mature. It's the structured analytical grading system, the one used to score schedule quality from literally 0% to 100%.
So what does a sound and achievable schedule actually look like under this microscope? We need to break down the specific components that are mandatory, the criteria for using them properly, and this is the big one, how to interpret that final conformance score. Because, as we're about to find out, you could score a 95% and still fail the baseline viability test.
That's the critical point. We are defining the absolute minimum standard required for professional scheduling practice, and we're going to explore the consequences when those foundational requirements are missed.
So I want to start with the big picture, the conceptual framework. Why this rigorous indexing system in the first place? Why did the Project Management Institute feel the need to formalize schedule assessment to this degree?
It was really driven by necessity. For decades, schedule quality assessment was often subjective. It relied so heavily on the experience of whoever was doing the review.
The gut feel of the senior planner.
Exactly. The primary purpose of the conformance index is to inject objectivity into that process. It measures how effectively a schedule model incorporates these very specific, defined components, the behavioral rules that go with them, and, the established good practices from the rest of the standard.
So it formalizes quality control.
It formalizes quality control, and it takes the guesswork out of due diligence.
So it's not enough just to say, yes, we have a critical path. You have to actually demonstrate that you're using the critical path correctly.
Precisely. That it's calculated properly, that it's free of artificial restraints, and that it is the actual driver of the completion date, not just something that looks nice on a chart.
Right.
And the index provides two extremely valuable outcomes for any organization that's managing projects. First, it gives you that objective evaluation of the model's quality. That's the due diligence piece.
Okay.
But the second function is, I would argue, more critical for the teams on the ground. It identifies the precise, specific areas where the schedule is weak. It gives you targeted guidance for improvement.
So it moves you beyond just saying the schedule is messy.
Exactly. It moves you to, you are failing component 2.3.1, activity resource, actual quantity because of inconsistent data entry. It's actionable.
I find that incredibly useful. It transforms a quality assessment from what could feel like a punitive measure into a diagnostic tool.
That's the perfect way to put it. It's a diagnostic tool.
Right.
So when you see a higher index score, it's not just a vanity metric. It directly correlates to a better application of those scheduling components.
Which in turn
dramatically increases the likelihood that the final schedule is sound, achievable, and reliable for forecasting. It gives project sponsors genuine confidence.
Reliability seems to be the operative word here, but we have to tackle the elephant in the room right away.
Yeah.
The absolute distinction the standard makes between a schedule being merely conformant and being viable.
Yes. This is the essential go-no-go point. It's a hard line. The standard says that omitting what we call the core required components, or CRCs, results in a non-conformant schedule.
Okay.
And critically, a non-conformant schedule may not be viable.
What does viability even mean in this context? Because a schedule can open up and the software can look fine, but it can still be non-viable, right?
Right. Viability means the schedule is structurally sound enough to perform its primary functions. Can it accurately identify the true critical path? Can it reliably calculate float and forecast real SIC completion dates?
Can it support resource leveling?
Can it support resource leveling and management decisions? If the structural integrity is compromised, say, by misusing constraints or missing key data, it's non-viable. It doesn't matter how attractive the Gantt chart looks.
So full, perfect utilization of the required components is the absolute minimum baseline for conformance.
It is the baseline.
And if you miss even one of those required components, you're instantly relegated to a status we'll get into later, developmental. Which I have to say sounds like a very polite way of saying failing to meet the minimum professional standard.
It is. The consequence is immediate. Your schedule is judged as fundamentally unreliable for serious management use. And we have to stress this again. The assessment is intensely focused on the proper use of the component according to good practices, not just the mere presence of a data field.
Okay, let's elaborate on that distinction between presence and proper use, because I think that's where a lot of teams slip up. Give us a real-world example of a core required component being there, but being improperly used, leading to a failure.
A classic one is the core required component called data date, sometimes called the status date.
Okay, every schedule has one.
Every schedule must have one. Its presence is just having a date entered into the field. Simple. Its proper use, however, means that date is current and accurately reflects the moment in time the schedule was last updated with progress. So if an assessor comes in and finds the data date is 6 weeks old, or, even worse, they find activities marked as in progress that physically started before the data date.
That's a huge red flag.
It's an immediate failure of that component. You lose the point, and because it's a CRC, you fail the entire viability check right there.
So you can't just populate the field with a placeholder date and call it a day. The data integrity has to be impeccable. It has to reflect reality.
Absolutely. The quality of the input is paramount. And this adherence to good practice, it directly reflects the schedule model's maturity. A high conformance score suggests that the organization operates with discipline, its data is reliable, its controls are robust, it's evidence of a high scheduling capability.
But you mentioned a critical caveat earlier, and I want to push back on it a little. We've established that a high score suggests reliability, but you caution that it does not guarantee project outcomes.
Yep.
So why spend all this time achieving 100% technical perfection if external factors can still derail the project? Doesn't that high score sometimes give teams a false sense of security?
That's a profound point, and it's a necessary dose of reality in project management. A high score means you built the perfect analytical model. Think of it like a Formula One race car.
Okay.
A 100% conformance score means the engine, the transmission, the tires, the computer systems are all flawlessly built and tuned according to the optimal engineering standard. But
if the driver makes a mistake,
or the track surface changes unexpectedly, or a competitor violates the rules, the perfection of the car doesn't guarantee a victory.
so the schedule structure is really just one part of the equation.
Exactly. Conformance confirms the structural health. It ensures the critical path is mathematically accurate. It minimizes risk that comes from the planning process itself. But if your fundamental assumptions, let's say the original duration estimates for key activities, were just fundamentally flawed from the start.
The old garbage in, garbage out problem.
Precisely. Or if external political or economic factors intervene, the high score only confirms that you have a perfect plan based on imperfect premises. You still dramatically reduce the structural risk, but you don't eliminate execution risk or assumption risk.
That distinction is vital for anyone listening. Achieving a high score is about professional rigor, not about waving a magic wand.
It means you eliminated the risk that the schedule model itself, its logic, its calculations, its data, will be the source of failure. And that, in itself, is enormous progress.
So let's focus on that foundation now, those core required components. The standard establishes 36 of these CRCs as the fundamental DNA of any sound schedule, whether it's a 2-month office move or a multi-year dam construction. Why 36? What's special about that number?
The 36 CRCs represent the irreducible set of elements needed for a schedule to fulfill its basic mission under the critical path method. That mission is calculating dates, managing dependencies, and controlling progress. They are the absolute non-negotiables.
So if you miss one,
If you miss, say, the requirement for activity logic, the dependencies between tasks, then your critical path calculation is based on arbitrary dates, not network reality. It's meaningless. If you omit remaining duration, you lose the ability to accurately forecast future completion based on the progress you've actually made.
so the minimum goal for any professional scheduler is not optimization, it's not about scoring well, it's just about mastering and flawlessly implementing those 36 CRCs. That's the baseline professional entrance exam.
It absolutely is. If you fail to use even one of those 36 properly, you're signaling that you lack the fundamental competence to build a reliable CPM model, at least according to this global standard. This rigorous focus gives the most immediate, actionable feedback. Fix the foundation before you even think about worrying about the penthouse suite.
That sets the stage perfectly for the taxonomy of all the components, because once we secure that base of 36, the complexity scales up based on what the project's actual mandate is.
When you look at the master list of components, the sheer quantity can be a bit intimidating. I mean, we're talking about over 100 specific schedule attributes.
Right.
But the index's true strength is in its classification system. It immediately defines the priority of every single element.
So let's break that classification down. We've got three main categories based on necessity and impact: required, optional, and not scored, or NS, components. The first two contribute to the score, and the third is more of a warning label.
Exactly. And the required components are where we spend most of our attention because they're the ones that determine that minimum pass-fail threshold.
Let's dive deeper into those required components, starting again with the universal non-negotiables.
These are the core required components, CRCs. As we said, there are 36 CRCs, and they are mandatory for every single schedule model. If you think of the schedule model as a car, the CRCs are the engine, the wheels, the steering, and the brake pedal. You just can't drive without them.
Give us a few more examples of CRCs, and, more importantly, what happens if they're used improperly, beyond just losing a point? What's the real-world impact?
Okay, take activity logic. We touched on it. If a task has no predecessor or no successor, it's called an open end. The calculation engine cannot accurately trace the impact of that activity's duration on the total project float or on the end date.
It's just floating out there in space.
It's an island. And if you have too many of those open ends, your critical path can be artificially shortened or, worse, become completely arbitrary. Another CRC is calendar definition. If your schedule relies on people working an 8-hour, 5-day week, but the calendar assigned to an activity incorrectly applies a 24/7 calendar,
Whoops.
your durations will be drastically underestimated, and the date calculated will be impossible to hit. The failure isn't just a point loss on a score sheet. It's a structural integrity failure that renders the schedule useless for prediction.
That provides the necessary weight to the word required. Now, the other group of required elements are the conditional required components. This is where the index gets really intelligent and scales.
Yes. These become mandatory only if the project contract or an organizational policy or the specific scope requires them. This prevents a simple internal IT project from being evaluated against the same metric as a massive government-mandated construction program.
And we have three categories here, driven by resource management, financial control, and uncertainty assessment. Let's start with resource management.
That's the resource required components, or the RRCs. If your contract requires resource loading, which means you have to track, manage, and report on specific resources like manpower, equipment, specialized teams, then these 13 RRCs are instantly added to your mandatory list.
13 RRCs. Why so many just for resources? That seems like a lot.
It does, but it's because resource management integrates the schedule with real-world capacity constraints. You need components like resource assignment to define who's working on what. You need resource leveling to manage conflicts when someone is over-allocated.
Sure.
And if you're required to report on actual hours burned, you need activity resource actual quantity. If you claim you're doing resource loading but you miss any of these 13, your resource management data is incomplete or unreliable, and you fail that conditional requirement.
So if resource loading is mandated, your minimum required component count immediately jumps from 36 to 49.
Correct. Next up, we have financial control, which in this world means earned value management, or EVM. These are the EVM required components, the ERCs.
Okay.
If EDM or earn schedule is required for performance measurement and financial tracking, and this is often mandated on large federal projects, then 9 components become mandatory.
9 components for EVM. What are you looking for there to ensure proper integration?
We're talking about components like the estimated completion, or EAC, which is central to forecasting your final cost outcomes, and something like the EVMS Work Package Identifier, which is critical. It ensures that the schedule activities align perfectly with the formal financial accounting system.
So the schedule and the finance system are speaking the same language.
Exactly. If you misalign those identifiers, you can't reliably calculate your cost performance index, your CPI, or your schedule performance index, your NPI. And that renders your whole earned value analysis useless for the client.
And finally, managing uncertainty. The risk-required components, or KRCs, I assume these become mandatory if a comprehensive schedule risk analysis, like a Monte Carlo simulation, is part of the project mandate.
Precisely. If risk analysis is required, you have to implement these 7 components correctly. These are the components that shift the schedule from a deterministic model, with fixed dates, to a probabilistic model, which gives you likely date ranges.
What are the key KRCs that allow that transition to happen?
Well, you need components like activity pessimistic duration and activity optimistic duration. These aren't your standard durations. They're inputs for the simulation engine. You needed to define the range of possibilities for how long an activity might take.
The 3-point estimate.
The 3-point estimate, exactly. And then you also need the output metrics, like the activity risk criticality index, which tells you, based on thousands of simulations, how often a specific task landed on the critical path. Without these 7 components, you just cannot credibly claim to have performed a structured, schedule-based risk analysis.
This taxonomy is brilliant, really, because it clearly defines what a simple schedule is versus a complex one based on the contractual need, not just the number of tasks. Let's just run that maximum requirements scenario again.
Okay, if the project is high stakes and requires all 3 resource loading, EVM, and riskier co-required components are 36 CRCs plus 13 RCs, plus 9 ERCs, plus 7 KRCs.
Which gives you a total of
65 required components. And every single one of those 65 must be used perfectly to achieve minimum conformance. A failure in any one, even a small data issue, means you failed the viability check.
Now let's move to the scoring elements that aren't mandatory but still count toward the final index. The optional components. We have 46 of these.
The 46 optional components are there to enhance the model beyond that baseline viability. They provide granularity or detailed tracking or sophisticated reporting capabilities. They are really the features that differentiate a good schedule from an exceptionally mature one.
So if they aren't mandatory, why score them at all? Is this where organizations can kind of pad their score?
Well, they're scored to encourage continuous improvement and the adoption of best practices. You get 1 point for each optional component, but and this is the important part, only if it adheres to good practice. If you choose to use an advanced feature, the standard holds you accountable for using it correctly. For instance, using an activity code for robust WBS reporting is optional. If you use it consistently and meaningfully, you get the point. If you use arbitrary codes or you leave a bunch of them blank, you don't get the point, and you're potentially just cluttering the schedule with useless data.
So it incentivizes utility. You shouldn't include optional components just for score inflation. You should only include them if they genuinely serve the project management team's needs.
Exactly. They are often employed by highly sophisticated organizations or for mega projects where extreme detail is necessary for control.
Okay, let's transition to the final category, which I think offers a great conceptual insight into the whole philosophy of CPM scheduling. Not scored, or NS components. There are 13 of these. Why is the PMI essentially saying we acknowledge these exist, but we won't score them, and we actually discourage their use?
This is probably the most illuminating section of the index for a scheduler. These 13 NS components are actively excluded from the scoring because they have the potential, the inherent tendency, to disrupt or override the fundamental mathematical engine of the critical path method.
So these are tools that introduce artificiality into the network logic.
Precisely. The classic examples are hard constraints. Things like a mandatory finish date or a start no earlier than constraint that's just applied arbitrarily. In pure CPM, the dates are calculated only by activity durations and the logical dependencies between them.
Right, the math.
It's all about the math. When you introduce a hard constraint, you are forcing a date that may not be supported by the logic. You're overriding the math.
And what's the danger of forcing that date? What happens?
The danger is twofold. First, it can artificially suppress the critical path. If you put a mandatory finish date far out into the future, it gives tasks a false sense of float. It can actually hide the real critical path and prevent the team from identifying the true schedule drivers.
And the second danger?
Second, it shifts the schedule's predictive quality from being a logical calculation to being a forced adherence to a date, which may be completely unattainable. The PMI standard is prioritizing schedules that rely on network integrity over those that use these artificial constraints to mask reality.
That is a critical takeaway. So if I'm a scheduler and I'm feeling pressure from management to hit a specific milestone, using a mandatory finish date might appease them in the short term, but the conformance index is telling me that I am actively damaging the quality of the model I'm using to track the project.
You are compromising the schedule's ability to tell the truth. By labeling these as not scored, the standard sends a very strong signal. Use these only when absolutely necessary, like for a legal deadline, and understand that they inherently degrade the purity of your CPM model. A conformance scheduler uses logic dependencies to calculate dates, not fixed dates to bypass logic.
That summarizes the structure beautifully. So the total universe of scorable components, the CRCs, the conditional requirements, and the optional components is 111. That's the universal maximum score.
And this structure ensures flexibility. You address the 36 CRCs first, then you integrate the RRCs, ERCs, or KRCs as dictated by the contract. And finally, you can optimize with the optional components that actually make sense for your project's needs. You don't aim for 111 unless the contract mandates every single conditional requirement and you choose to implement all 46 optional features perfectly.
Let's just confirm that spectrum one last time. Scenario 1. Basic internal project, no conditional requirements. Minimum required is 36 CRCs.
Correct.
Scenario 2. Project requires only resource loading. Minimum required is 49 components.
Yep.
And scenario 3. A highly complex project requiring resources, EVM, and risk analysis. The minimum required is 65 components. The standard adjusts the threshold for minimum viability, but that requirement for 100% adherence to that minimum remains absolute.
Rigidity on the foundation, flexibility on the enhancements. That's the core philosophy.
Now we get to move into the actual mechanics of the evaluation, which is detailed in section 5.2. This is the practical application. Determining that percentage score based on those 111 total scorable components.
The scoring total, as we've established, is 111. That figure is the denominator in our final calculation. It represents the sum of all the components that, if implemented correctly, add value to the schedule model.
And the assessment process follows 6 defined steps. Let's start with the step that determines the context for everything else.
Step 1. Determine project requirements, the starting line. Before an assessor can even look at the first activity, they must establish the minimum required components. This involves answering those 3 critical questions based on the project documents. Is resource loading required? Is EVM required? Is schedule-based risk management required?
This is the step that determines that variable minimum threshold for conformance, which we said ranges from 36 to 65 components. This is the moment the scheduler knows exactly how high the initial hurdle is.
Yes, and this step is all about ensuring fairness. A schedule should only be penalized for missing elements it was never required to have in the first place. This brings us immediately to the most high-stakes part of the whole assessment.
Step 2. Evaluate required components. The go-no-go check.
This is the pass-fail moment. The assessor systematically checks every single component that was defined as mandatory for this specific project, the CRCs plus any applicable conditional requirements, against the established good practices. 1 point is awarded for perfect utilization, 0 for anything less.
You mentioned that the scheduler needs deep knowledge of these good practices. What's a common pitfall here, beyond just the obvious missing data? Where do people get tripped up?
A very common one relates to the proper use of activity original duration, which is a CRC. Good practice requires that the basis of that estimate be documented.
So you can't just pluck a number out of the air.
Exactly. If the duration is simply a number entered by the scheduler with no supporting reference, or if the documentation is vague, like it just says expert opinion and lacks any detail, it fails the good practice test. The component is present, but it's improperly used.
And here is the core structural rigidity of the entire index, the critical threshold.
The threshold is, it's unforgiving. All required components must be fully implemented and 100% utilized correctly. If one single component out of your 65 required components is missing or improperly used, the schedule is immediately flagged as developmental.
That seems incredibly strict. I mean, maybe even punitive. You're telling me that a $500 million project schedule that shows 99% adherence to its 65 requirements but misses one obscure data field is non-conformant,
Yeah.
while a small internal project that only requires the 36 CRCs and implements them perfectly, which might only give it a score of 32%, is deemed conformant. Does that strict pass-fail baseline really serve the project team who put in all that effort?
That's a powerful point, and it's where the index generates the most controversy among practitioners. I get it. However, the standards philosophy is that the required components, especially those 36 CRCs, are so fundamental to the network's viability that a failure in any one of them fundamentally undermines the model's trustworthiness as a predictive tool.
Okay.
That 99% schedule, by missing that one required component, has demonstrated a structural weakness that might, for instance, lead to an erroneous float calculation or an unverified resource commitment, a crack in the foundation.
So the standard prioritizes soundness over raw complexity, or even a high score. A smaller schedule with a perfect foundation is considered better than a massive, complex schedule with even one crack in that foundation.
Exactly. The 99% score is only used for feedback at that point. The schedule is not deemed fit for purpose, and it cannot be designated as conformant. This rule forces schedulers to prioritize data integrity and foundational practices over just adding sophisticated optional features.
Okay, so assuming the scheduler passes step 2, they hit 100% on all the required components. They then move into the optimization phase. Step 3 and 4, evaluate optional components and calculate the raw score.
The assessor then examines the remaining 46 optional components. For each of those, 1 point is awarded if it's present and used correctly. For example, if the scheduler uses activity steps to track progress granularity within a longer task, and those steps are well-defined and updated consistently, that's a point.
And if they're defined but just ignored after that?
0 points.
Yeah.
This ensures that adding complexity doesn't introduce more risk. If you're going to use an optional feature, it must be robustly managed.
Right.
So we calculate the raw score by adding the points earned from the required components, which, if they pass step 2, is the total number of required components, and the points earned from the optional components. This raw score is the numerator for our final percentage.
Okay, so let's use our earlier example. A project where resource loading was required, so that's 49 components. They passed 100% on those 49, and they also correctly implemented 10 optional components. The raw score is 49 plus 10, which equals 59.
That's the raw numerical measure of completeness and adherence to good practice. Now we just convert it to the standardized metric in step 5. Calculate the conformance index, the final number.
And the index is that raw score divided by the total possible score, which is always 111, then multiplied by 100. So let's solidify that 53% figure for our specific scenario.
With a raw score of 59, we calculate 59 divided by 111 times 100. That yields 53.15%. That is the final official conformance index score.
And what does that mean?
It means the schedule model is structurally sound, it's compliant with all of its required elements, plus it has implemented 10 best practice optional enhancements. It's a solid conformance schedule.
That brings us to step 6. Interpret results and outcomes. This is where these scores translate back into project reality. And we have 2 categories of outcomes here.
The 2 categories are binary, and it's all based on the result of step 2. If the schedule meets 100% of all its required components, it is the conformance schedule, and it's scored on that continuum, typically from 32% up to 100%. If it misses any required component, it is a developmental schedule. It fails to meet the minimum standard.
Let's discuss the importance of that 32% figure. Where does that number come from, and why is it so important as a baseline?
The 32% defines the absolute lowest possible score for a schedule that is still considered structurally sound or conformant. It's derived from the simplest possible compliance scenario.
The one with just the 36 CRCs.
Exactly. If a project has 0 conditional requirements, no RRCs, ERCs, or KRCs, the scheduler only needs to implement the 36 CRCs perfectly. The calculation is 36 divided by 111 times 100, which is approximately 32.4%.
So 32% isn't a mediocre score. It is the minimum possible score for a viable schedule. Anything less than that implies a failure of one of those 36 core elements.
Precisely. If a scheduler scores, say, 25% It means they didn't even get all 36 CRCs right. They are missing foundational elements, and the schedule is therefore developmental, regardless of what the raw number is.
What are the immediate actionable consequences for a team that receives a developmental status? This must be a major internal red flag.
Oh, it is a massive red flag, especially in environments where the schedule drives payments or contract milestones. A developmental schedule is, by definition, fundamentally unreliable.
So what happens?
The immediate consequence is usually a required rework cycle. The assessment provides specific feedback. For instance, missing proper documentation of Activity Risk Criticality Index, KRC 2.1, which the team must then address, fix, and resubmit for reassessment, potentially under very tight deadlines. In high-stakes government or complex infrastructure projects, failure to achieve conformance can jeopardize funding or even contract approval.
And on the flip side, what about a high score, say 90%? What does that signal to the organization and to the client?
A 90% score signals exceptional scheduling maturity. It means the team not only mastered all of its required components, let's say all 65 in a fully conditioned project, but also correctly implemented the vast majority of the 46 optional components.
Which says, what about them?
It signals an ability to manage complexity, to perform robust analysis, and to maintain a high standard of data integrity throughout the project lifecycle. It suggests the organization is leveraging its schedule for strategic decision-making, not just for reporting.
The assessment clearly serves as a crucial feedback loop. Even if you're flagged as developmental, the raw score breakdown guides you directly to the weak spots, improperly defined calendars, vague resource assignments, or misuse of logic.
It turns an abstract failure into concrete actions. The scheduler has to use this knowledge proactively. This assessment isn't just a snapshot in time, it's a mechanism for driving continuous process improvement within the scheduling function itself. Schedulers must not only know the 111 scorable components, but deeply understand the good practices associated with them to anticipate the assessment criteria.
The focus on proper usage, not just presence, is the thread that really ties this whole index together. It prevents box ticking and mandates true professional execution.
It formalizes the criteria for what constitutes a mature, reliable schedule model. It takes schedule quality out of the realm of subjective opinion and locks it down into objective, measurable adherence to a global standard. It helps everyone from the project manager to the CEO speak the same language about the structural health of a schedule.
Before we wrap up, I want to reiterate that inherent conflict we discussed earlier, that tension between structural perfection and outcome reality.
It's the essential philosophical dilemma of project controls, isn't it? The PMI Conformance Index guarantees a technically excellent blueprint. It ensures the math works, the dependencies are clear, and the data is consistent. However, the schedule is always a model of reality, not reality itself.
And if the reality, the ground truth, doesn't match the model's assumptions,
Then technical conformance can only mitigate, not eliminate, the risk.
it seems like the index prepares the scheduler for every predictable structural risk that's inherent in the planning process itself, but it leaves the irreducible uncertainty of execution to the broader project management team.
Exactly. You are eliminating structural vulnerability so that when a real problem emerges, like a major supply chain delay or unexpected political interference, you can trust your schedule to accurately calculate the impact and provide reliable mitigation options. You haven't guaranteed success, but you've guaranteed you have the best possible tool to navigate failure.
This has been an extensive and I think a really detailed deep dive into the PMI Conformance Index. We've established that schedule quality is not a feeling. It's a measurable metric defined by a universe of 111 scorable components.
And we learned that the non-negotiable foundation of any reliable plan lies in those 36 core required components. The strict requirement for 100% adherence to these CRCs dictates the viability of the entire schedule model.
The system scales intelligently, allowing schedules to adapt their required components based on project mandates for resources, EVM, and risk, ranging from 36 to 65 mandatory elements. And we understand why the index signals caution around those 13 not scored components. They so often compromise the integrity of the true critical path logic.
And we saw that the minimum bar for entrance onto the conformance score continuum is that 32% threshold, which represents the successful implementation of just the 36 CRCs. Any failure to meet all the required components immediately classifies the schedule as developmental, regardless of its potential raw score.
It truly is the definitive standard for measuring schedule maturity and reliability. But let's return to that philosophical tension, that unavoidable gap between planning perfection and project outcomes.
This is the final provocative thought we want to leave you with. The learner, as you apply this knowledge in your work. We've demonstrated that the conformance index ensures your schedule model is technically robust, logically sound, and compliant with all professional standards.
But
However, if that schedule is 100% conformant, but the underlying assumptions, the productivity rates, the supply chain lead times, or the reliability of subcontractor estimates are fundamentally flawed, how much power does optimal component usage truly have? What element beyond the schedule structure itself, perhaps the realism of the assumptions, the accuracy of the estimates, or the quality of the organizational execution, ultimately dictates the success or failure of a project?
a question to mull over as you build your next viable schedule. Thank you for joining us for this deep dive into the structure of sound project planning. We hope this knowledge speeds up your path to expertise.
Until next time.